Welcome! In this unit, we'll be reviewing your algebra and geometry skills. These are skills you've probably learned before in your high school or previous mathematics courses, but these will be specifically focusing on things that you'll need to succeed in your precalculus and ultimately your calculus classes. Let's begin by looking at an example of when you might need some algebra or geometry skills. Back in the 70s, there was a really popular Tootsie Pop commercial featuring an owl who asked the question, how many licks does it take to get to the Tootsie Roll center of a Tootsie Pop? For those of you who aren't familiar with it, Tootsie Pops were a candy with a Tootsie Roll center and some coating on the outside. I brought my Tootsie Pop today. Well, this isn't actually a Tootsie Pop, it's a little bit larger, but we could ask the question, how many licks would I have to make on this lollipop to get to the candy in the center? So this is basically a math question, although it seems like a candy question. We could do an experiment. Suppose I took this Tootsie Pop, unwrapped it, and suppose I licked it for a minute, and then measured the circumference to figure out how much of the lollipop was I able to lick off in a minute. And suppose I repeat that experiment several times. So I lick it for 1 minute, then I lick it for another minute, and I get some data. Let's look at the data when I licked this lollipop. On this graph here, you see some blue dots. Those blue dots represent the circumference at various points in time during my experiment. As I'm licking this lollipop, I'm keeping track of the circumference at various measurements at various points in time, and I'm denoting them by a blue dot. You notice this data looks like it's sort of straight. If I was going to draw a straight line through the data, most of the data points would be pretty close to that straight line. Let's look at that. Here I've drawn a black line that pretty well fits this data. This is called the line of best fit, and it can be found using a technique called linear regression. On there, I also have an equation for the data. That black equation, y equals negative 0.34x plus 6.34, is the equation of the line of best fit. It's basically an equation for the line that goes through the data as close as possible. Well, let's talk more about what this equation represents and what sort of things we can do with it. Namely, we want to answer that question from the old Tootsie Pop commercial, how many licks does it take to finish the lollipop? Well, let's take a look at our equation. The equation that best fit my data for my experiment was y equals negative 0.34x plus 6.34. Let's pick this equation apart a little bit. The x in the equation corresponded to time. That was the x-axis, or the lower axis on my figure. It basically just corresponded to different values of time for licking the lollipop. The y-axis on my diagram corresponded to circumference. So the y value is a circumference in inches of what the current circumference is at a given time. Normally, when we look at linear equations, we put them in what we call a standard form, or one of several standard forms. In particular, my favorite standard form is the slope-intercept form, in which you have both the slope information of the graph, or how steep that line is, and the intercept, where does it hit the y-axis. We usually denote that as y equals mx plus b. The m corresponds to a slope, the b corresponds to the y-intercept. In this case, our slope value is negative 0.34. The units on that would be inches per minute. Basically, this slope corresponds to how much of this lollipop, how much of the circumference am I licking off in each minute. And the y-intercept, the b value of 6.34, what would that correspond to? Well, that measurement is in inches, and that corresponds to the initial circumference of my lollipop. So in this particular experiment, I had a lollipop that initially had a 6.34 inch circumference. Well, we still haven't answered the owl's question from that commercial, how many licks does it take to finish the lollipop? What information would we be wanting to look for in order to answer that question? Well, that's really asking us to find the x-intercept. We want to know what is the time value, or how long is the time, which corresponds to x, at which I'd finish the lollipop. Finishing the lollipop corresponds to y equals 0. Y was our circumference value, and when I'm done with the lollipop, I should have no more left, so I'd have a circumference of 0. In order to answer this question then, I found my data, I found the line which best fit my data, and now I want to take my linear equation and solve it for the x-intercept. So I plug in y equals 0 to my equation, I move all the x terms to one side, all the constant terms to the other side, and I can solve for x. And if you see by my arithmetic up here, I've gotten that it would take me 18.7 minutes to finish my lollipop, given the data that I've had. Obviously, my data wasn't perfect. It's not exactly a linear function, but in the real world, we very often approximate real-world experiments or phenomenon with some sort of function. In this case, a linear function seemed like a good approximation to my data. Well, let's talk more about what sort of skills will you need to have in order to use algebra and geometry to study problems in precalculus and calculus. We're going to be dealing in this unit with four main types of functions. Those four main types are polynomials, rational functions, radical functions, and problems or functions involving absolute values. Polynomials you can think of simply as sums of powers of x. For example, x squared, x cubed, x to the fourth, etc. Anytime I have a function that's a sum of those type of terms where the base is a variable, usually x, but it could be something else, and the power is an integer like 2, 3, 4, 5, those we call polynomial expressions. The formula I've written down here for a polynomial, you notice it has some strange things, an minus 1, etc. Those a's just are taking the place of any constant coefficient, just any real number, just a number there, and that's going to give us a polynomial. We also will talk about rational functions. Rational functions are functions made up of a numerator and a denominator, where both the numerator and denominator are polynomials. And I just told you what a polynomial was. The one stipulation is, in mathematics, we always have to be careful that we don't want to divide by 0. So with our rational functions, we'll usually make the stipulation that the denominator can't equal 0. The denominator equaling 0 is not part of our domain. There's two other types of functions you'll be talking about in this unit, and that one of those is radical functions. Radical functions are things involving square roots or other type of roots, such as third roots, fourth roots, fifth roots, etc. When you deal with these, we usually denote it by that square root sign that you see in the diagram up there, and you'll know when to recognize those because you'll just see that radical form. Finally, the last function that tends to scare students a little bit, but really isn't that scary at all, is the absolute value function. The absolute value, simply put, is just the positive version of a number. If I put in 3, the positive version of 3 is still 3. However, if you put in negative 3, we want to switch the sign to make the positive version, so negative 3, the absolute value of negative 3, is simply 3. The equation that I've written there is the definition of absolute value. It simply says that if x is less than 0, we want to make the positive version, so I have to change the sign or take negative x. If x was already positive, I don't need to do anything when I take the absolute value of x. I simply keep the value x alone. This kind of piecewise defined function with two parts is one that you'll encounter a lot in this course. So finally, let's talk about what are you going to learn in this unit. In this unit, first and foremost, you'll learn to solve linear equations, just like we did with that lollipop problem. You'll also learn how to solve linear inequalities. Inequality is like an equation, except you'll either have a greater than, less than, or the greater than or equal to, or less than or equal to sign in the equation. For example, here I've shown you a compound inequality. We know that 5x plus 7 is less than 18, but it's also greater than or equal to 3. You'll learn how to solve things like that. Find out what values of x make this expression true. You'll also be learning how to solve inequalities involving absolute values. For example, if I tell you that the absolute value of x minus 3x is smaller than or equal to 2, you'll want to figure out what values of x make that expression true. We'll also learn how to factor polynomials. This is one of those skills that a lot of students tend to remember from high school, but we'll give you a refresher and remind you of those special cases that you may not always remember. Here's an example of a polynomial, x squared plus x minus 2, which I've factored or broken into the multiplication of two linear terms, x plus 2 times x minus 1. Another skill you'll be learning how to do is how to simplify and solve rational expressions. So for example, I've given you a rational expression using an inequality, and you'll learn how to solve what values of x make this rational expression, or a ratio of two polynomials, greater than or equal to 0, also known as positive. Finally, in this unit, you'll also be working with simplifying and solving expressions involving radicals. So we'll be learning the rules of how to manipulate terms within radicals to simplify the overall expression and make it easier to solve certain types of equations. What are the applications that you'll be looking at for algebra and geometry? Well, there's a lot of them, Basically, this section is really focused on giving you some tools and techniques to solve applications you'll be encountering in later sections. So for this particular section, we won't be focused as much on what the applications are, but on getting you some tools to solve later applications. Almost any problem I can think of in math, science, engineering, business is going to involve some sort of polynomials or rational functions or absolute value functions. So these tools will have a wide-reaching effect. When do you use algebra? Well, algebra is going to come up pretty much any time you have some quantity you don't know, some other ones you do know, and you know a relationship between the knowns and the unknowns. Basically, you're using some known information to solve for this piece you don't know. And that's kind of a simplified definition of what algebra really is. Well, thank you, and I really hope you enjoy reviewing your algebra and geometry skills. Thank you, and I'll see you next time.
Let's discuss real numbers. Informally, a real number is a number with a decimal representation. And we represent the set of real numbers by a capital R. Now, there are different subsets of real numbers. The first subset to consider are what we call the natural numbers. And these are just the counting numbers that we're used to. 1, 2, 3, 4, and so on. And we represent the set of natural numbers by a capital N. That is, n is equal to 1, 2, 3, 4, and so on. The second subset to consider is what we call the integers. The integers are all these natural numbers, together with their negatives and 0. And we represent the set of integers by a capital Z. So Z is all the negative natural numbers. Together with 0. And then all these natural numbers. The third subset to consider are what we call the rational numbers, and we represent the set of rational numbers by a capital Q. And these are fractions or ratios of integers. So A over B, where B is not 0, and A and B are integers. Now, the decimal representation of a rational number either terminates or repeats. For example, 1 divided by 2. This is a rational number, and its decimal representation is 0.5, and it stops or terminates. Whereas 1 divided by 3, which is also a rational number, has its decimal representation repeating. It doesn't stop, it repeats. Now, if a real number is not rational, then it's what we call an irrational number. And the set of irrational numbers we represent by a capital I. So these are real numbers that are not rational. So a real number is either rational or irrational. So let's write that up here. Capital R is the rational numbers together with the irrational numbers. And we have that the natural numbers are contained in the integers, contained in the rationals, are contained in the reals. Let's look at an example. Let S be this set, and we want to list the subsets of S, consisting of the natural numbers, the integers, the rationals, and the irrationals. Remember that the natural numbers are the counting numbers, 1, 2, 3, 4, and so on. So looking at S, we see we have 3 here, as well as 10. So these will be our natural numbers. Now the integers are these natural numbers together with 0. And we do have 0 in our list. So let's add 0 here, as well as any negative natural number. Looking at S, we see we have this negative 1 here in the front, but also we have this minus square root 4. Because of the square root, we might have missed this. But isn't the square root of 4 just 2? So this is really just negative 2, which is an integer. So we'll add these to our list as well. Negative 1 and negative square root of 4. Now what about the rationals? All of these integers are rational numbers. Because think of 3, for example. We can write 3 as 3 divided by 1, so we can think of it as a fraction. So we'll have all of these integers, 3, 10, 0, negative 1, negative square root 4. But what else? Looking at S, we have this 3/4 here. That will be a rational number. But also look at this last number here. Again, because of this square root, it might be misleading. But really, this is the same as square root 81 divided by the square root of 4, which is equal to 9 divided by 2. So it is a rational number. So we'll add those two values to our list here. 3/4 and square root 81 over 4. All right, finally, the irrational numbers are any number in S that are not in this set here. Namely, negative square root 5 pi and square root 7. So our irrationals are negative square root 5 pi and square root 7. And this is how we classify real numbers into these subsets. Thank you, and we'll see you next time. Let's look at some properties of real numbers. For example, which real number property justifies each of these 4 statements? Well, let's first recall some properties of real numbers. And we are assuming here that all the variables, both in the example as well as in the table, represent real numbers. Let's look at this first statement here. 5 times AB is equal to 5A times B. It turns out that the property that's being illustrated here is the associative property for the operation of multiplication. It's this property here. So let's write that. Associative property for the operation of multiplication, and we'll just write the little multiplication symbol here. Now, often when students are learning these properties, they confuse associativity with commutativity. With the commutative property, we flip or reverse the order. So the commutative property for the operation of multiplication might be something like this. 6 times 9 is equal to 9 times 6. Notice we are flipping or reversing the order of the multiplication. Think of a commuter going back and forth to school. Whereas with the associative property of multiplication, we're either associating the A with the B first or the A with the 5 first, and the result is the same. All right, what about this second statement here? 4 plus R is equal to R plus 4. This is demonstrating the commutative property for the operation of addition. It's this property here. Notice we are flipping or reversing the order of the addition. So this is the commutative property for the operation of addition. We'll put the little plus here. All right, what about this third statement here? 3u plus 7u is equal to 3 plus 7 times u. This is demonstrating the distributive property down here. But notice that our statement is starting on the right and then going to the left. But that's okay because the equal sign works in both directions. So this third one is the distributive property. All right, and what about this last statement down here? M plus n times 0 is equal to 0. Now remember that m and n are both real numbers, which means that m plus n is also a real number. So this is demonstrating this multiplication property of 0 down here, where m plus n is x. So this last statement is illustrating the multiplication property of 0. And this is how we demonstrate some real number properties. Thank you, and we'll see you next time. Let's look at scientific notation. Scientific notation is a way to express or rewrite a large number or a small number in a concise way. For example, let's write 569,000 in scientific notation. Now, to write a number in scientific notation means the following. It means we can rewrite it in the form a times 10 raised to the nth power, where a in absolute value is between 1 and 10, and n is an integer. So the first thing we need to do here with our number is to move the decimal point until we get a number whose absolute value is between 1 and 10. And you might be thinking there is no decimal point here. But isn't 569,000 equal to 569,000.00? So there is a decimal point. So if we move this decimal point 1, 2, 3, 4, 5 places to the left, we get 5.69, which is equal to our A here. It's the number we're looking for here whose absolute value is between 1 and 10. Now what about n? We need to find an integer n such that 5.69 times 10 to the nth power is equal to this 569,000. Well, since we moved the decimal point 5 units to the left to go from here to here, going in the other direction, we'd have to multiply by 10 to the 5th, or n is equal to 5. That is 5.69 times 10 to the 5th is equal to 569,000. Therefore, our answer is 5.69 times 10 to the 5th. And let's check this. What is 5.69 times 10 to the 5th. This is equal to 5.69 times 10 times 10 times 10 times 10 times 10, 5 times. Or 5.69 times 100,000, which is 569,000. So to go from a big number to scientific notation, n is positive. What about the other way? In other words, what about going from a small number to scientific notation? Again, we'll need to find our a and our n, where a is a number in absolute value between 1 and 10, and n is an integer. So let's look at our number here, negative 0.000000691. In order to find our a, we need to move this decimal point 1, 2, 3, 4, 5, 6, 7 places to the right. Therefore, our a is equal to negative 6.91. But what about our n? We need to find an integer n such that negative 6.91 times 10 to the nth power is equal to negative 0.000000691. Well, since we moved our decimal point 7 units to the right to get to a, then to go in the other direction, we'll need to multiply by 10 to the negative 7th. So n here will be negative 7. That is negative 6.91 times 10 to the negative 7th power is equal to negative 0.000000691. So our answer then is this negative 6.91 times 10 to the negative 7th power. And again, let's check or verify that this is true. Negative 6.91 times 10 to the negative 7th power is the same as negative 6.91 times 1 divided by 10 to the positive 7th power, which is equal to negative 6.91 times 1 divided by 10 million, 7 zeros, or negative 6.91 divided by 10 million, which is negative 0.000000691. So to go from a small number to scientific notation, n will be negative. And this is how we write numbers in scientific notation. Thank you, and we'll see you next time. Let's look at the properties of integer exponents. For n and m integers and a and b real numbers, we have the following properties. The first property states that a to the n times a to the m is equal to a to the n plus m, and is often referred to as the product rule. For example, a squared times a cubed is equal to a to the 2 plus 3, or a to the 5th. The second property states that a to the n raised to the mth power is equal to a to the n times m, and is often referred to as the power of a power rule. For example, a squared cubed is equal to a to the 2 times 3, or a to the 6th. Notice that in the first property, when the base is the same, we add the exponents, whereas in the second property, when you have a power of a power, we multiply the exponents. These properties are often confused, so know when to add and when to multiply. The third property states that a times b to the mth power is equal to a to the m times b to the m, and is often referred to as the power of a product rule. For example, a times b squared is equal to a squared times b squared. We raise both factors to the power of 2. The fourth property states that a divided by b raised to the mth power is equal to a to the m divided by b to the m, and is often referred to as the power of a quotient rule. For example, a divided by b raised to the third power is equal to a to the third divided by b to the third. And here we're assuming, of course, that b is not equal to 0. All right, the fifth property states that a to the m divided by a to the n is equal to a to the m minus n, and is often referred to as the quotient rule. For example, a to the 5th divided by a squared is equal to a to the 5 minus 2, or a cubed. So when the bases are the same and we're dividing, we subtract the exponents. The sixth property states that a to the 0 is equal to 1 for a not equal to 0. 0 to the 0 is not defined for various reasons, and this is often referred to as the zero exponent rule. For example, 3 raised to the 0 power is equal to 1. And the last property to consider here is that a to the negative nth power is equal to 1 divided by a to the positive nth power, and is often referred to as the negative exponent rule. For example, a to the negative third power is equal to 1 divided by a to the third power. All right, let's see an example. Let's simplify the following expression and write our answer using only positive exponents. Since multiplication is both commutative and associative, we can regroup this multiplication as follows. We can take all the numbers first, the 2, the 3, and the 5, and multiply them. So this is equal to 2 times 3 times 5. And then multiply the w terms together. So times w to the negative 5th power times w to the 4th. And then group the v terms together. We have this term and this term. So times v to the negative 6th power times v to the 7th. And finally, we'll group the u terms together. So times u to the 7th times u squared. So this is equal to 2 times 3 times 5 is 30, and then times w to the negative 5 plus 4 by the product rule. Because these bases are the same, we can add those exponents. Same with the v term, so it'll be v to the negative 6 plus 7. And finally, we'll do the same with the u terms, so it's u to the 7 plus 2, which is equal to 30 times w to the negative first power times v to the positive first power times u to the ninth. And then by the negative exponent rule, this is equal to 30 times 1 divided by w to the first power. Remember, we want to write our answer using only positive exponents. And when the exponent of a variable is 1, we usually do not write it. So writing this as one fraction and dropping those exponents of 1 gives us our answer of 30v u to the ninth divided by w. All right, let's see another example. Let's simplify this expression and write our answer using only positive exponents. Well, the first thing we can do is simplify what's inside these parentheses by, again, grouping like terms. So this is equal to, let's group our numbers together, so 6 divided by 3, and then times, grouping our m terms together, we have m divided by m to the negative 1. And then finally, grouping the n terms together, we have n to the negative 2 divided by n squared, still raised to the negative third power, which is equal to 6 divided by 3 is 2, and then times m raised to the 1 minus a minus 1. And this comes from the quotient rule. Because the bases are the same, we subtract the exponents. And we'll do the same with the n terms, so it's n to the negative 2 minus 2. Whole thing still raised to the negative third power. And this is equal to 2 m squared, because it's 1 minus a minus 1, times n to the negative fourth power, whole thing to the negative third. And then by the power of a product rule, we can raise each of the factors to the negative third power. Which is equal to 1 divided by 2 to the positive third power by our negative exponent rule. And then times, we have a power of a power, so remember we multiply 2 times negative 3, which is negative 6. Same with the n term. We have a power of a power, so we multiply. So we have negative 4 times negative 3, which is positive 12. And remember, we want to write our answer using only positive exponents. So let's use that negative exponent rule again on this m term. So this is equal to, we have 1 over 2 cubed is 8, and then we have 1 divided by m to the positive sixth power, n to the 12th. And writing it as one fraction will give us our answer of n to the 12th divided by 8 times m to the 6th. And this is how we work with integer exponents. Thank you, and we'll see you next time. Let's add and subtract polynomials. For example, let's add these two polynomials together. The first thing we'll do is remove these parentheses. In other words, this is equal to 6x squared minus x minus 2, and then plus 7x squared minus 5x plus 3. And now let's focus on grouping like terms. The 6x squared and 7x squared are like terms, as well as the negative x and negative 5x, as are negative 2 and 3. So grouping these together gives us 6x squared plus 7x squared, and then plus negative x minus 5x, then plus negative 2 plus 3, which is equal to 13x squared minus 6x plus 1, which would be our answer. Now sometimes you'll see polynomials added vertically. We have this first polynomial, 6x squared minus x minus 2. And then we're adding to this the second polynomial, 7x squared minus 5x plus 3. And now the like terms are aligned vertically. So adding them will give us the same answer of 13x squared minus 6x plus 1. All right, let's look at another example. Let's subtract. Now with subtraction, we have to be very careful when we remove our parentheses and distribute this negative or negative 1 to all three of these terms in the second polynomial. That is, this is equal to negative u squared plus 5u, and then minus 3u squared minus 7u minus 6. Again, we'll group like terms. The negative u squared and negative 3u squared are like terms, as well as the 5u and negative 7u. So grouping them together gives us negative u squared minus 3u squared, and then plus 5u minus 7u, and then minus 6, which is equal to negative 4u squared minus 2u minus 6, which would be our answer. And now if we try to do this vertically, we have to be careful here because of the subtraction. In other words, we have negative u squared plus 5u, and then minus, but it's minus the entire second polynomial, this 3u squared plus 7u plus 6. So negative u squared minus 3u squared is negative 4u squared, and then 5u minus 7u is negative 2u. Now we have to be very careful with this constant term here. So let's put a plus 0 here in the first polynomial, because when we're subtracting, it's really 0 minus 6, or negative 6, which is the same answer. Now often when we subtract vertically, you'll see the following instead. We have the negative u squared plus 5u, but then subtraction means we add the opposite. So plus, and then the opposite of the second polynomial is negative 3u squared minus 7u minus 6. And so now we can add. We get negative 4u squared minus 2u minus 6, which again is the same answer. So be careful with subtraction. All right, let's look at one more example. Notice now we have three polynomials, but we are subtracting the second and adding the third. So we need to be careful when we're removing our parentheses. That is, this is equal to negative 5w squared minus 5w plus 3, and then minus a negative 4w squared, or plus 4w squared, and then minus a negative 2w, or plus 2w, and then minus a negative 2, or plus 2, and then plus 3w minus 2w squared plus 1. Again, grouping like terms, negative 5w squared, 4w squared, and negative 2w squared are like terms, as well as the negative 5w, 2w, and 3w, as are the 3, the 2, and the 1. So grouping these together gives us negative 5w squared plus 4w squared minus 2w squared, and then plus negative 5w plus 2w plus 3w, and then plus 3 plus 2 plus 1, which is equal to negative 5w squared plus 4w squared minus 2w squared is negative 3w squared. And then we have plus negative 5w plus 2w plus 3w is 0w, which we don't write. And then we have plus 3 plus 2 plus 1, which is plus 6, which would be our answer. Now, if we wanted to do this vertically, we need to be careful here for a few different reasons. So we have this first polynomial here, negative 5w squared minus 5w plus 3. But then looking back up here, we're subtracting this entire second polynomial, which is equivalent to adding its opposite. And its opposite is 4w squared plus 2w plus 2. And then we're adding this third polynomial. However, this third polynomial is not written in order. We want to put this negative 2w squared first. So we have negative 2w squared plus 3w plus 1, and then we're going to add, which gives us negative 3w squared, and then all the w terms cancel, and then we have plus 6, which is the same answer. And this is how we add and subtract polynomials. Thank you, and we'll see you next time. Let's look at multiplying binomials. For example, if we wanted to multiply 2x plus 5y and 3x minus y, we could take this entire binomial here and distribute it to each of these two terms, which would give us 2x plus 5y times 3x, and then plus 2x plus 5y times negative y. And again, we can distribute this 3x to these two terms, as well as the negative y to these two terms, which gives us 2x times 3x plus 5y times 3x plus 2x times negative y and plus 5y times negative y, which is equal to 6x squared plus 15yx minus 2xy minus 5y squared. And now 15yx and negative 2xy are like terms because yx and xy are equal by commutativity. So we can combine them, which gives us our answer of 6x squared plus 13xy minus 5y squared. Now this type of multiplication comes up often, and there is an acronym used to describe it. And the acronym is FOIL. The F in FOIL stands for first, which means we multiply the first terms in each binomial, so A times C. The O stands for outer, which means we multiply the outer terms in the two binomials, so A times D. The I stands for inner, which means we multiply the inner terms of the two binomials, so B times C. And finally, the L here stands for last, which means we multiply the last terms in the two binomials, so B times D. And the answer to this multiplication is the sum of all of these, F plus O plus I plus L. So let's apply this method here to see that we get the same answer that we just found. Okay, so we still have this product, 2x plus 5y times 3x minus y. So what is F here? This is the product of the first terms in the two binomials. So 2x times 3x, which is 6x squared. And what about O? O is the product of the outer terms in the two binomials. So 2x times negative y, which is negative 2xy. And I is the product of the inner terms in the two binomials. So 5y and 3x, which is equal to 15yx. And L is the product of the last terms in the two binomials. So 5y times negative y, which is negative 5y squared. And therefore, this product is the sum of all of these. So it's 6x squared minus 2xy plus 15yx minus 5y squared. And again, negative 2xy and 15yx are like terms, so we can combine them, which gives us the same answer of 6x squared plus 13xy minus 5y squared. So FOIL is a quick way to do distributive multiplication of two binomials. Let's see another example. Let's multiply these two binomials here. Well, we can apply the FOIL method we just saw. This is equal to the product of the first terms in the two binomials, so 2x times 2x, plus the product of the outer terms in the two binomials, so 2x times 1, and then plus the product of the inner terms in the two binomials, so negative 1 times 2x, and then plus the product of the last terms in the two binomials, so negative 1 times 1, which gives us 4x squared plus 2x minus 2x minus 1. And notice the outer and the inner terms will cancel, which leaves us with our answer of 4x squared minus 1. Now it should be pointed out that these binomials are special and that we're multiplying together the difference and sum of the same two terms. We have 2x and 2x and 1 and 1. And there's a special formula in this type of case. And the formula is that a minus b times a plus b is equal to a squared minus b squared, because the outer and inner terms will always cancel, which is what we just saw. That is, in our case, our a is 2x and our b is 1. So our answer here is a squared minus b squared, or 2x squared minus 1 squared, which is this 4x squared minus 1. Let's see another example. Now be careful here with this power of 2. We cannot apply that to each of these two terms. What this means is 3y minus 5 times 3y minus 5. So again, we can FOIL. This is equal to the product of the first terms in the two binomials, so 3y times 3y, and then plus the product of the outer terms in the two binomials, so 3y times negative 5, and then plus the product of the inner terms in the two binomials, so negative 5 times 3y, and then plus the product of the last terms in the two binomials, so negative 5 times negative 5, which is equal to 9y squared minus 15y minus 15y plus 25. And combining the outer and inner terms gives us our answer of 9y squared minus 30y plus 25. Now again, this is a common type of multiplication here, where we're multiplying a binomial by itself. And there's a special formula again in this type of case. And the formula is that a minus b quantity squared is equal to a squared minus 2ab plus b squared. That is, the outer and inner terms are the same, so there'll be two of them, which we just saw with a equal to 3y and b equal to 5. So our answer here is a squared, or 3y squared, minus 2 times a times b, and then plus b squared, or 9y squared minus 30y plus 25. And this is how we multiply two binomials. Thank you, and we'll see you next time. Let's learn how to multiply polynomials. The first thing we do when we multiply polynomials is we use the distributive property. And then we combine like terms when necessary. For example, let's multiply 2x squared and 3x squared minus x plus 4. The first thing we'll do is distribute this monomial to each of the three terms in the trinomial, which gives us 2x squared times 3x squared plus 2x squared times negative x plus 2x squared times 4, which is equal to 2 times 3 is 6, and then times x to the 4th. Because the bases are the same, we add the exponents. And then minus 2x cubed, and finally plus 8x squared. And since there's no like terms to combine, this would be our answer. All right, let's look at another example. Let's multiply this binomial and this trinomial. The first thing we'll do is distribute the entire binomial to each of these three terms in the trinomial. That is, this is equal to x squared plus 1 times 2x squared plus x squared plus 1 times negative 3x plus x squared plus 1 times 4. And now we're going to use the distributive property again and distribute this 2x squared to each of these two terms, the negative 3x to each of these two terms, as well as a 4 to each of these two terms, which gives us x squared times 2x squared plus 1 times 2x squared plus x squared times negative 3x plus 1 times negative 3x plus x squared times 4, and finally plus 1 times 4. And multiplying all these out gives us 2x to the 4th plus 2x squared minus 3x cubed minus 3x plus 4x squared plus 4. Now in this example, we do have like terms to combine, don't we? We have this 2x squared and this 4x squared, which are like terms. So we will need to combine them. So this is equal to 2x to the 4th, and then we have the minus 3x cubed term. And now combining these x squared terms, we have plus 6x squared, and then we still have the minus 3x and plus 4. So this would be our answer here. All right, and this is how we multiply polynomials. We use the distributive property as well as combining like terms when necessary. Thank you, and we'll see you next time. Let's look at multiple operations with polynomials. For example, let's perform the indicated operations and simplify. The first thing we'll do is distribute this negative, which really means negative 1, to each of these two terms here. That is, this is equal to x cubed minus 2 minus 2x cubed, and then minus 3x minus 4. And again, we'll distribute this negative, or negative 1, to each of these three terms, which gives us, we have this x cubed minus 2, and then minus 2x cubed, minus a negative 3x, which is plus 3x, and minus a negative 4 is plus 4. So now let's combine like terms. The x cubed and negative 2x cubed are like terms, as well as the negative 2 and 4. And combining these gives us our answer of negative x cubed plus 3x plus 2. Let's look at another example. Let's perform the indicated operations and simplify. Well, we can begin by foiling this product out. That is, this is equal to 3u times 3u, which is 9u squared, and then 3u times 2v, which is 6uv, and then minus 6vu minus 4v squared. And then we still have this minus 2u minus 3v quantities squared. Now what is this here? There's a common mistake that students make often that should be pointed out. They'll want to apply this power of 2 to both of these two terms. And we cannot do that. That is, this is not equal to 2u quantity squared plus negative 3v quantity squared. What it is equal to is 2u minus 3v times 2u minus 3v. So we need to FOIL again. That is, this is equal to 9u squared plus 6uv minus 6vu minus 4v squared, and then minus the whole quantity that FOILing this product out will give us, which is 4u squared minus 6uv minus 6vu plus 9v squared, which is equal to 9u squared plus 6uv minus 6vu minus 4v squared, and then distributing the negative or negative 1 through gives us minus 4u squared plus 6uv plus 6vu minus 9v squared. And now 6uv and negative 6vu will cancel. And then we can combine the rest of the like terms. 9u squared and negative 4u squared are like terms, as well as negative 4v squared and negative 9v squared, as are 6uv and 6vu. And combining these gives us our answer of 5u squared plus 12uv minus 13v squared. All right, let's look at one more example. Let's perform the indicated operations and simplify. Again, be very careful not to apply this power of 2 to both of these terms. We need to FOIL x plus h times x plus h. That is, this is equal to 3 times x squared plus 2xh plus h squared, and then minus 5 times x plus h plus 7 minus the quantity 3x squared minus 5x plus 7. And now we'll distribute the 3 to these three terms, the negative 5 to these two terms, as well as the negative or negative 1 to these three terms, which gives us 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 7 minus 3x squared, and then minus a negative 5x or plus 5x minus 7. Now 3x squared and negative 3x squared cancel, as well as negative 5x and 5x, and 7 and negative 7, which leaves us with our answer of 6xh plus 3h squared minus 5h. And this is how we perform multiple operations with polynomials. Thank you, and we'll see you next time. Let's look at rational exponents. For m and n natural numbers and b any real number, we have the following. That b to the m over n is either one of these. We can either take the nth root of b first and then raise that to the mth power, or the other way around. We can raise b to the mth power and then take the nth root of that. However, note that b cannot be negative when n is even. Otherwise, we'd be taking the even root of a negative number, and we know we cannot do that. So when are we going to use the first method, and when are we going to use the second? Let's see an example. Let's say we wanted to compute 8 to the 2/3 power. If we use the first method, this is equal to 8 to the 1/3 power, whole thing squared. And the cube root of 8 is 2, so this is 2 squared, which is equal to 4. Now if we use the second method, we would first square the 8, so this is 8 squared to the 1/3 power, which is equal to 64 to the 1/3 power, and the cube root of 64 is 4. So it doesn't matter, they're the same, right? So you can use either method. But in some cases, we'll want to use one method over the other. For example, let's say we wanted to compute 27 to the 4/3 power. We most definitely would want to do it this first way. Namely, this is equal to 27 raised to the 1/3 power, and then that whole thing raised to the 4th. And we know what the cube root of 27 is, right? That's 3. So this is 3 to the 4th power, which is equal to 81. But if we tried to use the second method, we would have to raise 27 to the 4th power and then take the cube root of that. It is much more difficult, right? Because what is this? It would be more challenging this way. So it's sort of case specific on when you'd use which method. All right, what about rational exponents that are negative? What we do is we take 1 over b to the positive m divided by n. And then we do what we did before. For example, let's say we wanted to compute 9 to the negative 3/2 power. By this is the same as 1 divided by 9 to the positive 3/2 power. Now the question is, which method would we use to compute this denominator? Would we compute 9 cubed raised to the 1/2 power, or 9 to the 1/2 whole thing cubed? This here is much more promising, isn't it? Because otherwise, we would have to compute 9 cubed. All right, so what is 9 to the 1/2 power? That is equal to 3, and 3 cubed is equal to 27. All right, so this denominator here then is 27. Therefore, our answer is 1 divided by 27. And this is how we work with rational exponents. Thank you, and we'll see you next time. Let's discuss simplified radical form. In order for an algebraic expression to be in simplified radical form, all of the following must be true. The first property that must hold is that no radicand contains a factor to a power greater than or equal to the index of the radical. For example, the cube root of y to the 5th would not be considered simplified, so this is not simplified. Because the power of the factor y, namely 5, is greater than the index of the radical, which is 3. The second property that must hold is that no power of the radicand and the index of the radical have a common factor other than 1. For example, the 9th root of x to the 12th would not be simplified. Because 9 and 12 have a common factor of 3. The third property that needs to hold is that no radical appears in the denominator. For example, 2 divided by the square root of 7 is not simplified. Because we have this square root of 7 in the denominator. And the last property that must hold is that no fraction appears within a radical. For example, the square root of 5 divided by 4 is not simplified. Because we have this 5/4 within the radical. All right, let's see an example of how we do put an algebraic expression into simplified radical form. Let's put this expression into simplified radical form, and we're assuming here that x and y represent positive real numbers. The first thing we should notice here is that the radicand contains factors raised to powers greater than the index of 4. We have the 6 as well as the 9. Since we are simplifying a fourth root, we need to focus on the perfect fourth power factors of the radicand, this 16x to the 6th y to the 9th. Now, something is a perfect fourth power factor when its exponent is a multiple of 4. So what do we have? We have the fourth root of 16x to the 6th y to the 9th is equal to the fourth root of 16, but 16 is 2 to the 4th power. And now we're going to extract the perfect fourth power factors here. So we're going to rewrite x to the 6th as x to the 4th times x squared. And we're going to rewrite y to the 9th as y to the 8th times y. And this is equal to the fourth root of 2 to the 4th, x to the 4th, x squared, and then we're going to rewrite y to the 8th as y squared to the 4th power, and then times y. Now let's group together all perfect fourth power factors, namely 2 to the 4th, x to the 4th, and y squared to the 4th. So this is equal to the fourth root of 2 to the 4th, x to the 4th, and then y squared to the 4th, and then times x squared y. And now by properties of exponents, this is equal to the fourth root of 2x y squared, all raised to the 4th power, and then times x squared y. Again, by properties of exponents, this is equal to the fourth root of 2x y squared to the 4th, and then times the fourth root of x squared y. And now this is equal to the fourth root of 2xy squared to the 4th is 2xy squared. And then we still have this fourth root of x squared times y. So the question is, are we done? And we're not, because 2 and 4 have a common factor other than 1. So let's first split this up as 2xy squared, and then the fourth root of x squared, and then the fourth root of y. Now let's convert this term here to rational exponent form. In other words, this is x to the 2/4 power, which is x to the 1/2 power, or square root of x. Therefore, this is equal to 2xy squared times the square root of x times the 4th root of y, which would be in simplified radical form. All right, and this is how we put an algebraic expression into simplified radical form. Thank you, and we'll see you next time. Let's look at square root addition and subtraction. For example, let's add these two numbers together. The first thing we'll do is we'll simplify each of the square root terms by extracting all perfect squares. In other words, this is equal to 5 times the square root of 9 times 5. 45 is equal to 9 times 5, and 9 is a perfect square. And then plus the square root of 4 times 5. 20 is equal to 4 times 5, and 4 is a perfect square. And now by properties of radicals, this is equal to 5 times the square root of 9 times the square root of 5 plus the square root of 4 times the square root of 5, which is equal to 5 times the square root of 9, which is 3, times the square root of 5, plus the square root of 4, which is 2, times the square root of 5, which is equal to 15 times the square root of 5, plus 2 times the square root of 5. And finally, we can combine these. If we have 15 square root of 5 plus 2 more, then we have 17 square root of 5, which would be our answer. All right, let's look at another example. Let's simplify this. Again, let's start off by simplifying each square root term by extracting all perfect squares. In other words, we can write 27 as 9 times 3, and 9 is a perfect square. And then we can write 75 as 25 times 3, and 25 is a perfect square. And finally, we can write 12 as 4 times 3, and 4 is a perfect square. Again, by properties of radicals, this is equal to the square root of 9 times the square root of 3, and then plus 3 times the square root of 25 times the square root of 3, minus 2 times the square root of 4 times the square root of 3, which is equal to the square root of 9 is 3, so we have 3 times the square root of 3, plus 3 times the square root of 25, which is 5, times the square root of 3, minus 2 times the square root of 4, which is 2, times the square root of 3, which is equal to 3 times the square root of 3, and then plus 15 times the square root of 3, and minus 4 times the square root of 3. Again, we can combine these. We have 3 square root of 3 plus 15 square root 3, which is 18 square root of 3, minus 4 square root 3. So we're left with 14 square root of 3, which would be our answer. All right, let's see one more. Again, we'll start by working with each square root separately and extracting the perfect squares. In other words, this is equal to 5 times the square root of 24. But 24 is 4 times 6, and 4 is a perfect square. Minus 4 times the square root of 32, but 32 is 16 times 2. and 16 is a perfect square, plus 3 times the square root of 18, and 18 is 9 times 2, and 9 is a perfect square, minus 2 times the square root of 54, and 54 is 9 times 6, and 9 is a perfect square. Again, by properties of the radical, this is equal to 5 times the square root of 4 times the square root of 6 minus 4 times the square root of 16 times the square root of 2 plus 3 times the square root of 9 times the square root of 2 minus 2 times the square root of 9 times the square root of 6, which is equal to 5 times the square root of 4, which is 2, times the square root of 6 minus 4 times the square root of 16, which is 4, times the square root of 2, plus 3 times the square root of 9, which is 3, times the square root of 2, minus 2 times the square root of 9, which is 3, times the square root of 6, which is equal to 10 square root of 6 minus 16 square root of 2 plus 9 square root of 2 minus 6 square root of 6. Now what's different here that we didn't see in the last two examples is we're left with two different types of radicals. We have the square root of 6 in two terms and the square root of 2 in the other two terms. So we'll combine terms with common radicals. That is 10 square root 6 minus 6 square root 6 would leave us with 4 square root 6. And then negative 16 square root 2 plus 9 square root 2 would be minus 7 square root of 2, which is our answer. And this is how we add and subtract with square roots. Thank you, and we'll see you next time. Let's look at multiplication involving square roots. For example, let's simplify this expression here. Let's begin by first simplifying these square roots separately. So what is the square root of 20? Well, let's extract all perfect squares here. In other words, 20 is 4 times 5. And then by properties of radicals, this is equal to the square root of 4 times the square root of 5, which is equal to 2 times the square root of 5. And what about the square root of 80? This is equal to the square root of 16 times 5, which is equal to, again, by properties of radicals, square root of 16 times square root of 5, or 4 times square root of 5. So let's put these simplifications back into here, which gives us that this is equal to 4 times 2 square root of 5, because we just found that the square root of 20 was 2 square root of 5, and then times the square root of 80. And the square root of 80 we just found to be 4 square root of 5. And now by commutativity, we can regroup this multiplication as 4 times 2 times 4, and then times the square root of 5 times the square root of 5, which is equal to 4 times 2 is 8, times 4 is 32, and then square root of 5 times square root of 5 is just 5. Because remember, we have the following property that the square root of a times the square root of b is equal to the square root of a times b for a and b non-negative. So the square root of 5 times the square root of 5 would be square root of 25, or 5. And this is equal to 32 times 5 is 160, which would be our answer. Now we could have began a bit different and just applied this property from the very beginning. In other words, this is equal to 4 times the square root of 20 times 80, which is equal to 4 times the square root of 1600. And if we simplified this, we'd get to the same answer. But 1600 is a pretty big number, so we decided to simplify the smaller radicals first. All right, let's look at another example. Let's simplify this. What we'll do is we'll begin by foiling. That is, this is equal to 5 square root of 3 times 3 square root of 3 plus 5 square root of 3 times negative 2 square root of 2 plus 4 square root of 2 times 3 square root of 3, and finally plus 4 square root of 2 times negative 2 square root of 2, which is equal to 5 times 3 is 15, and then times the square root of 3 times 3 are 9, minus 10 times the square root of 6 plus 12 times the square root of 6, and minus 8 times the square root of 4, which is equal to 15 times 3, the square root of 9 is 3, and then minus 10 square root 6, plus 12 square root 6, minus 8 times the square root of 4, which is 2, which gives us 45 minus 10 square root of 6 plus 12 square root 6 minus 16. And now we'll combine these numbers here, as well as the terms with the square root of 6 in them, which gives us 45 minus 16 is 29, and then minus 10 square root 6 plus 12 square root 6 is positive 2 square root 6, which would be our answer. And this is how we work with multiplication involving square roots. Thank you, and we'll see you next time. Let's learn how to rationalize a denominator. For example, let's rationalize the denominator of this expression and write our answer in simplified form. Looking at this denominator here, we have an irrational number here and an irrational number here. Remember, to rationalize the denominator means to make the denominator a rational number. And we can do that by multiplying both the numerator and denominator by the conjugate of the denominator. And remember, the conjugate is the same expression, but we just change the minus to a plus. And if we multiplied our denominator by this, we need to multiply our numerator by this as well. Let's put parentheses here so we know that we're going to FOIL both the numerator and denominator. So what do we get? Looking at the numerator here, we have 3 square root of 2 times 3 square root of 5, and the square root of 2 times square root of 5 is square root of 10, and 3 times 3 is 9. So this is equal to 9 square root of 10. The outer term is 12 square root of 4. The inner term is negative 6 square root 25. And the last term is negative 8 square root of 10. What about the denominator? When we FOIL this out, we have 9 square root of 25. The outer term is plus 12 square root of 10. And the inner term is minus 12 square root of 10. And the last term is minus 16 square root of 4. Now, by multiplying by the conjugate, these outer and inner terms in the denominator will cancel. And what are we left with? We have 9 square root of 10, and then plus 12 square root of 4. But the square root of 4 is 2, so we have plus 24. And then minus 6 square root of 25, and square root of 25 is 5. So this is minus 30. And then minus 8 square root of 10. Divided by, we have 9 times the square root of 25, or 9 times 5, which is 45. And then minus 16 times square root of 4, but square root of 4 is 2, so it's minus 32. Now let's combine like terms. This 9 square root of 10 minus 8 square root of 10 gives us positive 1 square root 10. So this is equal to square root of 10. And then 24 minus 30 is negative 6, and the denominator is 13. And we have rationalized our denominator and written our answer in simplified form. So this would be our answer. And this is how we rationalize a denominator. We multiply both the numerator and denominator by the conjugate of the denominator. Thank you, and we'll see you next time.
Hey Coursera Precalculus students. My name is Dr. Sarah Eichhorn, and I'll be one of your instructors for this course. The other instructor is Dr. Rachel Lehman. We're both mathematics faculty members at the University of California, Irvine, and we're really looking forward to working with you in this course. To begin with, I'd like to give you a little bit of an overview of what to expect. Each week, there'll be a set of lecture videos. Each video will be 3 to 10 minutes in length, and then there'll be a quiz following every 3 to 5 videos. These quizzes are designed to test exactly what you saw presented in the lecture video. The lecture video and the quizzes will not give you a full, complete view of precalculus. To do that, you'll also want to check out the readings and the additional homework assignments. These are designed to give you a little further practice with the material and kind of see some topics that aren't covered in the lecture videos. Just to be clear, the readings will sometimes overlap with the lectures a little bit, and sometimes will have some complementary additional information. Each week, we anticipate that you'll have to spend about 8 to 10 hours working with the material, a little bit more if you're a little rustier and haven't seen math in a while. We hope by the end of this 10-week course, you'll be prepared to enter a calculus course, or you'll have the mathematics skills sufficient for whatever your learning goal is. At the end of the course, there'll be a 10th week, and in that week, we'll have a review and a final exam. The final exam will be structured just like the quizzes and designed to cover all the material from the course. We hope you'll take a look at the course homepage and look at that syllabus for more information about the class. In addition to those quizzes, lecture videos, and readings, there's also the discussion forums. The discussion forums are the real power behind a Coursera class. There's approximately 20,000 students enrolled in this class, and Dr. Lehman and myself can't respond to that many emails, so we hope you'll use the discussion forums to talk to each other. We'll be monitoring the forums and pitching in and throwing out ideas and answers whenever is needed, but your Coursera learning community is very bright, and hopefully your other students can help you as well. In addition to Dr. Lehman and myself, there will be 2 TAs for the class. These teaching assistants will be there to help you learn and process the material, answer questions in the forums. They are Minyang Zhao and Alexander Block, and the 2 of them are both mathematics majors at the University of California, Irvine, so hopefully they'll be pitching in the discussion forums to help you out a bit. As you may have seen, we opened up the course a week early with a week 0. This was designed to give you some brush up on the prerequisite materials, but also to help you become familiar with the quiz tool. I've already seen in the discussion forums that some of you are having a little trouble getting the quiz notation down and find the instructions a little tricky. I will tell you, it gets easier once you get used to how we ask you to enter things. Hopefully by the middle of the course, you'll be very comfortable with it and it won't seem difficult at all. Anytime you're having trouble, feel free to use the forums for some help, and don't forget to reread those instructions. I will tell you the reason we do the quiz notation the way we do
is that the Coursera quiz tool is actually pretty smart, and we have to be a little bit clever so that it will realize that some mathematical answers are different from others. For example, the Coursera quiz tool knows that 1/2 is the same as 0.5 is the same as 5 times 10 to the negative 1. So if we want a particular one of those notations, you will see us ask for your answer in a particular format. The reason we don't just do multiple choice is we want you to have a rich learning experience as close as possible to an on-ground version of the class. In mathematics, multiple choice can be very difficult because often you can just plug in the answers and see which one works. And we won't actually be testing the do you know how to do the method. As you work through the course, we hope you'll have a really good time talking in those discussion forums with your classmates and community and asking any questions that we can help with. We will be checking in with you every week. In the videos, you'll see me occasionally, but a majority of the videos are done by Dr. Rachel Lehman. You just don't see her. She'll be the disembodied voice in the great math handwriting, explaining carefully for you how to do things. We'll check in with you each week to make sure things are going well. First off, to start off, I wanted to give some shout outs to some people during week 0 who had some fantastic discussion forum contributions. Super thanks to Ron Brannon. He had some awesome feedback on a typesetting tool called LaTeX, and also some very elegant math results that he was sharing with the community. Another shout out goes to Doug Parker. He had some great comments and feedback to his fellow classmates on the properties of integer exponents quiz. And then finally, I'd like to thank Dylan Smith. One of the things we recommended on the course syllabus was this tool called Alex. If you have a little extra money to spend on the class and want a deeper, richer learning experience, Alex software has been shown to be pretty good with our UC Irvine students, and we would highly recommend it to you. And Doug Smith said he used it in our algebra course and was a big fan. So I'd encourage you to check out his comment if you're thinking about you might be interested in purchasing Alex. Anyways, good luck with the first week and have fun learning. Bye.
Let's look at solving linear equations. For example, let's solve the following equation for y. The first thing we'll do is we'll distribute the 3 to both of these two terms, as well as the 5 to these two terms, which gives us 3 times y plus 6 is equal to 5 times y minus 30. Now, when solving linear equations, what we want to do now is bring all the variables to one side and all the numbers to the other, which would give us 3y minus 5y is equal to negative 30 minus 6, or negative 2y is equal to negative 36. And now dividing both sides by negative 2 gives us our answer of y is equal to 18. Now, if we didn't want to work with all of these negatives, we could have started in the same way by distributing the 3 and the 5 through, giving us this 3y plus 6 is equal to 5y minus 30. But now if we bring the 3y to the right and the negative 30 to the left, we get 6 plus 30 is equal to 5y minus 3y, or 36 is equal to 2y. And now dividing by 2 gives us the same answer of y is equal to 18. But we didn't have to work with all those negatives. All right, let's look at another example. Let's solve this equation for t. Again, we'll start in a similar way and distribute this negative 3 to both of these two terms, as well as the 5 to both of these two terms, which gives us 4 minus 3t minus 6 plus t is equal to 5t minus 5 minus 7t. Now let's combine like terms on both sides of the equation. The 4 and the negative 6 are like terms, as well as the negative 3t and t, and so are 5t and negative 7t. Combining these gives us that 4 minus 6 is negative 2, and then negative 3t plus t is negative 2t, is equal to 5t minus 7t is negative 2t, and then minus 5. Again, let's bring all the variables to one side and the numbers to the other. And what does that give us? We have negative 2t plus 2t is equal to negative 5 plus 2. But isn't the left-hand side here just 0? So 0 is equal to negative 5 plus 2 or negative 3? No. So what does that mean? That means that no value of t will work. No matter what value of t we try to plug into this equation, we will never get a true statement. And what would our answer be in such a situation? Our answer would be no solution. Because there's no value of t that will satisfy this equation. Now, what if this value over here, negative 3, actually had turned out to be 0? Then what would our answer be in that situation? We'd have 0 is equal to 0, which is always true. So no matter what value of t you'd plug in, we'd always arrive at a true statement. Our answer in such a situation would be all real numbers. All right, let's see another example. Now this example is different in that we have these fractions here. Now there's different approaches to solving such an equation. But the approach that students seem to like best is to find the least common multiple of these denominators here so we can multiply both sides of the equation by that least common multiple to eliminate the fractions. So let's do that. What is the least common multiple of these denominators here? Isn't that 30? So let's multiply both sides of this equation by 30. So we have 30 times the entire left side is equal to 30 times the entire right side. And now let's distribute the 30 to these two terms, as well as these two terms, which gives us 30 times v plus 10 divided by 15 plus 30 times negative 1/5 is equal to 30 times v plus 1 divided by 6 plus 30 times negative 1/10. Now 15 goes into 30 2 times, so we'll have a 2 left here. 5 goes into 30 6 times, so we'll have a 6 left here. 6 goes into 30 5 times, we'll have a 5 left here. And 10 goes into 30 3 times, we'll have a 3 left here. And now our equation has simplified as follows. 2 times v plus 10 plus 6 times negative 1 is equal to 5 times v plus 1 plus 3 times negative 1, and we've eliminated the fractions. And now let's distribute the 2 and the 5 through, which gives us 2 times v plus 20, and then we have minus 6 is equal to 5 times v plus 5, and then minus 3. And now combining like terms, we have 2v, and then 20 minus 6 is 14, is equal to 5v, and 5 minus 3 is 2. And now we'll bring all the variables to one side and the numbers to the other. If we bring the 2v to the right and the 2 to the left, if you remember from the first example, then we can eliminate working with the negative coefficient of v. That is, we have the following. 14 minus 2 is equal to 5v minus 2v, or 12 is equal to 3v, and dividing both sides by 3 gives us our answer of v is equal to 4. And this is how we solve different types of linear equations. Thank you, and we'll see you next time. Let's work with algebraic symbol manipulation. For example, let's solve the following equation for f. Right now we have c is equal to something, and we want to manipulate this equation to get f is equal to something instead. And we'll begin by multiplying both sides of the equation by 9/5 in order to get rid of this fraction here. That is, we have 9/5 times c is equal to 9/5 times 5/9 times f minus 32. And 9/5 times 5/9 is 1, so these fractions will cancel, which leaves us with 9/5 times c is equal to f minus 32. And now we'll add 32 to both sides of the equation, which gives us 9/5 times c plus 32 is equal to f minus 32 plus 32. And negative 32 plus 32 will cancel. They add together to give us 0, which leaves us with f is equal to 9/5 times c plus 32, which would be our answer. By the way, these are the equations that we use to convert between Fahrenheit and Celsius temperatures. All right, let's see another example. Let's solve the following equation for y. What we can do is we can start by multiplying both sides of the equation by this denominator here, y minus 3, which gives us x times y minus 3 is equal to 3y plus 2 divided by y minus 3 times y minus 3. And now the y minus 3's on the right will cancel, and we are assuming here, of course, that y does not equal 3, which leaves us with x times y minus 3 is equal to 3y plus 2. And now let's distribute this x to both of these two terms, which gives us x times y minus 3x is equal to 3y plus 2. Now remember that we want to solve this equation for y. So let's bring all the y's to one side and everything else to the other, which gives us x times y minus 3y is equal to 2 plus 3x. And now we'll factor y out of both terms on the left, which gives us y times x minus 3 is equal to 2 plus 3x. And now let's divide both sides of the equation by x minus 3. And the x minus 3's on the left will cancel, and we're assuming here, of course, that x does not equal 3, which leaves us with our answer of y is equal to 2 plus 3x divided by x minus 3. And this is how we algebraically manipulate an equation to solve for a variable. Thank you, and we'll see you next time. Let's look at solving linear word problems. A total of 703 tickets were sold for the school play. They were either adult or student tickets. There were 53 more student tickets sold than adult tickets. How many adult tickets were sold? Let's start by introducing some notation here. Let's let S be equal to the number of student tickets sold. And A be equal to the number of adult tickets sold. Now we're told that there were 53 more student tickets sold than adult tickets. That is, S, which is the number of student tickets sold, is equal to A, which is the number of adult tickets sold, plus 53. There's 53 more student tickets sold. Moreover, the total number of tickets sold was 703. And since they're either adult tickets or student tickets, that means that S plus A has to equal 703. Now we're asked to find out how many adult tickets were sold, which means we want to solve for A. Therefore, if we replace in this equation S with A plus 53, then we'll have an equation that just involves A, and we'll be able to solve for it. So let's do that. That is, we have A plus 53 plus A is equal to 703. And then combining like terms on the left gives us 2A plus 53 is equal to 703. And now we can subtract 53 from both sides, which gives us 2A is equal to 703 minus 53, or 2A is equal to 650. And then dividing both sides by 2 gives us A is equal to 325. So there were 325 adult tickets sold to this play. All right, let's look at another example. James will rent a car for the weekend. He can choose one of two plans. The first plan has an initial fee of $69 and costs an additional 60 cents for every mile driven, whereas the second plan has no initial fee but costs 90 cents for every mile driven. How many miles would James need to drive for the two plans to cost the same? Well, let's let X equal the number of miles that James drives. What then would be the cost of the first plan? Well, he has to pay an initial fee of $69 and then an additional 60 cents for every mile driven. That is, this is equal to 69 plus 0.60 times X, because X is the number of miles that he's going to drive, and for every one of those miles, they're going to charge him another 60 cents. Now, what about the cost of the second plan? Now, there's no initial fee, but it's going to cost him 90 cents for every mile driven. That is, this is equal to 0.90 times X. Now we want to know how many miles he would need to drive for the two plans to cost the same. So we want to find the value of X that will make these equal. That is, we'll solve the following equation for X. 69 plus 0.60X is equal to 0.90X. Or 69 is equal to 0.90X minus 0.60X. Or 69 is equal to 0.30 times X. And now we can divide both sides by 0.30. Which gives us x is equal to 69 divided by 0.30. But 0.30 is 3 divided by 10. So this is equal to 69 times 10 divided by 3. And 3 goes into 69 23 times. Therefore, this is equal to 23 times 10, or 230. Therefore, the answer to our question here is 230 miles. And this is how we solve these types of linear word problems. Thank you, and we'll see you next time. Let's work with percentage word problems. Starting today, a table is being sold at Jaime's furniture store for $345. This is 69% of its regular price. What was the price yesterday? So this price here, $345, is 69% of its regular price. And we want to know what the price was yesterday. Well, if today is the first day that this table is being sold at this discounted price, then the price yesterday was the regular price. So let's let x equal the price yesterday, or the regular price. Therefore, $345 is 69% of x, because the sale price is 69% of the regular price. And translating this into an equation gives us 345 is equal to 0.69 times x. Is means equals, percent means divide by 100, and of means times. Therefore, we can divide both sides now by 0.69, which gives us x is equal to 345 divided by 0.69, which is equal to 345 divided by 0.69 is 69 divided by 100, which is equal to 345 times, and now we flip this fraction here. And 69 goes into 345 5 times. So this is equal to 5 times 100, or 500. Therefore, the price yesterday was $500. Now, rather than doing this out the long way here, we could have at this point used a calculator and we would have gotten to the same answer. All right, let's see another example. At a sale this week, a desk is being sold for $603. This is a 33% discount from its original price. What is its original price? Well, what does this mean, a 33% discount? A 33% discount means that the desk is being sold for 100% minus 33%, or 67% of its original price. $33% isn't the amount the desk is being sold for, it's the amount the desk is being discounted at. So let's let X equal its original price. Now this desk is being sold for $603, which means $603 is 67% of its original price, or X. Again, let's translate this into an equation. We have 603 means equals 67% means 0.67, or 67 divided by 100, and of means times. And now we'll divide by 0.67, which gives us that X is equal to 603 divided by 0.67, which is equal to 603 divided by 0.67 is 67 divided by 100, which is equal to 603 times 100 divided by 67. And 67 goes into 603 9 times. Therefore, this is equal to 900, which is our answer. Therefore, the original price then of the desk was $900. And this is how we solve percentage word problems. Thank you, and we'll see you next time. Let's look at word problems that involve area and perimeter. For example, the length of a rectangle is 5 times its width. If the area of the rectangle is 405 square feet, find its perimeter. Okay, so let's let L equal the length of the rectangle. And W be equal to the width. That is, this is L and this is W. Now we're told that the length is 5 times its width, which means then that L, the length, is equal to 5 times the width, or 5W. But we're also told that the area of the rectangle is 405 square feet. And remember that the area of a rectangle is the length times the width, which means that the length times the width is equal to this 405 square feet. Now we know that L is equal to 5W, so let's replace L here with 5 times W, which gives us 5 times W is equal to 405, or 5W squared is equal to 405, and then dividing both sides by 5 gives us that W squared is equal to 81, which means W is equal to plus or minus the square root of 81. But since W is the width of this rectangle here, we're going to choose the positive. So W is positive square root 81, or positive 9. And then we can plug this back in here to give us what L is equal to. That is, L is equal to 5 times 9, or 45. So let's write that up here. L, the length of the rectangle, is 45 feet. And W, the width, is 9 feet. However, this isn't what we're asked to find, is it? We're asked to find its perimeter. Remember, the perimeter of a rectangle is 2 times the length plus 2 times the width. So plugging in the values we just found for L and W, we'll be able to find this perimeter. Namely, P is equal to 2 times 45 plus 2 times 9. Or P is equal to 90 plus 18, which is equal to 108. So therefore, our answer is 108 feet. All right, let's look at one more. The length of a rectangle is 4 centimeters longer than its width. If the perimeter of the rectangle is 48 centimeters, find its area. Again, let's let L equal the length of the rectangle. And W be equal to its width. Now we're told that the length is 4 centimeters longer than its width. Therefore, L is equal to W plus 4. But now in this example, we're given what the perimeter is equal to. It's 48 centimeters, and we want to find the area. Again, we're going to use the formula that the perimeter of a rectangle is 2 times its length plus 2 times its width, which we are given is equal to 48, which means 2 times L plus 2 times W has to be equal to 48. And now we can replace L here with W plus 4, which gives us 2 times, be careful, it's the whole quantity W plus 4. Then plus 2W is equal to 48. Or 2W plus 8 plus 2W is equal to 48. Or 4W plus 8 is equal to 48. And then subtracting 8 from both sides gives us 4W is equal to 48 minus 8, or 4W is equal to 40. And then dividing both sides by 4 gives us that W is equal to 10. And then we can plug this value back into this equation to find L. Namely, L is equal to 10 plus 4, or 14. So let's write that up here. L is equal to 14 centimeters, and W is equal to 10 centimeters. Remember, we're looking for the area of the rectangle. Again, we'll use the formula that area is equal to length times width, where area is equal to 14 times 10, or area is equal to 140 square centimeters. All right, and this is how we work with area and perimeter word problems. Thank you, and we'll see you next time. Let's look at distance, rate, and time. For example, 2 trains leave the station at the same time. One is heading west and the other east. The westbound train travels 12 miles per hour faster than the eastbound train. If the 2 trains are 400 miles apart after 2 hours, what is the rate of the westbound train? So let's let x equal the rate in miles per hour of the westbound train. Now we're told that the westbound train travels 12 miles per hour faster than the eastbound train, which means the eastbound train travels 12 miles per hour slower than the westbound train. Therefore, if x is equal to the rate of the westbound train, then x minus 12 is equal to the rate in miles per hour of the eastbound train. Now we're going to use the famous formula that distance is equal to rate times time to help us solve this problem. Or in symbols, d is equal to r times t. Now let's keep track of things in a table here. So here's r for rate, here's t for time, and here's d for distance. And here is the westbound train, and here's the eastbound train. So x is the rate of the westbound train. X minus 12 is the rate of the eastbound train. And we know something about how far apart the trains are after 2 hours. So we're going to let t equal 2 here, which means after 2 hours, the distance that the westbound train has traveled is r times t, or 2x. And the distance after 2 hours that the eastbound train has traveled is 2 times x minus 12. So if here's the station, and after 2 hours, the distance that the eastbound train has traveled is 2 times x minus 12. And the distance that the westbound train has traveled after 2 hours is 2 times x. But we're told that after those 2 hours, these 2 trains are 400 miles apart, which means that this total distance is 400. That is, the sum of those 2 distances has to be 400. Namely, 2x plus 2 times x minus 12 is equal to 400. Or 2x plus 2x minus 24 is equal to 400. Or 4x minus 24 is equal to 400. And then adding 24 to both sides, we get 4x is equal to 424. And then dividing both sides by 4 gives us that x, which is the rate we're looking for of the westbound train, is 106 miles per hour. And this is an example of how we use this very important formula here. Distance is equal to rate times time. Thank you, and we'll see you next time. Let's look at how we can use linear equations to help us solve mixture problems. For example, a student is mixing two solutions that contain hydrogen chloride. The first solution is 15% hydrogen chloride, and the second is 5% hydrogen chloride. How many milliliters of each solution should the student mix in order to obtain 100 milliliters of an 8% hydrogen chloride solution? All right, so the student has a solution that is 15% hydrogen chloride, which is being mixed with a solution that is 5% hydrogen chloride to produce a solution that is 8% hydrogen chloride. All right, so let's let X equal the number of milliliters of the 15% solution that the student will mix, and Y equal the number of milliliters of the 5% solution. And therefore, X plus Y will equal the number of milliliters of the 8% solution. However, looking back up here in our problem, we know how many milliliters that has to be. It has to be 100, which means that X plus Y is equal to 100, or Y is equal to 100 minus X. So let's write that up here. We're mixing X milliliters of the 15% solution with Y, or 100 minus X milliliters of the 5% solution to obtain 100 milliliters of an 8% hydrogen chloride solution. Now, what's important to realize here is that the amount of hydrogen chloride before mixing is equal to the amount of hydrogen chloride after mixing. We do not create more hydrogen chloride by mixing. Now, what is the amount of hydrogen chloride before mixing? Well, what is the amount of hydrogen chloride in the first solution here? Well, if there's X milliliters of this solution, 15% of which is hydrogen chloride, then the amount of hydrogen chloride in this first solution is 0.15 times X. And then plus the amount of hydrogen chloride in the second solution, which is 0.05 times 100 minus X. And this has to be equal to the amount of hydrogen chloride after mixing, or 0.08 times 100. So now let's solve this linear equation for X. We have 0.15 times X plus, and distributing the 0.05 to both of these two terms, gives us 0.05 times 100, which is 5, and then minus 0.05 times X is equal to 0.08 times 100, which is 8. And combining the X terms on the left-hand side and bringing the 5 to the right-hand side gives us 0.10 times X is equal to 3. And now dividing both sides by 0.10 gives us that X is equal to 30. And if X is equal to 30, we can plug that in over here which gives us y is equal to 100 minus 30, or 70. And therefore, writing our answer up here, the student would need to mix x, or 30 milliliters of the 15% solution with y, or 70 milliliters of the 5% solution in order to obtain 100 milliliters of the 8% hydrogen chloride solution. So this would be our answer here. And this is how we can use linear equations to help us solve mixture problems. Thank you, and we'll see you next time. Let's learn how to solve a linear inequality. For example, let's solve the following inequality for v and write our answer in interval notation. Now, for the most part, when we solve linear inequalities, we proceed in the same way as we do when we solve linear equalities. However, there is one difference which we'll see. Let's begin by getting the negative 7 to the right-hand side, or we'll add 7 to each side. In other words, we have minus 7 plus 4v is greater than or equal to negative 15 plus 7. And negative 7 plus 7 is 0. They'll cancel. And we're left with 4v greater than or equal to negative 8. Now let's divide both sides by 4, which is exactly the point we need to be careful. This is where the difference between inequalities and equalities comes up. If this number 4 would have been a negative number, we would have had to flip or reverse the direction of that inequality. In other words, in general, we have the following: that when we multiply or divide both sides of an inequality by a positive number, the inequality stays the same, like in this case. However, when we multiply or divide by a negative number, we flip the inequality sign. Okay, so we don't have to flip our inequality here, so we have v greater than or equal to negative 2. Let's look at this on a number line. Here's negative 2. V can equal negative 2 and anything to the right. Now we are asked to put our answer in interval notation. Doing this, we have close bracket, negative 2, because we want to include negative 2, up to positive infinity, which would be our answer. All right, let's see another example. Let's solve the following inequality for x and write our answer in interval notation. Again, we'll begin by getting this number negative 15 to the right, or adding 15 to both sides. So we have minus 3x minus 15 plus 15 is greater than 3 plus 15. And negative 15 plus 15 is 0. They'll cancel. And we're left with negative 3x is greater than 18. And now let's divide both sides by negative 3. However, remember that when we divide both sides of an inequality by a negative number, we have to flip this inequality sign. That is, we need to flip the greater than and make it a less than. So we get x is less than negative 6. Okay, let's look at this again on the number line. It's negative 6. We do not want x to equal negative 6, so we put an open circle and then less than, everything to the left of negative 6. And again, we're asked to put our answer in interval notation. Therefore, our answer is negative infinity up to negative 6, open parenthesis because we do not want x to equal negative 6. Now, if we didn't want to worry about dividing by this negative, we could have started just a bit different here. We still have the same inequality, minus 3x minus 15, greater than 3. But then if we bring the minus 3x to the right, or add 3x to both sides, and bring the 3 to the left, or subtract 3 from both sides, what do we get? We have minus 15 minus 3 is greater than positive 3x, or negative 18 is greater than positive 3x. And now when we divide, this number's positive, so we don't have to worry about the inequality flipping. So we get x less than negative 6, which we can write in the other direction, x less than negative 6, which is our same answer. All right, this is how we solve linear inequalities. Just remember to be careful when you multiply or divide by a negative number. Thank you, and we'll see you next time. Let's learn about compound inequalities. A compound inequality is two inequalities joined by either the word and or the word or. For example, this would be considered a compound inequality. And the way we solve compound inequalities is we work with each side separately. So let's start with this first inequality here. We can begin by subtracting 2 from each side. Which gives us 3x is less than or equal to negative 6, because 2 minus 2 is 0. Now dividing both sides by 3, and 3 is a positive number, so this inequality will not flip. It gives us x is less than or equal to negative 2. All right, what about this second inequality here? Again, we can begin by subtracting 4 from both sides. Which gives us 4x is greater than 20. Again, dividing gives us x is greater than 5. Now, because our inequalities are joined by the word or, our solution here will be all x values that make at least one of these inequalities true. So let's graph this. So here's 0. Let's say this is negative 2, and this is 5. All right, x less than or equal to negative 2. We put a closed circle at negative 2, and less than, we go to the left. X greater than 5. X cannot equal 5, so we put an open circle, and then greater than, we go to the right. Which would be our answer. All right, let's see another example. Now, although we don't see the word and or the word or here, this is still a compound inequality. In fact, it's a short way of writing the following. 15 is less than or equal to 3 minus 2x, and 3 minus 2x is less than 33. Again, we can solve each inequality separately. So let's begin by subtracting 3 from both sides, which gives us 15 minus 3 less than or equal to 3 minus 3 and then minus 2x. And 15 minus 3 is 12. So we have 12 less than or equal to negative 2x, because the 3's will cancel. So now let's divide both sides by negative 2. But we have to be careful here because we're dividing by a negative, which means this inequality will flip, which gives us negative 6 is greater than or equal to x. Or we can write it the other way, x less than or equal to negative 6. All right, what about this other inequality here? Again, we can subtract 3 from both sides, which gives us 3 minus 3 minus 2x less than 33 minus 3, or negative 2x less than 30. Again, divide both sides here by negative 2. And this inequality will flip, which gives us x is greater than negative 15. Now let's graph this. Here is negative 15, and here is negative 6. So less than or equal to negative 6, x can equal negative 6, and then we go to the left. Greater than negative 15, so we put an open circle here. We go to the right. Now, because these inequalities are joined by the word and here, our solution is all x values that make both of them true, which would be this intersection here. In other words, our answer would be the following. So here's negative 15, here's negative 6, closed at negative 6, open at 15, and everything in between. Now, when working with this type of compound inequality, we didn't necessarily need to split. We could have started with this original chain of inequalities. So 15 less than or equal to 3 minus 2x is less than 33, and worked with all the parts at the same time. In other words, we can subtract 3 everywhere, which would give us 15 minus 3 is less than or equal to negative 2x, because the 3's would cancel in the middle. It's less than 33 minus 3. Or 12 is less than or equal to negative 2x, which is less than 30. And now we'll divide everything by negative 2. But remember, these have to flip. And this gives us negative 6 greater than or equal to x greater than negative 15, which we normally write in the other way, negative 15 less than x less than or equal to negative 6, which is our answer. All right, this is how we work with compound inequalities. Thank you, and we'll see you next time. Let's work with linear inequality word problems. Rachel is a saleswoman. She receives a salary of $45,000 per year. In addition, she receives 7% of her sales amount for the year. What are the sales amounts that will allow her to earn more than $56,900 per year? So we want Rachel's earnings to be more than, just greater than, $56,900. Well, what are these earnings? We're told that she receives a base salary of $45,000, but then also 7% of her sales amount for the year. That is, her earnings are the base salary plus 7% or 0.07 of means times her sales amount. So let's let X equal Rachel's annual sales amount. Therefore, her earnings here would be the base salary, $45,000, plus 7% of X. And putting that in here gives us the following inequality. 45,000 plus 0.07 times X needs to be greater than 56,900. And now we can subtract 45,000 from each side, which gives us 0.07 times X is greater than 56,900 minus 45,000. Or 0.07x is greater than 11,900. And now we can divide both sides by 0.07, which gives us x is greater than 11,900 divided by 0.07. Now what is this number here? Let's compute that. So it's 11,900 divided by 0.07 is equal to 11,900 divided by 7 divided by 100, which is equal to 11,900 times 100 divided by 7. And then 7 goes into 11,900, 1,700 times. Therefore, this is equal to 170,000. And putting that back in here, that means that as long as X, which is Rachel's annual sales amount, is larger than $170,000, indeed, she'll be earning more than $56,900 per year. And this is how we work with linear inequality word problems. Thank you, and we'll see you next time. Let's look at solving absolute value equations. For example, let's solve this equation for W. Now, if the absolute value of 2W plus 5 is equal to 7, then either 2W plus 5 is equal to 7, or 2W plus 5 is equal to negative 7. In other words, if the absolute value of A is equal to B, then either A is equal to B, or A is equal to negative B, which is what we're using here. And let's work with each equation separately. We'll begin with this first one here. We'll start by subtracting 5 from both sides, which gives us 2W is equal to 7 minus 5, or 2W is 2. And now dividing both sides by 2 gives us that W is equal to 1. And what about this second equation? Again, we can subtract 5 from both sides, which gives us 2W is equal to negative 7 minus 5, or 2W is equal to negative 12. Again, dividing both sides by 2 gives us that W is equal to negative 6. Now let's check these answers by plugging them into the original equation. So let's check. We'll start with w equal to 1. And when w is equal to 1, the question is 2 times 1 plus 5 in absolute value equal to 7? Or is absolute value of 7 equal to 7? And yes, it is. And what about w equal to negative 6? The question is the absolute value of 2 times negative 6 plus 5 equal to 7? Or is the absolute value of negative 12 plus 5, which is negative 7, equal to 7? And it is. So our answer then is w is equal to 1 or negative 6. Now, in solving these types of absolute value equations, and the right-hand side is a positive number like this, and we apply this fact, then we don't really need to check our answers, but it never hurts. However, with something like this, where the right-hand side is not a positive number, we must check our answers. We're still going to use the fact that if the absolute value of a is equal to b, then either a is equal to b or a is equal to negative b, but we're just going to have to check our answers at the end. Okay, so applying this, we have that x plus 4 then is either equal to 3x plus 8 or x plus 4 is equal to negative 3x plus 8. But be careful to use parentheses here. Again, we'll solve each equation separately. Let's begin with the first equation. We'll bring the 3x to the left and the 4 to the right, which gives us x minus 3x is equal to 8 minus 4, or negative 2x is equal to 4. And then dividing both sides by negative 2 gives us that x is equal to negative 2. And now let's solve the second equation. We'll begin by distributing the negative to both of these two terms. That is, we have x plus 4 is equal to negative 3x minus 8. And now we'll bring the negative 3x to the left and the 4 to the right, which gives us x plus 3x is equal to negative 8 minus 4, or 4x is equal to negative 12, and then dividing both sides by 4, we get x is equal to negative 3. Now remember, we must check these answers by plugging each of them into the original equation wherever we see an x. So let's start with x equal to negative 2. The question is the absolute value of negative 2 plus 4 equal to 3 times negative 2 plus 8? Or is the absolute value of 2 equal to negative 6 plus 8, which is 2? And yes, it is. So negative 2 works. What about negative 3? The question is the absolute value of negative 3 plus 4 equal to 3 times negative 3 plus 8? Or is the absolute value of negative 3 plus 4, which is 1, equal to negative 9 plus 8, which is negative 1? And no, this is not true, because the absolute value of 1 is equal to 1, not negative 1, which means we need to cross off negative 3 here. Therefore, our only answer is x is equal to negative 2. So let's write that here then. Our answer is x equal to negative 2. And this is how we solve absolute value equations. Just be very careful to check your answers when that right-hand side is not a positive number. Thank you, and we'll see you next time. Let's learn how to solve absolute value inequalities. Let's solve the following inequality for x and put our answer in interval notation. If the absolute value is less than or equal to 9, that means what's inside the absolute value is between -9 and 9. In other words, we're going to use the following fact to help us. That the absolute value of y less than or equal to a means that -a is less than or equal to y is less than or equal to a. Let's apply that here. Namely, -9 is less than or equal to 5 minus 2x is less than or equal to 9. Now remember, when solving this type of compound inequality, we can work with all the parts at the same time. So let's start by subtracting 5 everywhere, which gives us -9 minus 5 is less than or equal to 5 minus 5 minus 2x, which is less than or equal to 9 minus 5. Or -14 is less than or equal to -2x is less than or equal to 4. And now let's divide everything by -2. However, remember, when we divide by a negative, we better flip or reverse the direction of both of these inequalities. Which gives us 7 is greater than or equal to x is greater than or equal to -2. Which we usually write in the other direction. -2 is less than or equal to x is less than or equal to 7. Let's look at this on the number line. Let's say this is -2 and this is 7. X is greater than or equal to -2. So x can equal -2. And then we go to the right. However, x has to be less than or equal to 7, so we stop here. And we're asked to put our answer in interval notation. Therefore, our answer would be close bracket, because we want to include -2, up to 7. Again, close bracket, because we want to include 7. All right, let's look at another example. Let's solve this inequality and again put our answer in interval notation. Now the difference here is that we have greater than rather than less than, like the last example. Now if the absolute value is greater than 1, then what's inside the absolute value is either larger than 1 or smaller than -1. In other words, we're going to use the following fact to help us solve this problem. That the absolute value of y greater than a means that y is greater than a or y is smaller than -a. And this is what we're going to apply here. And this gives us that 3 plus 2x is either greater than 1 or 3 plus 2x is smaller than -1. And now when solving this type of compound inequality, we work with each side separately. So let's start with this first inequality here. We'll bring the 3 to the right, or subtract 3 on both sides, which gives us 2x is greater than 1 minus 3, or 2x is greater than -2. And now dividing both sides by 2, we get x is greater than -1. And what about the second inequality? Again, we'll bring the 3 to the right-hand side, which means 2x is less than -1 minus 3, or 2x is less than -4. Again, dividing by 2 gives us x is less than -2. And since these inequalities are joined by the word or, then the solution is all x values that make at least one of these true. Let's look at this on the number line. Let's say that this is -2 and this is -1. Greater than -1, we do not want x to equal -1, so we put an open circle. Greater than, we go to the right. X less than -2. Again, we put an open circle because x cannot equal -2. Less than, we go to the left. But again, we're asked to put our answer in interval notation. And doing this gives us our answer of -infinity up to -2, open parenthesis because we do not want x to equal -2, union, again, open parenthesis, -1 up to infinity. And this is how we solve absolute value inequalities. Thank you, and we'll see you next time. Let's solve inequalities that involve radicals. For example, let's solve the following inequality for x. All right, so what does the left-hand side here equal? Most students will say that it equals x minus 6, which is not true. In fact, it equals the absolute value of x minus 6. That is, the square root of something squared is only equal to that thing if that thing is greater than or equal to 0. Otherwise, it's the negative of it. Or the square root of y squared is equal to the absolute value of y. For example, the square root, say, of 2 squared is equal to the square root of 4, which is 2. So yes, the square root of y squared is y. But what about the square root, say, of -2 squared? If that y is negative, this is the square root of 4, which is 2. So these aren't equal, they're the negatives of each other. So be very careful here. It's a very common mistake. Therefore, the inequality that we need to solve is that the absolute value of x minus 6 is less than or equal to 9. And remember, when solving absolute value inequalities, this means that -9 has to be less than or equal to x minus 6, has to be less than or equal to 9. So this translates into this compound inequality. And now we can add 6 everywhere, which gives us -9 plus 6 is less than or equal to x is less than or equal to 9 plus 6, or -3 is less than or equal to x is less than or equal to 15. Which we could write in interval notation as the interval -3 up to 15. Or we could even graph it. The solution set would be the interval from -3, including -3, all the way up to 15, including 15. So just be really careful that you use the absolute value here. All right, let's see another example. Let's solve this inequality for y. Again, we have the square root of something squared, and be careful, remember, it's the absolute value of that thing, which needs to be greater than 5. So when solving absolute value inequalities, if we have the absolute value of something is larger than 5, then that means that that quantity is either larger than 5 or that quantity is smaller than -5. And now we'll solve this compound inequality by working each side separately. Solving this first inequality, we subtract 3 from both sides, which gives us negative 2y is greater than 5 minus 3, or negative 2y is greater than 2. And now we'll divide both sides by negative 2. But remember, we have to flip or reverse the direction of this inequality, which gives us y is less than negative 1. All right, and what about the second inequality? Again, we'll subtract 3 from both sides, which gives us negative 2y is less than negative 5 minus 3, or negative 2y is less than negative 8. Again, dividing by negative 2. And flipping or reversing the direction of our inequality gives us that y is greater than 4. And because these inequalities are joined by the word or, our solution here will be the set of all y that make at least one of these inequalities true. So graphing this gives us the following. Let's say this is negative 1. Less than negative 1, we do not want to include negative 1, so we put an open circle, and less than we go to the left. And let's say this is 4. We do not want to include 4, so we put an open circle. Greater than, we go to the right, which would be our answer here. And in interval notation, we could write negative infinity up to negative 1, open parenthesis because we don't want to include negative 1, union, again, open parenthesis at 4, up to infinity. So just be very careful that you use this absolute value here when starting off. Thank you, and we'll see you next time.
Welcome. In this unit, we'll be talking about polynomial and rational functions. Polynomial and rational functions are amongst the most useful functions in mathematics because they come up a very large amount of the time. When you get into your calculus courses, one of the first things you'll learn is how to do calculus with polynomial and rational functions. Well, what is so special about these two types of functions? A lot of real-world examples from engineering, physics, business, biology, etc. involve polynomial and rational functions, which is why we're going to spend a particular amount of time studying these. Let's begin by defining these functions. A polynomial function is simply the sum of terms involving powers of x. Here, x is some variable, and the powers, the n minus 1, etc. that you see listed here, are just integer numbers. They could be 0, 1, 2, 3, 4, etc. The coefficients of each term, denoted by the a's here, each coefficient is just some constant number. That constant number could be anything. It could be 2, it could be 7, it could be a half. Those a's are just holding the place of constants. When we sum them up like this, we call that a polynomial. Another type of function we'll be dealing with is rational functions. Rational functions are simply the ratio of two polynomials. So a rational function here, I've denoted as r of x, is the ratio of two polynomials. In the numerator, you have p of x, in the denominator, a q of x. The one special stipulation we want to make is that the denominator should not equal 0. So when we talk about the domain of rational functions, we'll always specify that the denominator polynomial cannot equal 0, so that q of x will not equal 0. Let's give an example of when we might encounter a function that's a polynomial or a rational function. In this case, let's talk about the most popular polynomial, in my opinion, the quadratic equation. Well, a common example that you've probably heard before is projectile motion. In physics, you'll probably take a course where you learn about the projection of a ball. When I throw a ball with a particular velocity, what is the trajectory of that ball? And we'll ask lots of questions like, how long does it take for the ball to fall back into my hand? How long does it take for the ball to reach a certain height? What is the maximum height this ball reaches? Or if I drop this ball, how long does it take the ball to reach the ground? These are all questions that we can answer using polynomial functions. Projectile motion is related to quadratics in two separate ways. One, the shape I get if I take a ball and I launch it at a particular angle with a particular velocity, that ball moves in what we call a parabolic orbit or a parabolic trajectory. So it kind of looks like a parabola. Another relationship is that when you drop a ball, the speed of the ball is such that the position of the ball as a function of time satisfies a quadratic equation. Namely, the position is related to time squared. So if I drop this ball, the position would have been a function of t squared. In general, there's a physics equation, h equals h0 minus 16t squared. This equation is the equation for a ball dropped, or any object dropped, from a height h0 falling under Earth's gravity. That 16 you see there comes from the equation for Earth's gravity, or namely the gravitational constant on the Earth. And this one happens to be in feet as our measurement. Let's do an example problem. Suppose we drop a ball from a height of 200 feet off the roof of a building, and we want to know when that ball will hit the ground. Well, using that equation from physics, we can set up the equation h of t equals 200 minus 16t squared. And since I want to know when it hits the ground, I want to know when the height is 0, because the ground is at the bottom, so I set that equation equal to 0. Let's go ahead and solve this equation. I'm going to move all the terms involving t to one side and all the constants to the other side. I get 16t squared equals 200. Now if I solve for t, I can divide both sides by 16, and I get t squared equals 200 over 16, or I can simplify that to 12.5. Finally, if I want to get t by itself, I know t squared is 12.5, so t must be the square root of 12.5, which if you bust out a calculator here, that's 3.54 seconds. You might be asking yourself, well, when I take t squared equals something and I take the square root, don't I get a plus or minus? You're right. Normally you would say plus or minus the square root of 12.5, but because here t represents time, time can't be negative, so we'll only be talking about the positive values of time, and that's why I just picked the positive 3.54 seconds. So there's an example of how we would use a polynomial, in this case a quadratic equation, to solve for an important information from an application problem. Let's move on. What are you going to learn in this unit? Well, in this unit you'll learn several skills involving polynomial and rational functions. Namely, you'll learn to solve quadratic equations, which you probably already encountered in this course earlier, but here we're going to be focusing on three main techniques. You're going to be solving quadratic equations by factoring, something you've already played with a little bit. You'll also learn a technique called completing the square, and you'll learn how to use the quadratic formula. Another thing we'll be doing is graphing and working with these graphs of quadratic functions, namely parabolas. So you'll be learning about what happens when you transform the graphs of parabolas and how to find the vertex of these parabola graphs. Another thing we'll be learning to do is performing polynomial long division. Polynomial long division is a useful skill that will come up later in calculus. At this point, it may not seem clear to you why this is a wonderful, useful skill, but trust us, this is a precalculus course, and we're hoping that this skill will come back and help you later. Another thing we'll be learning to do is performing arithmetic with complex numbers. Complex numbers are things involving I, or the square root of a -1. That's called an imaginary number. So we'll be dealing with how to do arithmetic, add, subtract, multiply, and divide, numbers involving those complex numbers, namely square root of -1s. We'll also learn how to work with some rational functions. We'll be able to find their asymptotes and graph rational functions. We'll also be talking about how to solve polynomial and rational inequalities. You've already worked a little bit with polynomial inequalities when you dealt with linear inequalities. Now we'll learn how to deal with it when there's higher powers, such as quadratic parts. What are the applications of these rational and polynomial equations? There's a lot of examples. We already saw projectile motion. For those of you interested in the business world, a lot of profit equations involve quadratic or polynomial equations, and you'll very often want to learn how to find maximums of things like that. And if you know the graph, it's very easy to find a maximal term for something like a profit function. Another thing that comes up a lot is manufacturing. When you're trying to make boxes or containers for things, you want to minimize the amount of materials you use and maximize the amount of space available for your product. This is an example of using polynomial functions. There's a lot of polynomial functions that come up in other areas. If you skim through your book, you'll see examples of applications to physiology and muscle contraction, shooting of a basketball, and all sorts of other examples like that. Well, I hope you enjoy learning about polynomial and rational functions. Thank you, and I'll see you next time.
All right, let's look at factoring a quadratic expression. For example, let's factor x squared minus 10x plus 21. To factor this expression means we want to write it as a product, x plus m times x plus n, where m and n are integers. Now think about what must be true. Let's FOIL this right-hand side. We have x squared plus n times x plus m times x plus m times n, or x squared plus n plus m times x plus m times n. So in order for this equality to hold, the coefficient of x on the left, namely -10, has to be equal to the coefficient of x on the right, n plus m, and then these constants, 21 and m times n, also have to be equal. That is, n plus m has to be equal to -10, and m times n is equal to 21. So let's start by looking at some factors of 21. And whichever factors of 21 add up to give us -10 will be the m and n we're looking for. So let's make a table here. So m, n, and n plus m. All right, so what are some factors of 21? We have 1 and 21. We have -1 and -21. We have 3 and 7, and -3 and -7. When we add these values together, 1 plus 21 is 22. This is not -10 that we're looking for. -1 minus 21 is -22. It's also not -10. 3 plus 7 is +10, so it's not -10. But if we add these two factors together, yes, these add up together to give us -10. So therefore, we found our m and n up here. So our answer then is x minus 3 times x minus 7. This method of factoring is sometimes referred to as factoring by trial and error, because we're trying different factors of 21 until we find the ones that add up to -10. And let's verify to ourselves that indeed we did get the right factorization here. So if we FOIL this, we get x squared minus 7x minus 3x plus 21, which is equal to x squared minus 10x plus 21, which, yes, is our expression. Now, sometimes you'll see these problems done as follows. We'll still want to find these two numbers, n and m, that add up to -10 and multiply to 21. But then this -10x will be rewritten as follows. We still have the x squared, but then we have these numbers down here, -3 and -7, that add up to -10. So we'll rewrite -10x as -3x minus 7x, and then we still have the plus 21. And then we'll factor by grouping. So we'll group these first two terms together and the last two terms together. We'll factor out an x from the first two terms, which leaves us with x minus 3. And then we'll factor out a negative 7 from the last two terms, which also leaves us with an x minus 3. And then we factor out this common binomial here, which leaves us with the same answer of x minus 3 times x minus 7. Now this is sometimes called the AC method because we want to look at a quadratic expression of the form ax squared plus bx plus c and find factors of a times c that add up to b. And in our case, a was 1 and c was 21. Now this AC method is more commonly used when our a is greater than 1. So let's see an example of that. For example, let's factor 2x squared minus 7x plus 3. Let's compare it to the quadratic form ax squared plus bx plus c. So we see here that our a is equal to 2, our b is equal to negative 7, and our c is equal to 3. Let's apply this AC method that was just described. What we do is we multiply a and c together, so it's 2 times 3, which is 6. And we want to look at factors of 6 that will add together to give us our b, or a negative 7. And we find that the factors would be negative 1 and negative 6. Therefore, we rewrite this quadratic expression as 2x squared and then minus 1 times x, or just minus x, and then minus 6x plus 3. And then we factor by grouping. And from the first two terms, we can factor out an x, and we're left with 2x minus 1. And from the last two terms, we can factor out a negative 3, and then we're also left with 2x minus 1. Which then we can factor out this common binomial, which gives us our answer of 2x minus 1 times x minus 3. Now, how would we factor this? By trial and error. In other words, we want to try to write our quadratic expression 2x squared minus 7x plus 3 as a product of two binomials. But if we FOILed out these binomials, the first term would have to be 2x squared. So 2x and x would work on our first slots. And our last term after FOILing would have to be 3. So what are our choices here for the second slots? Well, we could put a plus 1 here and a plus 3 here, because 1 times 3 is 3. Or we could put minus 1 and minus 3, because minus 1 times minus 3 is also 3. Or the other way around, we could have minus 3 here and minus 1 here, as well as plus 3 here and plus 1 here. Now remember that our outer and inner terms would have to combine to give us this negative 7x. Therefore, this first choice here, this plus 1 plus 3, as well as the last choice, the plus 3 plus 1, can't work because their outer and inner terms would combine to give us a positive number, which means these middle two here would be our only possibilities. Now what happens if we FOIL these two binomials out? We'd get 2x squared minus 2x minus 3x, which is minus 5x, and then plus 3. So our middle term is not right. So we'll cross this off as well. But if we FOILed these two binomials out, we would get to our original quadratic expression. Therefore, this is the factorization we found by the trial and error method, which is the same answer that we found by the AC method. All right, and this is how we factor a quadratic expression. Thank you, and we'll see you next time. Let's work with special factoring formulas here. For example, let's factor this expression. Now this is what we call the difference of two squares. In other words, this is actually equal to 8u quantity squared minus 5 squared. So it's the difference of two squares. And in this type of situation, there's a special formula that can help us factor this. And the formula is that a squared minus b squared is equal to a minus b times a plus b. And let's think about why this is true. Let's FOIL the right-hand side here. We'd have a squared plus ab minus ba minus b squared. But ab and ba are the same by commutativity, so they'll cancel here. And we're just left with the left-hand side. Okay, let's apply that here with a equal to 8u and b equal to 5. In other words, this is equal to a minus b, or 8u minus 5, times a plus b, or 8u plus 5, which would be our answer. All right, let's see another special formula. Let's factor this expression. Now this is what we call a perfect square. And there are special formulas here as well. And the formulas are that a squared plus 2ab plus b squared is equal to a plus b quantity squared, or a squared minus 2ab plus b squared is equal to a minus b quantity squared. Again, we can verify these formulas by FOILing out the right-hand sides. However, we'll just do that with the last one here. A minus b quantity squared. This means a minus b times a minus b, which is equal to a squared minus ab minus ba, and then plus b squared. And ab and ba are the same, so we'll have two of them. Which is the left-hand side here. Now, a tip-off that our expression might be of this form is that both the first term and the last term are perfect squares. That is, this is equal to 2x quantity squared minus 20x, and then plus 5 squared. Now, if this middle term here, 20x, is equal to 2 times the product of this and this, then it's going to be of this form. And sure enough, this is equal to 2 times 2 times 5 is 20. So this is 20x. And because of this negative here, we'll be using this second formula down here. In other words, this is of the form a squared minus 2ab plus b squared, where a is equal to 2x and b is equal to 5. Therefore, by this formula, this will factor into a minus b quantity squared, or 2x minus 5 quantity squared. Now, sometimes it's hard for students to recognize these perfect square forms. If you didn't notice that this was of this form, you could have factored in other ways and you would have gotten to the same answer. But it is very useful if you can recognize these forms. Let's see another one. Let's factor this expression. Now, this is what we call a sum of two cubes. In other words, this is equal to 2x quantity cubed plus y squared quantity cubed. And again, there's a special formula in this case. And the formula is that a cubed plus b cubed factors into a plus b times a squared minus ab plus b squared. Now there's also a formula for the difference of two cubes. And although we're not going to be using it here, let's write it anyway. It states that a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. Notice on this first formula, we have a plus here and a plus here, but a minus here. Whereas on the second one, we have a minus here and a minus here, but a plus here. Again, we can verify these formulas by multiplying out the right-hand sides, but let's just show that with the first one here that we're going to be using. That is, we have a times a squared minus ab plus b squared, and then plus b times a squared minus ab plus b squared, which is equal to a cubed minus a squared b plus ab squared plus ba squared minus ab squared plus b cubed. And the minus a squared b and plus a squared b will cancel, as well as the ab squared and minus ab squared. And we're left with the left-hand side of our formula, a cubed plus b cubed. Okay, so let's apply that here with a equal to 2x and b equal to y squared. So by our formula, this is equal to a plus b, or 2x plus y squared, and then times a squared, which is 2x quantity squared, minus a times b, and then plus b squared, or plus y squared squared, which is equal to 2x plus y squared times 4x squared minus 2xy squared plus y to the fourth, which would be our answer. So it's very useful to be able to recognize these special factoring formulas. They could help you out a lot. Thank you, and we'll see you next time. Let's look at factoring by grouping. For example, let's factor the following expression by grouping. Now, to factor means we want to write this expression as a product of other numbers or algebraic expressions. Now, looking here, there is nothing in common to all four of these terms. And when that's the case, we try to group terms together and look for common factors. And we can begin by trying to group the first two terms together and the last two terms together. In other words, this is equal to 4v to the fifth plus v to the fourth, and then plus 20v plus 5. And now the greatest common factor in the first two terms is v to the fourth power. Factoring that out, we're left with 4v plus 1. And the greatest common factor in the second two terms is a 5. Factoring that out, we're left with 4v plus 1, which is the same binomial expression in the first grouping, which is why factoring by grouping works here, because now we can factor that out of both of these. In other words, this is equal to 4v plus 1 times v to the fourth plus 5, which would be our answer. Let's look at another example. Again, let's factor this expression by grouping. And we'll start in the same way. We'll group the first two terms together as well as the last two terms. In other words, this is equal to 5w cubed minus 4w squared plus negative 25w plus 20. And now the greatest common factor in the first two terms is a w squared. And when we factor that out, we're left with 5w minus 4. Now, what is the greatest common factor in the second grouping? Well, we could factor either a 5 out or a negative 5 out. But remember, our hope is that we're going to get the same binomial left over. So what happens when we factor out a 5 here? We'd be left with negative 5w plus 4, which is not that same binomial. However, if we factor out a negative 5, we're left with 5w minus 4, which is that same binomial. So that's what we want to factor out, is the negative 5. So this is minus 5 times 5w minus 4. And now we can factor this binomial out of each of these groupings, which gives us 5w minus 4 times w squared minus 5, which would be our answer. All right, let's see one more example. Again, let's factor this by grouping. And we'll begin in the same way. We'll group together the first two terms and then the last two terms, which gives us 3pr minus qr and then plus 6ps minus 2qs. Now the greatest common factor in these first two terms is an r. When we factor that out, we're left with 3p minus q. Now remember, our hope is to get the same binomial left over in the second grouping. And if we pull out a 2s, we'll be left with that same binomial, won't we? 3p minus q. So let's do that. So we have plus 2s times 3p minus q. And then factoring that out of each of these groupings gives us 3p minus q times r plus 2s, which would be our answer. Now, in all these examples, we've been starting with grouping the first two terms and then the last two terms. But what if we started a little bit different here? So we still have this expression, 3pr minus qr plus 6ps minus 2qs. But instead of grouping the first two terms and the last two terms, what if we grouped the first term and the third term together, and then the second term and the fourth term? In other words, let's write this as 3pr plus 6ps plus negative qr minus 2qs. Now the greatest common factor in the first two terms is a 3p, so let's pull that out. And we're left with r plus 2s. Now remember, in this second grouping over here, our hope is that after factoring, we have the same binomial left over. So if we factor out a negative q here, we'll be left with r plus 2s, which is the same binomial. So let's do that. So we have minus q times r plus 2s. And now we can factor out that binomial, which leaves us with r plus 2s times 3p minus q. And by commutativity, that's the same as this, isn't it? Okay, and this is how we factor by grouping. Thank you, and we'll see you next time. Let's look at solving a quadratic equation. For example, let's solve this equation here for x. Now, when solving quadratic equations, it's useful to have 0 on one side and see if we can factor the other. Well, here we already have 0 on the right, so let's see if we can factor the left-hand side, which we can. It factors into x plus 5 times x minus 1. And now we can use the fact that if we have a product of factors equal to 0, then either the first factor is equal to 0 or the second factor is equal to 0, or both. So let's use that here. So we have a product of factors equal to 0, which means either the first factor, x plus 5, is equal to 0, or the second factor, x minus 1, is equal to 0, which means x is equal to negative 5 or x is equal to 1, which would be our answers. All right, let's look at another example. Let's solve this equation for y. Now this is a bit different from the first example in that we don't already have 0 on the right-hand side. So let's start off by bringing the 3 to the left-hand side, which gives us 2y squared plus 5y minus 3 is equal to 0. And now we have 0 on the right-hand side. So let's see if we can factor the left-hand side here. And we can. It factors into 2y minus 1 times y plus 3. And again, we have a product of factors equal to 0, which means either the first factor, 2y minus 1, is equal to 0, or the second factor, y plus 3, is equal to 0. And then adding 1 and dividing by 2 gives us that y is equal to 1/2, or subtracting 3 gives us that y is equal to -3, which would be our answer. So this is how we solve this type of quadratic equation. We get 0 on one side and factor the other. Thank you, and we'll see you next time. Let's learn about the discriminant. Let's find the number of real solutions of each of these three quadratic equations. Let's first recall the quadratic formula. It gives us the solutions to quadratic equations of this form: ax squared plus bx plus c is equal to 0. And those solutions are given by x is equal to -b plus or minus the square root of b squared minus 4ac, all divided by 2a. However, here we're not asked to find the solutions, but rather the number of real solutions. And this quantity here under this square root is what determines that. This quantity is what we call the discriminant. And if we think about it, if this discriminant, this b squared minus 4ac, is a positive real number, then there'll be two real solutions to this quadratic equation. -b plus the square root of that positive number divided by 2a, and -b minus the square root of that positive number divided by 2a. So in this case, there are two real solutions. Now, when the discriminant is identically equal to 0, there is only one real solution. Namely, x equal -b divided by 2a. Because in the numerator, we'd be adding and subtracting 0. And finally, what if that discriminant is a negative number? Then there are no real solutions. Because the square root of a negative number does not yield any real number. We'd have complex solutions, but not real solutions. So let's compute this discriminant for each of our three equations here. So for the first equation, we have a is equal to 3, b is equal to -6, and c is equal to 5. So therefore, our discriminant, b squared minus 4ac, is equal to -6 squared minus 4 times 3 times 5, which is equal to 36 minus 60, which is equal to -24, which is a negative number. Which means we're down in this third case, aren't we? Which means our first equation has no real solutions. All right, what about our second equation here? We have that a is equal to 3, b is equal to -6, and c is equal to 1, which means our discriminant then, this b squared minus 4ac, is equal to -6 squared minus 4 times 3 times 1, which is equal to 36 minus 12, which is equal to 24, which is greater than 0, which means we're in this first case down here. And therefore, our second equation has two real solutions. All right, and what about our last equation here? Our a is equal to 3, b is equal to -6, and c is equal to 3, which means that the discriminant b squared minus 4ac is equal to -6 squared minus 4 times 3 times 3, which is equal to 36 minus 36, which is equal to 0. And therefore, we're in this second case down here, which means our third equation has one real solution. So the discriminant helps us determine how many real solutions we have to a given quadratic equation. Thank you, and we'll see you next time. Let's learn about the quadratic formula. For example, let's use the quadratic formula to solve this equation for x. And here's the quadratic formula. It states that the solutions to quadratic equations of this form are given by x equal -b plus or minus the square root of b squared minus 4ac, all divided by 2a. And by the way, this is a direct result of completing the square. And our equation here is of that form where a is equal to 3, b is equal to 1, and c is equal to -2. So the quadratic formula tells us that the solutions are given by -b or -1 plus or minus the square root of b squared or 1 squared minus 4 times a, which is 3, times c, which is -2, all divided by 2 times a, or 2 times 3, which is equal to -1 plus or minus the square root of 1, and then we have plus 24, because it's -4 times 3, which is -12, times -2, which is positive 24, all divided by 6. And this is equal to -1 plus or minus the square root of 25 divided by 6, or -1 plus or minus 5 divided by 6, which means x is equal to -1 plus 5 divided by 6, or x is equal to -1 minus 5 divided by 6. And what are these two numbers? This is x is equal to -1 plus 5 is 4, and 4/6 reduces to 2/3. Or x is equal to -1 minus 5 is -6, and -6 divided by 6 is -1. So these would be our answers. Now, if we weren't told to use the quadratic formula here, we wouldn't want to. Because doesn't the left-hand side here just factor? It factors into 3x minus 2 times x plus 1. And therefore, we would get x is equal to 2/3, or x is equal to -1, which are the same answers. But perhaps you didn't see the factorization, so it's always okay to use the quadratic formula. You'll get to the same answers. Let's see another one. Let's use the quadratic formula to solve for y. Again, here's the quadratic formula. So in this case, we have that a is equal to 2, b is equal to 5, and c is equal to -1. So by this formula, we have x is equal to -b, which is -5, plus or minus the square root of b squared, or 5 squared, minus 4 times a, which is 2, and then times c, which is negative 1, all divided by 2 times a, or 2 times 2. And this is equal to negative 5 plus or minus the square root of 25, and then plus 8, all divided by 4, which is equal to negative 5 plus or minus the square root of 33 divided by 4. Therefore, our answers are x equal to negative 5 plus the square root of 33, all divided by 4, or x is equal to negative 5 minus the square root of 33 divided by 4. Now, unlike the first example, factoring here would not have helped us. However, we could have solved this by completing the square, and we would have arrived at the same answers that the quadratic formula just gave us. And this is how we use this formula. Thank you, and we'll see you next time. Let's solve a quadratic equation by completing the square. Let's solve this equation 4x squared plus 8x plus 1 is equal to 0 by completing the square. The first thing we'll do is bring this constant term, namely the 1, to the right-hand side of the equation, which gives us 4x squared plus 8x is equal to negative 1. Now, with completing the square, it is very important at this point to make sure that the coefficient of this square term is equal to 1. And right now, it is equal to 4. So what we need to do is divide both sides of the equation by 4. That is, we'll divide this first term by 4, the second term by 4, as well as the negative 1 by 4. Which leaves us with x squared plus 2x, and let's leave a little bit of room here, is equal to negative 1/4. And now the coefficient of the square term is 1. So the next step then in completing the square is that we take 1/2 the coefficient of x, which in this case is 2, and 1/2 of 2 is 1, and then we square this number. So we get 1 squared is equal to 1. And then we add this to both sides of the equation. So we'll have a plus 1 here and a plus 1 here. And now the left-hand side is a perfect square. It is x plus 1 quantities squared. And we've completed the square on the left. And this is equal to negative 1/4 plus 1, which is 3/4. And now we'll take the square root of both sides, which gives us x plus 1 is equal to plus or minus the square root of 3/4, or x plus 1 is equal to plus or minus the square root of 3 divided by the square root of 4, which is 2. And then we'll subtract 1 from both sides of the equation, which gives us x is equal to negative 1 plus or minus the square root of 3/2. And know that this means we have two solutions to this equation. We have x is equal to negative 1 plus the square root of 3/2, or x is equal to negative 1 minus the square root of 3/2. And this is how we solve a quadratic equation by completing the square. Thank you, and we'll see you next time. let's look at word problems that we can use quadratic equations to help us solve. For example, the perimeter of a rectangle is 22 feet and the area is 24 square feet. Let's find the dimensions of the rectangle. So let's let L be the length of the rectangle and W be its width. We're given that the perimeter is 22 feet. And recall that the perimeter of a rectangle is 2 times L plus 2 times W. Therefore, this is equal to 22. And we're also told that the area is 24 square feet. And remember that the area of a rectangle is length times width. So this has to be equal to 24. Now we can divide both sides of this perimeter equation by 2, which gives us L plus W is equal to 11, or L is equal to 11 minus W, which we then can plug into this area equation, which would give us an equation that just involves W. Namely, 11 minus W times W is equal to 24, or 11W minus W squared is equal to 24. And bringing all the terms to one side, we get W squared minus 11W plus 24 is equal to 0. And now the left-hand side will factor. It factors into W minus 3 times W minus 8. And we have a product of factors equal to 0, which means either the first factor is 0 or the second factor is 0. If the first factor is 0, then W would be equal to 3. And if the second factor is 0, then W would be equal to 8. Now, if W is equal to 3, then we can plug this value into here, and we'll get L is equal to 11 minus 3, or 8. And if W is equal to 8, then plugging this into here, we get that L would be equal to 11 minus 8, or 3. So in either case, our rectangle is 3 feet by 8 feet, which are the dimensions that we're looking for. All right, let's look at another example. A model rocket is launched with an initial upward velocity of 30 meters per second. The rocket's height after t seconds is given by this equation here. Find all values of t for which the rocket's height is 10 meters. So we're launching this rocket from the ground, and we want to know the time at which its height is 10 meters. But then it's going to come back down, and we want to know the other time at which its height from the ground is 10 meters. And we can find these times by plugging 10 in here for h and solving for t. Namely, 10 is equal to 30t minus 5t squared, and bringing all the terms to one side gives us 5t squared minus 30t plus 10 is equal to 0. And now we can divide everything by 5 to simplify this equation, which gives us t squared minus 6t plus 2 is equal to 0. Now this does not factor, so let's use the quadratic formula to help us solve for t. We have t is equal to negative b, or negative 6, plus or minus the square root of b squared, which is negative 6 squared, minus 4 times a, which is 1, times c, which is 2, all divided by 2 times a, or 2 times 1, which is equal to 6 plus or minus the square root of 36 minus 8, or 28, divided by 2. Now 28 is 4 times 7, so this is equal to 6 plus or minus the square root of 4 times 7 divided by 2, which is equal to 6 plus or minus 2 square root of 7 divided by 2. And dividing both terms in the numerator by 2 gives us 3 plus or minus the square root of 7. So we have t is equal to 3 minus the square root of 7, and t is equal to 3 plus the square root of 7. And if we put these values into our calculator, we get that this is approximately 0.35 seconds, and this is approximately 5.65 seconds. So the rocket's height is 10 meters at approximately t equal to 0.35 seconds on the way up. And then its height from the ground is 10 meters again at t approximately 5.65 seconds. And these would be the two values of t that we're looking for. All right, and these are a couple of examples of how quadratic equations can help us solve word problems. Thank you, and we'll see you next time. Let's look at simplifying fractions. For example, let's simplify this expression here. Now, these types of fractions, where the numerator or denominator or both contain a fraction, are often referred to as either complex fractions or compound fractions. However, don't confuse the word complex here with the complex number system. Now remember, when we're dividing two fractions, we multiply the numerator by the reciprocal of the denominator. That is, we flip the bottom fraction and multiply. And when we multiply fractions, we multiply the numerators and we multiply the denominators. And now this x squared minus 9 will factor. It's a difference of two squares, which gives us 5 times 3 plus x divided by 15x times, and this factors into x plus 3 times x minus 3. Now x plus 3 and 3 plus x will cancel, and we're assuming here, of course, that x does not equal negative 3. And 5 goes into 15 3 times, so we'll have a 3 left here in the denominator. And therefore, our answer is 1 divided by 3x times x minus 3. All right, let's see another example. Let's simplify this fraction. Now, there are different approaches here. For example, we could work with the numerator separately and then work with the denominator separately. However, the method that students seem to like best when working with this type of fraction is to first eliminate these denominators here. And we can do that by multiplying both the numerator and denominator by the least common multiple of these denominators, which in this case is their product, x times y. So let's do that. We'll multiply the numerator by x times y, as well as the denominator. Again, when multiplying fractions, we multiply the numerators and we multiply the denominators. And now we'll distribute this xy to these three terms, as well as distribute this xy to these two terms, which gives us x divided by y times xy plus negative 2 times xy plus y divided by x times xy, all divided by x divided by y times xy plus negative y divided by x times xy. Now the y's will cancel here, as well as the x's. And the same thing in the denominator, the y's will cancel, as well as the x's. And we are assuming here, of course, that x and y both are non-zero. And what are we left with? We have x times x, which is x squared, and then we have minus 2xy, and then plus y times y, which is y squared, divided by x times x, which is x squared, and minus y times y, which is y squared. And look, we've eliminated those original denominators. And now we can factor. Namely, this is equal to x minus y quantity squared divided by, and the denominator is the difference of two squares, which factors into x minus y times x plus y. And now we can cancel an x minus y from both the denominator and the numerator, which would leave us with 1 in the numerator. And we are assuming here, of course, that x minus y is non-zero, or that x does not equal y, which leaves us with our answer of x minus y divided by x plus y, which doesn't look quite as complex, does it? And this is how we simplify these types of fractions. Thank you, and we'll see you next time. Let's look at simplifying a ratio of polynomials. For example, let's simplify this expression here. The first thing we can do is factor a 3 out of the numerator, which gives us 3 times x squared plus x minus 6, all divided by x squared plus 4x plus 3. And now we can factor both quadratic expressions in the numerator and denominator, which gives us 3 times x plus 3 times x minus 2 divided by x plus 3 times x plus 1. And then we can cancel these common factors of x plus 3, and we're assuming here, of course, that x does not equal negative 3, which leaves us with our answer of 3 times x minus 2 divided by x plus 1. All right, let's look at another example. Let's simplify this expression here. Again, we can begin by factoring out the common factor in the numerator, which is 4 here, which leaves us with 1 minus w squared, still divided by w squared plus w minus 2. And now we can factor both the numerator and denominator. The numerator here is the difference of two squares, and it factors into 1 minus w times 1 plus w. And the denominator will factor into w minus 1 times w plus 2. Now, although these factors are not exactly the same, they're the negatives of each other, aren't they? That is, w minus 1 is equal to negative 1 minus w. And to see this, we can distribute the negative or negative 1 through to both of these terms, which would give us negative 1 plus w which is w minus 1. So let's use this fact here. That is, this is equal to 4 times 1 minus w times 1 plus w, and now divided by negative 1 minus w times w plus 2. And now we can cancel these common factors of 1 minus w, and we're assuming here, of course, w does not equal 1, which leaves us with our answer of negative 4 times 1 plus w divided by w plus 2. And this is how we simplify a ratio of polynomials. Thank you, and we'll see you next time. Let's look at adding and subtracting rational expressions. For example, let's add these two rational expressions together. Just like when we add fractions, we need to make sure that the denominators are equal before we add the numerators. And here we see that they're different, which means we need to find the least common denominator. And in this case, it's the product x minus 1 times x minus 2. So this is equal to 5 divided by x minus 1. And now we need to multiply both the numerator and denominator by what's missing from the LCD, which in this case is x minus 2. And in the second fraction, what's missing is this x minus 1. All right, and by commutativity, this x minus 1 times x minus 2 and x minus 2 times x minus 1 are equal, which means now we can add the numerators. In other words, this is equal to 5 times x minus 2 plus 4 times x minus 1, all divided by x minus 1 times x minus 2. And now we can distribute both the 5 and the 4, which gives us 5 times x minus 10 plus 4 times x minus 4, all divided by x minus 1 times x minus 2. And finally, combining like terms in the numerator, we get our answer of 9x minus 14, all divided by x minus 1 times x minus 2. All right, let's see another one. Again, we notice that these denominators are all different, which means we need to find the LCD in order to combine the numerators. But what we'll need to do first is factor the denominators to see what that LCD is. So this first denominator will factor into y plus 3 times y minus 1. And then the second one factors into y minus 1 times y minus 2. And finally, the last one factors into y plus 3 times y minus 2. All right, so what is the LCD here? We see that this y plus 3 is a common factor to two different denominators, which means we only need to include it once in the LCD. Same with this y minus 1. as well as the y minus 2. Which means that the LCD is the product of those three binomials. So y plus 3 times y minus 1 times y minus 2. And this will be equal to y divided by y plus 3 times y minus 1. And again, we're going to build up these rational expressions by multiplying both the numerator and denominator by what's missing from the LCD. In this first case, it's the y minus 2. And in the second case, we're missing the y plus 3. And in the last case, we're missing the y minus 1. Again, by commutativity, these denominators are all equal, which means we can combine these into one fraction now. In other words, this is equal to y times y minus 2 minus 1 times y plus 3 plus 5 times y minus 1, all divided by y plus 3 times y minus 1 times y minus 2. And now distributing in the numerator, we get y squared minus 2y minus y minus 3 plus 5y minus 5 divided by y plus 3 times y minus 1 times y minus 2. And now combining like terms in the numerator, we have y squared. And then we have minus 2y minus y, which is negative 3y, plus 5y, which is positive 2y. And then negative 3 minus 5 is negative 8, divided by this y plus 3 times y minus 1 times y minus 2. And now the numerator factors. It factors into y plus 4 times y minus 2, and then we still have this y plus 3 times y minus 1 times y minus 2 in the denominator. And now look, these y minus 2's can cancel. And we're assuming here, of course, that y cannot equal 2. Which leaves us with our answer of y plus 4 divided by y plus 3 times y minus 1. And this is how we add and subtract rational expressions. Thank you, and we'll see you next time. Let's multiply rational expressions. For example, let's multiply these two rational expressions and simplify our answer. Now, in multiplying rational expressions, we proceed in the same way as we do when we multiply numerical fractions. That is, we multiply the numerators, and then we multiply the denominators. Which gives us 9 times 4 is 36, and then we have times b times y cubed, all divided by 8 times 3 is 24, and then times b, and then times y, which is y squared. Now 24 and 36 are both divisible by 12, which means after simplifying, we'll have a 2 left here and a 3 left here. And we can also cancel these b's, and we're assuming here, of course, that b does not equal 0. And finally, we can cancel 2 of the y's, which would leave us with 1 y in the numerator. And also, we're assuming here that y does not equal 0. Therefore, our answer is 3 times y, all divided by 2. Let's look at another example. Let's multiply these two rational expressions. Again, we multiply the numerators. So x plus 1 times x squared minus 4x plus 3 divided by x squared minus x minus 6 times 4x plus 4. And now let's factor. We still have this x plus 1, but the second term in the numerator factors into x minus 3 times x minus 1. And this first term in the denominator factors into x minus 3 times x plus 2. And finally, from this last term in the denominator, we can factor out a 4. And we're left with x plus 1. Now we can cancel these x plus 1's. And we're assuming x does not equal negative 1. As well as these x minus 3's. And we're assuming as well that x does not equal 3. Which leaves us with our answer of x minus 1 divided by, and don't forget that 4 in the denominator, it's 4 times x plus 2. And this is how we multiply rational expressions. Thank you, and we'll see you next time. Let's see some examples of dividing rational expressions. For example, let's divide 2x to the 4th y squared over 5y by 4x over 15y. Now, dividing by this is the same as multiplying by its reciprocal. In other words, this is equal to 2x to the 4th y squared divided by 5y, and then times, remember with the reciprocal, we flip. So this is 15y divided by 4x. And when we multiply fractions, we multiply the numerators and then multiply the denominators. So this would be equal to 2 times 15, which is 30, and then x to the 4th times y squared times y, which is y cubed, divided by 5 times 4 is 20, and then we have x times y. Now 20 and 30 are both divisible by 10, so we'd be left with a 2 here and a 3 here. And then we can cancel this x with one of the x's in the numerator, which would leave us with x cubed left over in the numerator. And we're assuming here, of course, that x does not equal 0. And then we're canceling one of the y's, which leaves us with y squared in the numerator. Again, we're assuming y does not equal 0, which would leave us with our answer of 3x cubed y squared divided by 2. Let's look at another example. Let's divide these two rational expressions. Again, we'll begin by multiplying by the reciprocal of this. Namely, this is equal to 4x minus 4 divided by 2x plus 3 times, and then we flip the second rational expression. So you have 2x squared plus 5x plus 3 divided by 2x squared minus x minus 1. Again, we multiply the numerators and multiply the denominators. So this is 4x minus 4 times 2x squared plus 5x plus 3 divided by 2x plus 3 times 2x squared minus x minus 1. And now we'll factor. We'll begin by pulling a 4 out of this first term. So we have 4 times x minus 1. And then this factors into 2x plus 3 times x plus 1, all divided by 2x plus 3. Then this factors into 2x plus 1 times x minus 1. And now the x minus 1's will cancel, and we're assuming here, of course, that x does not equal 1, as well as these 2x plus 3's. And we're assuming here that x does not equal negative 3/2, which leaves us with our answer of 4 times x plus 1 divided by 2x plus 1. And this is how we divide rational expressions. Thank you, and we'll see you next time. We'll be learning about the square root property here. Let's solve this equation for x. Now there are a few different ways to solve this. First of all, let's notice that the left-hand side here is the difference of two squares, isn't it? Namely, 3x quantity squared minus 4 squared. And remember, in this case, we have a special formula for factoring the difference of two squares, namely a squared minus b squared factors into a minus b times a plus b. So let's apply that here, with a equal to 3x and b equal to 4. That is, the left-hand side factors into 3x minus 4 times 3x plus 4. And now we have a product of factors equal to 0, which means either the first factor is 0 or the second factor is 0, which means that x is equal to 4/3 or x is equal to negative 4/3, which would be our answer. Now, rather than solving this equation this way, we could use the following property. The square root property states that the solutions to the equation c squared is equal to d, where d is a positive real number, are c is equal to plus or minus the square root of d. Now, how could we use this here? Well, let's start by adding 16 to both sides of this equation, which gives us 9x squared is equal to 16. And then dividing both sides by 9, we get x squared is equal to 16 divided by 9. And by this property, with c equal to x and d equal to 16 over 9, we get that the solutions to this equation are x is equal to plus or minus the square root of 16 over 9. Or x is equal to plus or minus 4/3, which are the same answers. Let's look at another example. Let's solve this equation for y. Now here, it's much more straightforward to just start off using our square root property, with c equal to 2y minus 5 and d equal to 9. Therefore, the solutions to this equation can be found as follows. We have c is equal to plus or minus the square root of d. So C, which in this case is 2y minus 5, is equal to plus or minus the square root of D, which is 9, or 2y minus 5 is equal to plus or minus 3, which means 2y minus 5 is either equal to 3 or 2y minus 5 is equal to negative 3. And adding 5 to both sides, we get 2y is equal to 8, or 2y is equal to 2. And now dividing both sides by 2, we get y is equal to 4, or y is equal to 1, which would be our answer. And this is how we use this square root property here. Thank you, and we'll see you next time. Let's look at solving rational equations. For example, let's solve this equation for x. The first thing we'll do is multiply both sides of the equation by this denominator here, which gives us 3 times x minus 4 is equal to negative 6 divided by x minus 4 times x minus 4. And the x minus 4's on the right will cancel as long as x does not equal 4, which would leave us with 3 times x minus 4 is equal to negative 6. And now we'll distribute the 3 to both of these two terms, which gives us 3x minus 12 is equal to negative 6. And then we'll add 12 to both sides, which gives us 3x is equal to negative 6 plus 12, or positive 6. And then dividing both sides by 3 gives us x is equal to 2. Now, when solving rational equations, it's very important to check your answer and make sure that it doesn't make the denominator here 0. And it doesn't. The only excluded value is x equal to 4. So x equal to 2 would work and would be our answer. All right, let's look at another example. Let's solve this equation for y. Again, we'll begin in a similar way and multiply both sides of the equation by this denominator here, y minus 2, which gives us y minus 2 times 1 minus y minus 3 divided by y minus 2 is equal to y minus 2 times 2y minus 3 divided by y minus 2. And now we'll distribute the y minus 2 to both of these terms, which gives us y minus 2 times 1 plus y minus 2 times negative y minus 3 divided by y minus 2 is equal to y minus 2 times 2y minus 3 divided by y minus 2. And again, we can cancel these common factors of y minus 2 on both the left and the right-hand side, assuming, of course, that y does not equal 2. Which leaves us with y minus 2 times 1, which is y minus 2. And then we have minus this whole quantity, y minus 3, is equal to 2y minus 3. And distributing our negative gives us y minus 2 minus y plus 3 is equal to 2y minus 3. And combining like terms on the left, we have y minus y is 0, and negative 2 plus 3 is 1. So we have 1 is equal to 2y minus 3, or adding 3 to both sides, we get 2y is equal to 1 plus 3, or 4, which means y is equal to 2. However, remember that we have to check our answer and make sure that it's not the excluded value up here. And sure enough it is. If y is equal to 2, then we'd be dividing by 0. So we need to cross off y equal to 2 as a possibility here, which means that there's no solution here. All right, let's see one more example. Let's solve the following equation for w. Now, what are we going to be multiplying both sides of this equation by? What we need to do is determine what the least common multiple of these denominators is, or the least common denominator, which we can do by factoring these denominators first. So doing this gives us 2w minus 1 divided by the first denominator factors into w plus 3 times w plus 3 is equal to 1 divided by, and now here we can factor out a w, and we're left with w plus 3. And then we still have this plus 2 divided by w. So the least common denominator then, or the least common multiple of these denominators, is w times w plus 3 times w plus 3, which is what we're going to need to multiply both sides of this equation by. That is, we have w times w plus 3 times w plus 3 times 2w minus 1 divided by w plus 3 times w plus 3 is equal to w times w plus 3 times w plus 3 times 1 divided by w times w plus 3 plus 2 divided by w. And now we'll distribute this entire product here to both of these terms, which gives us w times w plus 3 times w plus 3 times 2w minus 1 divided by w plus 3 times w plus 3 is equal to w times w plus 3 times w plus 3 times 1 divided by w times w plus 3 plus w times w plus 3 times w plus 3 times 2 divided by w. And again, we can cancel these common factors both on the left and right, assuming, of course, that w does not equal negative 3. And as long as w is not 0, we can also cancel these common factors here. Which leaves us with, don't forget this w out here, w times 2w minus 1 is equal to w plus 3 times 1, or w plus 3, and then plus, and then we have 2 times w plus 3 times w plus 3. And then distributing the w gives us 2w squared minus w is equal to w plus 3 plus 2 times, and then foiling this out gives us w squared plus 6w plus 9. Or 2w squared minus w is equal to w plus 3, and then distributing the 2 gives us plus 2w squared plus 12w plus 18. And now the 2w squareds will cancel. And now we can bring all the w terms to the left-hand side, which gives us negative w, and then minus w is negative 2w, and then minus 12w gives us negative 14w is equal to 3 plus 18, which is 21. So w is equal to negative 21 divided by 14, or negative 3/2. But remember, we have to check and make sure that this does not make our denominators appear 0. And it doesn't. The only excluded values would be w equal to 0 or negative 3. So this is our answer then. W is equal to negative 3/2. And this is how we solve rational equations. Thank you, and we'll see you next time. Let's look at solving rational equations. For example, let's solve this equation for y. We'll begin by multiplying both sides of the equation by the least common multiple of these denominators here, which would be their product. Namely, y plus 2 times y minus 1 times 8 minus 7 divided by y plus 2 is equal to y plus 2 times y minus 1 times negative 5 divided by y minus 1. And now let's distribute this product to both of these terms, which gives us y plus 2 times y minus 1 times 8 plus y plus 2 times y minus 1 times negative 7 divided by y plus 2 is equal to y plus 2 times y minus 1 times negative 5 divided by y minus 1. Now, on the left-hand side, as long as y does not equal negative 2, we can cancel the y plus 2's. And on the right, as long as y does not equal 1, we can cancel the y minus 1's, which leaves us with y plus 2 times y minus 1 times 8 plus y minus 1 times negative 7 is equal to y plus 2 times negative 5. And now let's FOIL this here. This leaves us with y squared plus y minus 2, still times 8. And then we still have the plus y minus 1 times negative 7 is equal to y plus 2 times negative 5. And now let's distribute the 8 to these three terms, the negative 7 to these two terms, as well as the minus 5 to these two terms, which gives us 8y squared plus 8y minus 16 minus 7y plus 7 is equal to negative 5y minus 10. And combining like terms on the left gives us 8y squared plus y minus 9 is equal to minus 5y minus 10. And now let's bring everything to the left-hand side, which gives us 8y squared plus y plus 5y is plus 6y. And then minus 9 plus 10 is plus 1 is equal to 0. And now the left-hand side factors. It factors into 4y plus 1 times 2y plus 1 is equal to 0. And now we have a product of factors equal to 0, which means either the first factor is 0 or the second factor is 0, which gives us that either y is equal to negative 1/4 or y is equal to negative 1/2. Now, in solving rational equations, it's very important at this point to check and make sure that these values do not make these denominators 0. And they don't. The only excluded values would be negative 2 or 1. And neither of these values are negative 2 or 1. So both of these would work. So this would be our answer here. All right, let's look at another example. Let's solve this equation for x. Again, we'll look at what the least common multiple of these two denominators are, and it would be this product here. So let's multiply both sides of the equation by this product. So x minus 2 times x minus 4 times 2 divided by x minus 2 times x minus 4 is equal to x minus 2 times x minus 4 times 2 plus 1 over x minus 4. Now let's distribute this product to both of these two terms, which gives us x minus 2 times x minus 4 times 2 divided by x minus 2 times x minus 4 is equal to x minus 2 times x minus 4 times 2 plus x minus 2 times x minus 4 times 1 divided by x minus 4. And as long as x is not equal to 2, we can cancel the x minus 2's on the left. Also, as long as x is not equal to 4, we can cancel the x minus 4's on the left and on the right over here. And what are we left with? We have 2 is equal to x minus 2 times x minus 4 times 2, and then plus x minus 2 times 1. Or 2 is equal to, and let's FOIL this out, we have x squared minus 6x plus 8, still times 2. And then we have plus x minus 2. And now we'll distribute this 2 through to all these terms here, which leaves us with 2 is equal to 2x squared minus 12x plus 16, and then plus x minus 2. Or combining like terms on the right, we have 2 is equal to 2x squared minus 11x plus 14. And now bringing all the terms to one side gives us 2x squared minus 11x plus 12 is equal to 0. And this left-hand side will factor into 2x minus 3 times x minus 4. Now we have a product of factors equal to 0, which means either the first factor is 0 or the second factor is 0. When the first factor is 0, we get x is equal to 3/2, and when the second factor is 0, we get x is equal to 4. Remember, we have to check that these values do not make our denominators 0 up here. And sure enough, when x is equal to 4, both of these denominators will be 0. 4 is an excluded value, so we have to cross it off our list here. Therefore, our only answer would be x is equal to 3/2. And this is how we solve rational equations. Thank you, and we'll see you next time. Let's look at solving equations that are quadratic in form. For example, let's solve this equation for x. Now, the first thing you'll want to notice here is that x to the 4th is the square of this. In other words, this is the same as x squared squared minus 13x squared plus 36 is equal to 0. So if we let u equal x squared, we can substitute this into this equation to give us u squared minus 13u plus 36 is equal to 0, which is a quadratic equation. Therefore, our original equation here is quadratic in form, isn't it? All right, how do we solve this equation? Well, we can factor the left-hand side, and it factors into u minus 9 times u minus 4. Now we have a product of factors equal to 0, which means the first factor, u minus 9, is equal to 0, or the second factor is 0, which means u is equal to 9, or u is equal to 4. Now, a very common mistake that students make here is that they'll think they're done at this point. However, we're not done, are we? This is what u equals, but we're asked to solve for x. And we can do that by substituting back in these values of u into this equation here. Which gives us 9 is equal to x squared, or 4 is equal to x squared. And then taking the square root of each side, we get x is equal to plus or minus the square root of 9, which is equal to plus or minus 3, or x is equal to plus or minus the square root of 4, which is equal to plus or minus 2. Therefore, our answer is x is equal to 3, negative 3, 2, or negative 2. All right, let's look at another example. Let's solve this equation for y. Again, this is the square of this. That is, this equation is really 3 times y to the 1/3 quantity squared plus 2y to the 1/3 minus 8 is equal to 0. Again, let's let u equal y to the 1/3 power, which we then can substitute into our equation. And this gives us 3u squared plus 2u minus 8 is equal to 0. And again, we have a quadratic equation, which we can solve by factoring. So the left-hand side factors into 3u minus 4 times u plus 2. So we have a product of factors equal to 0. So either the first factor is 0, or the second factor is 0. Adding 4 and dividing by 3 will give us u is equal to 4/3. Or subtracting 2, we get u is equal to negative 2. Again, be careful here. Do not think that you're done. Remember, we have to solve for y. This is what u is equal to. So we'll take these values of u and substitute them back into this equation to solve for y. That is, we have 4/3 is equal to y to the 1/3, or negative 2 is equal to y to the 1/3. And now we can cube both sides. So when we do that, we get y to the 1/3 cubed is equal to 4/3 cubed. Or y is equal to 4 cubed, which is 64, divided by 3 cubed, which is 27. Or cubing both sides here gives us y to the 1/3 cubed is equal to negative 2 cubed, which means y is equal to negative 2 cubed, which is negative 8. So these would be our answers. And this is how we solve an equation that's quadratic in form. Thank you, and we'll see you next time. Let's look at solving equations involving radicals. For example, let's solve this equation for w. Let's begin by squaring both sides of this equation so we can eliminate our radical. In other words, the square root of w plus 5 squared is equal to 4 squared. However, we have to be very careful when we square both sides of an equation that we check our answers at the end, because we could come up with extraneous solutions. All right, so we have w plus 5 is equal to 16, and subtracting 5 from both sides gives us w is equal to 16 minus 5, or 11. But remember, we have to check our answer. That is, we need to plug in w equal to 11 into our original equation before we squared both sides to see if the equation is satisfied. So the question is the square root of 11 plus 5 equal to 4? Or is the square root of 16 equal to 4? And it is. Therefore, w equal to 11 works and is our answer. All right, let's look at another example. Let's solve the following equation for x. Again, we'll begin by squaring both sides of this equation, which gives us the square root of x plus 31 squared is equal to x plus 1 squared. Or x plus 31 is equal to, and then squaring out the right-hand side gives us x squared plus 2x plus 1. And now bringing all the terms to one side gives us x squared, and then we have plus 2x minus x, which is plus x, and then 1 minus 31, which is negative 30, is equal to 0. And now we can factor the left-hand side. It factors into x minus 5 times x plus 6. So we have a product of factors equal to 0, which means either the first factor, x minus 5, is equal to 0, or the second factor, x plus 6, is equal to 0. Which gives us that x is equal to 5, or x is equal to negative 6. But remember, we have to check these answers. Let's start with x equal to 5. We'll plug x equal to 5 into our original equation before we squared both sides, wherever we see an x, to see if our equation is satisfied. That is, the question is the square root of 5 plus 31 equal to 5 plus 1? Or is the square root of 36 equal to 6? And it is. So 5 works. What about negative 6? Again, we're going to plug in negative 6 up here wherever we see an x. So the question is the square root of negative 6 plus 31 equal to negative 6 plus 1? Or is the square root of 25 equal to negative 5? And no, it isn't. The square root of 25 is positive 5. So we need to cross off x equal to negative 6 as a solution here. Which means our only answer then is x equal to 5. All right, let's look at one more example. Let's solve this equation for y. Again, we'll begin by squaring both sides of the equation. So we have the square root of y plus 7 squared is equal to, be careful, we're squaring the entire right-hand side here. which gives us y plus 7 is equal to, and now we need to FOIL this right-hand side out, which will give us 4 plus 4 times the square root of 3 minus y, and then plus 3 minus y. Now, unfortunately, we're still left with a radical in our equation, so we need to isolate that. And we can do that by bringing all these other terms to the left-hand side, which gives us y and then plus y, which is 2y, and then plus 7 minus 4 minus 3, which is 0, is equal to 4 times the square root of 3 minus y. And now let's divide both sides by 2, which gives us y is equal to 2 times the square root of 3 minus y. And now we can square both sides of this equation, which gives us y squared is equal to 2 times the square root of 3 minus y squared. Or y squared is equal to 2 squared is 4, and then times the entire quantity 3 minus y. And now distributing our 4 gives us y squared is equal to 12 minus 4y. And now we can bring all the terms to one side, which gives us y squared plus 4y minus 12 is equal to 0. And now we can factor the left-hand side. It factors into y minus 2 times y plus 6. So we have a product of factors equal to 0, which means either the first factor is 0, which means that y is equal to 2, or the second factor is 0, which means y is equal to negative 6. But remember, we have to check these answers. So let's start with y equal to 2. So we have to plug in y equal to 2 in this original equation, wherever we see a y, before we squared both sides. So the question is the square root of 2 plus 7 equal to 2 plus the square root of 3 minus 2? Or is the square root of 9 equal to 2 plus the square root of 1? And it is, because the square root of 9 is 3, and the square root of 1 is 1, and 2 plus 1 is 3. So yes, that works. What about y equal to negative 6? The question is the square root of negative 6 plus 7 equal to 2 plus the square root of 3 minus a minus 6, or plus 6? Or is the square root of 1 equal to 2 plus the square root of 9? And it's not, is it? Because the square root of 9 is 3, and 2 plus 3 is 5, and the square root of 1 is 1. And 1 is not equal to 5. So we need to cross off y equal to negative 6 here, which means our only solution then is y equal to 2. So be careful when solving equations involving radicals. You have to always check your answers to make sure that you're not getting extraneous solutions. Thank you, and we'll see you next time.
Welcome! In this video, we'll be learning about functions and graphs. Functions are probably the most important mathematical object you'll ever learn about, and you probably will spend most of your mathematics courses talking about functions. Functions come up all the time in the real world. Let's start by talking about the definition of function. A function is a correspondence between two sets of elements such that to each element in the first set there is a corresponding element in the second set, and there's one and only one of these elements in the second set. The first set we call the domain, and the second set, the ones that correspond to the first set, are called the range of our function. We usually denote functions by y equals f of x. The way we read this is y is a function of x. In other words, we input x into a function and we get some output value y. This is what we mean by y equals f of x, or y is a function of x. Let's consider an example of a function. My function box here is denoting a function f of x. I'm going to think of a function as a magic black box, or in this case a brown box, in which you put in an input and the function gives you an output. So what I mean is we take an x, we put it into the function, and out comes a value, f of x. I'm going to have my student Victor, who's here with me today, help me out. Victor, say hi to everyone. Victor, what number would you like to put into the function first? Let's input the number 1. So we put 1 into the function, and out comes the number 2. So f of 1 equals 2. What number would you like to try next? 3. Let's try f of 3. We put 3 into our function, and out comes the value of 8. f of 3 equals 8. Let's try another one. How about 6? We plug in f of 6, we put it into the function, and out comes the value of 5. f of 6 equals 5. Let's do one more. We're going to plug in a half. We plug in half is my input into my function, and out comes my value of 7. f of a half equals 7. Let's try one more. What would you like to try next? Panda. Oh well, let's give it a try. f of panda, we put panda into the function, and out comes tiger. f of panda equals tiger. This is my function f of x. Let's go ahead and look at some of its properties. So you just saw my function box, f of x. Notice I put in several numbers. I put in 1, 3, 6 and a half. Those are the numbers Victor gave me. And out came the numbers 2, 8, 5, and 7. Let's ignore the panda turning into a tiger for right now. We can denote these values in a table, as you see on the graph, and we can also depict it as a graph where we have the x and y axis, and we denote each value of the function as a point with the x input and the y output. Let's look at a new function, g of x. Let's try a couple inputs to see what this new function does. Victor, let's put in 1. When we put in 1 to the function, the outcome is 1. Let's try another one. We plug in 2, we get 2. Let's try 3. Let's put in 3 into my function. Out comes the value of 3. I think I see a pattern here. We put in 7 into our function. What comes out? We get another 7. One more. Plug in 8. Have you figured out what's happening yet? We plug in 8. Out comes the value of 8. Let's take a look at this function. You notice it seemed to have a pretty strong pattern. Whenever I put in a 1, I got out a 1. I put in a 2, I got out a 2. Every number that I input seemed to be the same number I got as an output. You might guess that if I put in 100 to my function, I'd get 100 out. Over here we see we've got a table of our function values that we tried. We also have plotted the x and y values, the inputs and the outputs, on a Cartesian coordinate system, or the xy plane. Let's think about this function. Do we know which function this one is? Well, you probably guessed it. This is the function g of x equals x. For every x value I put in, I get the same x value out of the function, and I can connect those dots from my trials with a straight line. Just having 5 data points isn't enough to determine what the function actually is, but based on this, my best guess is this is probably the function g of x equals x. Let's look at a new function, h of x. When we're looking at h of x this time, let's pay particularly close attention to figure out if h of x is a function. Remember, a function is something that for every input, you get a correspondingly unique output, one and only one output for each input. Let's give this a try. Victor, you got an input for me? Let's try 1. H of 1 gives me a value of, let's see, 3. H of 1 is 3. Let's try another one. 2. H of 2 is 3 again. Let's try another. Plug in 3. H of 3 is, let's see, 3. H of 3 is 3. Let's plug in 7 now. H of 7 is 3. I think you're seeing a pattern here. Let's try one more just to be sure. H of 8, when we plug in 8, what do we get? Well, I'm not sure this time. 3. H of 8 is 3. This function seems to have, for every input, we get a value of 3. Does this contradict the definition of function? What do you think? It doesn't contradict it. It actually is a function. It kind of seems like it's not. Let's see why. The function we just saw, h of x, gave us an output of 3 no matter what the input was. If we graph this function, you notice all of the points lie in a horizontal line. A lot of students get confused and think that this isn't a function because all the values were the same. However, notice that we did get this. For each input, there was only one output. It wasn't like I put in a number and got 2 different outputs. So this actually is a function. The function value that it is h of x equals 3. No matter what number I input, the output is always 3, and the graph of this function looks like a horizontal line. Let's try one last function, r of t. Notice that my variable in this case for the input is t. Normally we use x, but there's nothing special about x. We just tend to use that a lot in mathematics, but the variable could be any letter. In this case, our function is r is a function of t. Let's go ahead and try out some values. Victor, you got an input for me? Let's try 2. r of 2 is pi. Let's try another one. 0. Let's plug in 0. r of 0 is scissors. Let's try one more. Let's put in a peep. r of a chicken is, let's see here, what do we got? A bunny. Let's try another one. Okay, let's input red. r of red is blue. So we put in some values to our function r of t. Victor, up till now, does it look like this is a function? Sure seems like it's a function so far, but to test this, let's try putting in one of the inputs we've already tried. Can I have a chick again? Last time when I put a chick in, I got a bunny. Let's see what happens this time. I'll put my chick into my function, and out comes a sock. One time I put in a chick and I got a bunny. Another time I got a dirty sock. This is an example of something that is not a function. Do you think it's a function now, Victor? No. This isn't a function because sometimes you put in a chicken, you got a bunny. Other times you got a sock. In the example we just did, the function r of t was looking pretty good to start out with. For each number I put in, or each object I put in, I got a unique output. But then, when I tried chick again, one time I got bunny, and the second time I got sock. So for this input, I got 2 different outputs. Let's remind ourselves what the definition of function was. A function is a correspondence between 2 sets of elements such that for each element in the first set, there corresponds one and only one element of the second set. The example we just tried violates this definition because sometimes for chick I got a bunny, sometimes I got a sock. You shouldn't think that these things that aren't functions are very exotic, strange things that you would never encounter. A lot of the things we deal with in mathematics aren't functions. For example, circles are not typically functions because it's possible to have a circle where you put in one x value and you get 2 different y values. For example, a circle with radius 1, when you plug in x, you might get y equals 1, or you might get y equals -1. So it's not a function. Let's go ahead and talk about the domain and range of these objects that we've been dealing with, these functions. Back to our function. The domain is a set of things we're allowed to put into the function. What are the allowable inputs to our function? So I input a domain, and the things I get out of the function, the outputs, are my range. So the domain is the inputs, the range is the outputs. When looking for a domain, you usually want to think about what is allowed to be put into the function. Usual things we look for is, remember, you're never allowed to divide by 0, so we look for places where there's division by 0. We also know that you're not allowed to take the square root of a negative, so we look for places where you might be taking the square root of a negative. Those are 2 common examples of things we look for when finding the domain of a function. The range, we usually look to see what are the allowable outputs for the given domain. In this unit on functions and graphs, you will learn to identify functions, that is, see whether it satisfies the rule that for each input there's one and only one output. You'll learn to evaluate functions. That's what we were doing with our box, but you'll be doing that symbolically and with graphs. For a given input, figuring out what the output value is. You'll be learning to find the domain and range of functions. What is the set of allowable inputs, and what are the corresponding outputs? You'll also graph and find equations for linear functions. Linear functions are a special type of function that are super important in mathematics and come up quite a lot. Linear equations are equations of the form f of x equals mx plus b. The graph of these functions are straight lines with various slopes m. M represents the slope, or how steep this linear function is. The domain and range for the linear functions are unique in that they're both all real numbers. You can put any real number in, you can get any real number out. You'll also learn how to find the line, the slope of the line, and the x and y intercepts of a given line in order to help you graph it. Other things you'll learn in this unit are to perform transformations of graphs. Transformations of graphs basically mean you'll start with a standard graph that you know. For example, the parabola graph is a common one you might already know. And you'll learn what happens when you do slight changes to it. For example, adding 2 to the parabola, x squared, moves the graph up 2 units. Subtracting 3, x minus 3, and then squaring it causes the graph to move 3 units to the side. We could also do things like stretch or expand our graph. For example, we have the graph here of 5x squared, which causes a vertical stretching of my graph. Another thing I could do is multiply by a negative number. If I look at f of x equals negative x squared, it causes my graph to reflect or give the mirror image over the x-axis. You'll be learning about these sorts of transformations in the coming unit. When talking about combinations of functions, you'll learn to do things like f plus g, f minus g, f times g, f divided by g, and something called composition. F composed with g means we do g of x first, and then we do f to the resulting output from g. It's basically like having 2 of my machine function boxes in a row, where one feeds into the other, and then you get an output after you've done both systems together. The last thing you'll be learning about is determining if a function is invertible and finding its inverse. Inverse functions basically let you go forwards and backwards to recover the original input. There's a lot of applications of functions. Basically, the applications of functions are everything around you. For example, if you're running, you might have a function of the amount of calories you burn as a function of the distance you've run. When you put your money in a bank, in an investment, you usually have a function of the amount of money you make as a function of the interest rate, or the amount of money you make as a function of the time you've left that investment in the bank. Well, have fun exploring functions. Thank you, and I'll see you next time.
Let's look at relations versus functions. For example, for each relation below, decide whether or not it is a function. Now, a relation is a relationship between sets of information, but with a specific order. In other words, it is a set of ordered pairs. Each pair has a first component and a second component. And the set of first components is what we call the domain of the relation. And the set of second components is what we call the range of the relation. Each value of the first component is sent to an element of the second component. That is, we can write this first relation here as the following set. So the value 4 in the first component gets sent to the value f in the second component. And 9 gets sent to f. -3 gets sent to w. 2 gets sent to f. And 7 gets sent to f. And the second relation is a set. Tree gets sent to 9. Paper gets sent to 1. Moon gets sent to -6. And cloud gets sent to -4. And finally, relation 3. Is a set -9 gets sent to -9. 9 gets sent to 9. -6 gets sent to -9. 7 gets sent to -9. And -5 gets sent to -9. But also, -5 gets sent to 9. Now, a function is a special type of a relation. In a function, no two ordered pairs have the same first component. That is, for each first component in the domain, there is exactly one second component. So let's write that here. In order for a relation to be a function, for each first component, in the domain, there is exactly one second component. So now looking at our relations here, both relation 1 and relation 2, yes, are functions, but relation 3 is not. Because -5 gets sent to two different second components here, -9 and 9, as shown here in this figure. So -5 is mapped to -9 as well as 9. So no, this is not a function. Yes, this is a function. And yes, this is a function. All right, and this is how we decide whether a relation is a function. Thank you, and we'll see you next time. Let's look at functions and the vertical line test. Let's determine whether the following equation defines y as a function of x. Now remember that in an equation of two variables, if each value of the independent variable, there corresponds exactly one value of the dependent variable, then the equation defines a function. In other words, if each allowed value of x maps to exactly one value of y, then the equation defines y as a function of x. So solving our equation for y gives us 3y is equal to 2x minus 6, and then dividing both sides by 3 gives us that y is equal to 2/3 x minus 6 divided by 3, or 2. Now for each input of the independent variable x, there will be exactly one unique output y. So yes, this equation does define y as a function of x. So yes, y is a function of x. Now another way to reach this conclusion is to think of the graph. The graph of this equation, y is equal to 2/3 x minus 2, is this line here, isn't it? It has y-intercept at -2 and a slope of 2/3, which means we go up 2 and over 3. Now there's something called the vertical line test. which gives us a way to determine whether an equation defines y as a function of x by looking at its graph. And what it says is that an equation defines a function if each vertical line in the rectangular coordinate system passes through at most one point on the graph. And so looking at our graph here, any vertical line that we pass through this graph will intersect the graph at only one point. So it represents a function. And the reason this is true, why this works, is because what is the equation of a vertical line? It is x equal to something. And so if it hits that graph in only one point, that means for that x value, there's only one output y. All right, let's look at another example. Let's determine whether this equation defines y as a function of x. Again, let's solve for y. So we have y squared is equal to 9 minus x squared. Or y is equal to plus or minus the square root of 9 minus x squared. So no, this equation does not define y as a function of x. Because for whatever allowed value of x we put in here, we have two outputs, the positive as well as the negative. And what does the graph of this look like? If we add y squared to both sides, we get x squared plus y squared is equal to 9. Isn't that just a circle centered at the origin with radius 3? So this is 3. And if we pass a vertical line through this graph, it's going to intersect it in two places, isn't it? Therefore, by the vertical line test, this equation does not define y as a function of x. And this vertical line that was just drawn here is at x equal to 2. And if we plug x equal to 2 in here, what do we get? We have y is equal to plus or minus the square root of 9 minus 2 squared, or 9 minus 4, which is 5. Which means that for x equal to 2, there's two different outputs, so it is not a function. All right, and this is how we determine whether an equation represents a function. Thank you, and we'll see you next time. Let's look at finding the domain of a function. For example, let's find the domain of this function and write our answer in interval notation. Now, the domain of this function is the set of all x that make square root 4 minus x divided by x minus 1 a real number. Now, the first thing to notice here is this x minus 1 in the denominator. X minus 1 cannot equal 0. Otherwise, we'd be dividing by 0, and this ratio would not be a real number, which means x cannot equal 1. Therefore, we'll have to exclude x equal 1 from the domain. Now, what else do we notice about this function? The numerator here contains a square root. And a square root will be a real number as long as what's under the square root, namely 4 minus x, is greater than or equal to 0, or x has to be less than or equal to 4. Looking on the number line, let's say this is 4, and this is 1. X equal to 1 has to be excluded from our domain. So let's put an open circle here at 1. But any other x less than or equal to 4 will be in the domain. That is, we'll put a closed circle at 4 less than we go to the left, but we cannot include 1. So this would be our domain graphed here. However, we're asked to put our answer in interval notation. Therefore, our answer would be negative infinity up to 1, open parenthesis at 1 because we cannot include 1, union, again open parenthesis at 1, up to 4, close bracket at 4 because we can include 4. And this is how we find the domain of a function. We look for the set of all x values that make f of x a real number. Thank you, and we'll see you next time. Let's look at evaluating functions. For example, if f and g are defined as follows, let's find all 4 of these. F of negative 2, f of x squared, g of 3, and g of x plus 1. Now we're given that f of x is equal to 2 minus 3x plus x squared. So when we are evaluating this function at any input, we put the input here and here. Let's write that out. So we have f of any input is equal to 2 minus 3 times that input plus that input squared. Now what about the function g? We're given that g of x is equal to x plus 4 divided by 2x minus 1. So when we are evaluating g at any input, we put the input here as well as here. So let's write that out as well. Namely, g of any input is equal to that input plus 4 divided by 2 times that input and then minus 1. All right, so we're first asked to find f of negative 2. Which means that this negative 2 here is our input. Which means we put it over here and here. That is, this is equal to 2 minus 3 times this input, or negative 2, plus that input, or negative 2, quantity squared, which is equal to 2 plus 6 plus 4, or 12, which would be our answer to the first part. All right, what about f of x squared? Now, don't let it confuse you that this is a variable now, and moreover that it's the same variable x that we see up here in the definition of our function. Remember, whatever's inside these parentheses is our input, which means we need to put it in over here and here. That is, this is equal to 2 minus 3 times that input, or times x squared, plus that input, or x squared, quantity squared, which is equal to 2 minus 3x squared plus x to the 4th, which would be our answer to the second part. All right, what about this third one here, g of 3? Now we'll start working with our function g. So 3 then is going to be our input. Which means looking over here on the right, we're going to plug it in here, and we're going to plug it in here. That is, this is equal to the input, which is 3, plus 4, divided by 2 times the input, or 2 times 3, minus 1, which is equal to 7 divided by 6 minus 1, which is 5, which would be our answer to the third part. And finally, what about g of x plus 1? Again, don't let it confuse you that you see a variable here inside the parentheses. And moreover, that it's the same variable as we have up here in the definition of g. Remember, whatever is inside the parentheses is our input. So this whole quantity, x plus 1, is our input, which means over here on the right, we're going to plug it in here and here. Namely, this is equal to the input, or x plus 1, plus 4, divided by 2 times the input, or 2 times x plus 1, and then minus 1, which is equal to x plus 5, divided by, now distributing our 2, we have 2x plus 2 minus 1, which is equal to x plus 5 divided by 2x plus 1, which would be our last answer. And this is how we evaluate functions. Whatever we see inside the parentheses, we put in as our input. Thank you, and we'll see you next time. Let's look at finding the domain and range of a function from its graph. For example, here's the graph of f. Let's find its domain and range. Now remember that the graph of f is the set of all points x, y, such that y is equal to f of x. Now the domain is the set of all x coordinates of points on the graph. And the range is the set of all y coordinates of points on the graph. So looking at our graph, what is the set of all possible x coordinates of points on the graph? It's this interval here, isn't it? Think of projecting the graph onto the x-axis and we'll get this interval. Notice that if we go further to the right here, there's no point on the graph with these x-coordinates. Or if we go further to the left over here, there's no point on the graph with these x-coordinates either. So therefore our domain is this interval. -3 up to 3. And notice that this is an open parenthesis here because this point over here is open. In other words, x equal to 3 is not the x-coordinate of any point on that graph because of that open circle. Now what about the range? What is the set of all possible y-coordinates of points on the graph? Let's look at our graph again. The set of all possible y-coordinates of points on the graph is this interval here. Think of projecting the graph onto the y-axis. So the range then is this interval. -4 up to 5. Now, some students think that we should not include 5 in our range because of this open circle over here. However, if you look over here, there is a point on the graph with the y-coordinate equal to 5, which is why we include 5 here. Therefore, these would be our answers here. All right, let's look at another example. Here's the graph of G. Let's find its domain and range. Again, the graph is the set of all ordered pairs x, y, such that y is equal to g of x. And again, the domain is the set of all possible x-coordinates of points on the graph. And the range is the set of all y-coordinates of points on the graph. Okay, so what is the domain? What is the set of all possible x-coordinates of points on our graph? So here's our graph. Again, think of projecting the graph onto the x-axis. So the domain then would be this interval here together with this interval here. That is, the domain is equal to -2 to -1 union 0 up to 4. Notice a few things here. Again, because of this open circle here, this is open. X equal to 4 is not the x-coordinate of any point on our graph. And also notice here there's this gap between -1 and 0 because those x values are not the x-coordinate of any point on our graph. Neither are the x values to the right of 4 or the x values to the left of -2. So this is our domain. Now, what about the range? Again, looking at our graph, remember the range is the set of all possible y-coordinates of points on our graph. Again, thinking of projecting this graph onto the y-axis will give us this interval here. That is, the range is equal to the interval from 1 up to 5. And we're not including 5 here because 5 is not the y-coordinate of any point on our graph. Now, sometimes students get confused and they won't include this bottom portion here because they're only looking at this piece of the graph. But aren't these y values here y-coordinates for points over here? So they are y-coordinates for points on our graph. So we include the entire interval from 1 up to 5. So this is our range here. And this is how we find the domain and range of a function given its graph. Thank you, and we'll see you next time. Let's look at the domain of a function and the intercepts of its graph. For example, let's find the domain of f and any x or y intercepts of its graph. Let's start with the domain. What's under the square root, namely this x plus 4, has to be greater than or equal to 0. Or subtracting 4 from both sides gives us that x has to be greater than or equal to negative 4, which is the domain of f. So let's write that in interval notation. Domain of f is equal to, x has to be greater than or equal to negative 4, so close bracket at negative 4 up to infinity, which would be the domain. Now what about the intercepts of its graph? Well, let's let y equal f of x. In other words, y is equal to the square root of x plus 4 minus 1. Let's start by determining whether the graph of f has any x-intercepts. Well, an x-intercept, if it exists, is the x-coordinate of a point where the graph of f intersects the x-axis. And on the x-axis, y is equal to 0, isn't it? Therefore, if we set y equal to 0 in our equation, we can see if there's any x-intercepts. Doing this gives us 0 is equal to the square root of x plus 4 minus 1. And adding 1 to both sides, we get 1 is equal to the square root of x plus 4. And then squaring both sides, we have 1 squared is equal to the square root of x plus 4 squared. Or 1 is equal to x plus 4. And then subtracting 4 from both sides gives us x is equal to negative 3. So the graph of f does have an x-intercept. All right, what about the y-intercepts? A y-intercept, if it exists, is the y-coordinate of a point where the graph of f intersects the y-axis. And on the y-axis, what does x equal? It equals 0, doesn't it? So we set x equal to 0 in our equation here and solve for y. So we have y is equal to the square root of 0 plus 4 minus 1. Or y is equal to 2 minus 1, or y is equal to 1, which is the y-intercept of the graph of this function. Now, can the graph of a function have more than one x-intercept, or more than one y-intercept? There can be more than one x-intercept, but there cannot be more than one y-intercept. Because if this is indeed a function, then when x is equal to 0, there cannot be two different outputs for y. So therefore, there can be at most one y-intercept. All right, let's see another example. Again, let's find the domain of this function f and any x or y intercepts of its graph. We'll begin with the domain again. The only issue with this function is if the denominator were equal to 0. So when does x squared minus 4 equal 0? This means that x squared is equal to 4, or x is equal to plus or minus 2. So we must exclude these values. That is, the domain of f, again written in interval notation, is negative infinity up to negative 2, open parenthesis, because we cannot include negative 2, union, again, open parenthesis at negative 2, up to 2, again, open parenthesis, union, open parenthesis, 2 up to infinity. And now, to find the intercepts, again, we'll let y equal f of x. In other words, we have y is equal to x squared minus 9 divided by x squared minus 4. So let's start with the x-intercepts, which we can find if we set y equal to 0, which means we have 0 is equal to x squared minus 9 divided by x squared minus 4. Now, a fraction is equal to 0 when the numerator is equal to 0 and the denominator is not. So where is our numerator? X squared minus 9 equal to 0. This happens when x squared is equal to 9, or x is equal to plus or minus 3. And neither of these values make our denominator here 0. So they're both x-intercepts. And let's see if the graph of f has a y-intercept. Which we can find by setting x equal to 0. In other words, we have y is equal to 0 squared minus 9 divided by 0 squared minus 4, or y is equal to 9/4. So the graph does have a y-intercept. And this is how we find the domain of a function and any x or y-intercepts of its graph. Thank you, and we'll see you next time. Let's look at computing the difference quotient. For example, let's compute the difference quotient for this function f of x equals 2x squared minus 4x plus 3. This expression here is called the difference quotient and is used often in calculus. So let's compute it for this function here. And we'll begin by computing f of x plus h. So f of x plus h is equal to 2 times x plus h quantity squared minus 4 times x plus h and then plus 3. All we're doing is we're plugging in x plus h wherever we see an x here. And this is equal to, squaring this out, 2 times x squared plus 2xh plus h squared, and then we still have the minus 4 times x plus h, and then plus 3. Now distributing, we get 2x squared plus 4xh plus 2h squared, and then minus 4x minus 4h plus 3. So let's plug that in here and f of x in here to find this difference quotient. Namely, f of x plus h minus f of x all divided by h is equal to this 2x squared plus 4xh plus 2h squared minus 4x minus 4h plus 3 minus f of x, which is this 2x squared, minus 4x plus 3. All divided by h, which is equal to 2x squared plus 4xh plus 2h squared minus 4x minus 4h plus 3. And be careful here, we have to distribute now the negative through to each term in f of x. So it's minus 2x squared plus 4x minus 3, all divided by h. Now combining like terms, this 2x squared minus 2x squared is 0, they'll cancel, as well as this minus 4x and positive 4x. And same with the plus 3 minus 3. Now the remaining 3 terms here in the numerator all have an h in them, so we can factor that out. In other words, this is equal to h times 4x plus 2h minus 4, all divided by h. And because h is not equal to 0, we can cancel the h's. And we're left with our answer of 4x plus 2h minus 4. And this is how we find a difference quotient for a function. Thank you, and we'll see you next time. Let's look at piecewise defined functions. A piecewise defined function is a function that is defined in pieces, or according to different rules depending upon the input. So for example, this would be considered a piecewise defined function. So what does this mean? It means that f is defined by different rules according to what x is. That is, if x does not equal -1, then f of x is equal to -3. Otherwise, if x does equal -1, then f of x is equal to -4. So there are different rules that define f depending upon the input x. So let's compute f of -5, f of -1, and f of 2, and then we'll graph f. Let's start with f of -5. Since -5 does not equal -1, we'll be using this first piece here. That is, f of -5 is equal to -3. All right, and what about f of -1? We'll be using the second piece down here, because the input is -1, which means f is equal to -4. And finally, what about f of 2? Well, since 2 is not equal to -1, we'll be using this first piece. That is, f of 2 is equal to -3. So it remains for us now to graph f. So let's say that this is the y-axis, and this is the x-axis. And let's say this is -1, and this is -3, and this is -4. As long as x does not equal -1, f of x or y is equal to -3. And y equal to -3 is the equation of this horizontal line here. However, when x is equal to -1, we have an open circle, because when x is equal to -1, the y value is -4. So this would be the graph of f. Let's look at another example. Let g be defined by this piecewise function. We're going to find g of -5, g of -2, and g of 2, and then we'll graph f. So let's start with computing g of -5. Now, which of these three intervals does -5 lie in? It lies in this first interval, doesn't it? Because -5 is less than -3. Therefore, we're going to use the first rule, or the first piece, to compute this. So g of -5 is equal to -4. All right, what about g of -2? Well, which piece or rule are we going to use to compute this? Well, -2 lies in the second interval, doesn't it? So we'll use the second rule. That is, g of -2 is equal to -2 minus 1, which is equal to -3. And finally, what about g of 2? Which of the three intervals does 2 lie in? And we have to be careful here, because we see a 2 here and we see a 2 here. However, the condition of equality is down in this third interval here. Therefore, we use this third piece. That is, g of 2 is equal to 3. Okay, so it still remains to graph g. So let's say this is the y-axis, and this is the x-axis, and let's say this is -3, and this is +2, and this is +3, and -4. When x is strictly less than -3, then y, or g of x, is equal to -4. Therefore, for any x less than -3, y is equal to -4. And then for any x between -3 and 2, the function is defined to be x minus 1, which is the equation of a line with y-intercept equal to -1 and slope 1. So it will look like this. And right when we get to 2, we have an open circle, because looking back over here, this is a strict inequality. But also looking back over here, we have the condition of equality at -3, which means over here we have to close this circle up. And also this will be -1 because the y-intercept is -1, and this would be 1 because the slope is 1. And then for x greater than 2, g of x is equal to 3. So we have a closed circle at 2, and then y equal 3 is the equation of a straight line. And this is how we work with piecewise defined functions. Thank you, and we'll see you next time. Let's look at intervals where a function is increasing, decreasing, or constant. For example, the graph of the function f is shown below. Let's find the intervals where f is increasing, decreasing, or constant, and then we'll find the domain and range of f, as well as any x or y intercepts of its graph. Now we have the following. A function f is said to be increasing or strictly increasing on an interval if for all a and b in that interval, where a is less than b, the y value at a, namely f of a, is less than the y value at b, namely f of b. And what does that mean about the graph of the function? Looking down here in this figure, it means that the graph of the function is rising as we look from left to right. And a function is said to be decreasing on an interval if the y value at a is larger than the y value at b, for any a less than b. And looking down here, what does that mean about the graph? It means the graph, looking left to right, is falling. And a function is said to be constant on an interval if for all a and b in that interval, the y value f of a is equal to the y value f of b. And looking at the graph will be horizontal on that interval. All right, let's start with increasing. Looking at the graph of our function here, we see that the graph is not rising on any interval. So therefore, our answer here would be none, since the graph is never rising. All right, where is f decreasing? Looking at our graph, we see that the graph is falling here as well as here, which corresponds to these intervals here and here. That is, the interval over which f is decreasing is -3 to -2, union 1 to 3. Now, what about where this function is constant? Looking at our graph here, we see that the graph is horizontal here, here, and here, which corresponds to the interval here, here, and here. Namely, -7 up to -3, union -2 up to 1, union 3 up to 5. All right, and we're also asked to find the domain and range of f as well as any x or y intercepts of its graph. So looking at our graph, we see that the domain is equal to the interval from -7 up to 5. Remember that the domain is the set of all possible x-coordinates of points on the graph. And the range is the set of possible y-coordinates of points on the graph. And looking at our graph, the y values range from 1 up to 6. And what about x and y intercepts? This graph never touches the x-axis, so there's no x-intercepts. And it crosses the y-axis right here, which is y equal to 4. So the y-intercept is y equal to 4. All right, let's look at another example. Here's the graph of f. Again, we'll determine the intervals where f is increasing, decreasing, or constant, and then we'll find the domain range as well as any x or y intercepts. Again, a function is increasing on an interval if for every a and b in that interval with a less than b, then the y value f of a is less than the y value f of b, and the graph will be rising on that interval. And the function is said to be decreasing on the interval. It's the other way around. The y value at a is greater than the y value at b, and the graph is falling. And the function is said to be constant on an interval if for all values in that interval, f of a is equal to f of b, and the graph is horizontal on that interval. So where is our graph increasing? Looking at the graph, we see it's rising here, which corresponds to this interval here. Or -2 up to 3. Now what about decreasing? Looking at our graph is not falling on any interval, so this would be none. And finally, where is our function constant? Looking at our graph, we see it's horizontal here, as well as here, which corresponds to this interval, as well as this interval. That is, our function is constant from -infinity up to -2, union 3 up to infinity. Now notice that in both of these examples, we've been writing these intervals as open intervals. These terms, increasing, decreasing, and constant, are defined in terms of intervals. Not point-wise, but in terms of intervals. So we could have included any of these endpoints and our answer would be correct. But by convention, most authors state these intervals as open intervals. All right, well, it still remains to find the domain and range of f as well as any x or y intercepts of its graph. So the domain here is the set of all x coordinates of points on the graph. And looking at our graph, every x value has a corresponding point on the graph. That is, the domain is the interval from -infinity to infinity. However, with the range, we're missing this big piece here, aren't we? And because of this open circle here, there is no point on the graph that has y coordinate equal to 1. But this point is closed, which means there is a point on the graph that has y coordinate equal to 3. And in fact, every point to the right of this on the graph also has y coordinate equal to 3. But not only that, there's also no points on the graph that have y coordinate larger than 3 or less than -4. That is, our range is the interval -4 up to 1, open parentheses, union the value 3, which we can write as the interval from 3 to 3. All right, well, we see that we have both an x-intercept and a y-intercept. The x-intercept is 2, and the y-intercept is -2. All right, this is how we work with these terms, increasing, decreasing, and constant, as well as domain, range, and intercepts. Thank you, and we'll see you next time.
Let's look at graph transformations. For example, let's sketch y equal to the square root of x plus 2 plus 1 by using graph transformations. Now, there are different types of graph transformations. There are transformations that we call translations, which are rigid movements of graphs. And then there's also transformations called stretching, shrinking, and reflecting, which aren't rigid movements of graphs. And in this lesson, we're going to be looking at the translations or rigid movements of graphs. And we have the following: that if f is a function and a and b are positive real numbers, then to obtain the graph of f of x minus a, we shift the graph of f to the right a units.
And to obtain the graph of y equal f of x plus a, we shift the graph of f to the left a units. But to obtain the graph of f of x plus b, we shift the graph of f up b units. And to obtain the graph of y equal f of x minus b, we shift the graph of f down b units. So to sketch graphs using graph transformations, or these translations here, what we do is we start with what's called a base function. And looking here, we can start by sketching y equal to the square root of x. So let's say that this is the y-axis, and this is the x-axis. The square root of x looks like this, where this is the origin, 0, 0. What are some other points on this graph? Well, we know when x is equal to 1, that y will also be equal to 1, which means we know we have the point 1, 1 on our graph. Now, what other point lies on our graph? Well, we wouldn't want to put, for example, x equal to 2 in here, because then the y value would be square root of 2. So what's the next x value that we know the square root of after 1 here? Well, that would be 4, wouldn't it? Because we know that the square root of 4 is 2. So that's another point we have in our graph. So this is 4. Then this is 2 here. So this is the point 4, 2. All right, so what does this plus 2 here do under the square root to this graph? Well, looking down here, we're in the second case, aren't we? We are adding a positive number to the x value within the function, which means we're going to shift this graph to the left a units, or in this case, 2 units. So we're going to shift this graph 2 units to the left. When we do that, what's going to happen to this point here, 0, 0? The y-coordinate is not going to change, but the x-coordinate is going to have 2 subtracted from it, which means it's going to get translated to the point -2, 0. And what about this point here? 1, 1. This is going to go to 1 minus 2, 1, or -1, 1. And what about this point here? This is going to go to 4 minus 2, 2, or 2, 2. All right, so let's sketch y is equal to the square root of x plus 2. So let's say this is the y-axis, and this is the x-axis. So we just found that the origin, that point 0, 0, was moving to -2, 0. So we have that point on our graph here, -2, 0. We also found that the point 1, 1 was moving to -1, 1. So we also have that point on our graph, -1, 1. And then we found that the point 4, 2 was moving to 2, 2. So we also have that point on our graph, 2, 2. So this shape is exactly the same, it's just moved 2 units to the left. All right, and looking back up here, what does this plus 1 do to this second graph here? Well, we're in this third case down here. We are now adding a positive number to the y value here on the second graph, which means we shift this second graph upward b units, or upward 1 unit. So when we do that, what happens to this point here, -2, 0? This point, -2, 0, goes to -2, 0 plus 1, or 1. And what about this point here, -1, 1? This point, -1, 1, is going to go to -1, and then 1 plus 1, or 2. And this last point, 2, 2, is going to go to 2, and then 2 plus 1, or 3. That is, we have the following graph of y is equal to the square root of x plus 2 plus 1. So here is the y-axis, and this is the x-axis. The point -2, 0 is moving to -2, 1. So it's here, -2, 1. And the point -1, 1 is moving to -1, 2. So here is the point -1, 2. And finally, the point 2, 2 is moving to 2, 3. So here's the point 2, 3. So our graph will look like this. Notice that we're just rigidly moving to the left and then up. All right, let's look at another example. Let's sketch this graph here using graph transformations. Again, we're going to just use translations here in this lesson. So looking at our function up here, what is our base function? It is y is equal to the absolute value of x. So let's sketch this. So let's say this is the y-axis, and this is the x-axis. The absolute value looks like this. We have the point 0, 0 on our graph, as well as 1, 1, and -1, 1. So looking back up here, what does this -3 do to this graph here? Well, we're in this first case here, aren't we? We are subtracting a positive number from the x-coordinate inside the function, which means we're going to shift this graph to the right a units or 3 units. So what's going to happen to this point 0, 0? It's going to get moved to 0 plus 3, or 3, 0. In this point, what's going to happen to this point, 1, 1? It's going to move to 1 plus 3, or 4, 1. And what about this point, -1, 1? It's going to move to -1 plus 3, or 2, 1. That is, we have the following graph of y is equal to the absolute value of x minus 3. We have the y-axis here, and the x-axis. So 0, 0 is moving to 3, 0. So 1, 2, 3, 0. And 1, 1 is moving to 4, 1. So here's 4, 1. And -1, 1 is moving to 2, 1. So here is 2, 1. So this graph looks like this. All right, and finally, what does this -2 do to this second graph here? Well, we're down in this last case here, aren't we? We are subtracting a positive number from the y value, which means we're going to shift this second graph downward by b units or by 2 units. So we shift this down 2 units. When we do that, what is going to happen to the point 3, 0? This is going to go to 3 and then 0 minus 2 or -2. And what about this point, 4, 1? It's going to get shifted to 4 and then 1 minus 2 or -1. And what about this point, 2, 1? It's going to get shifted to 2 and then 1 minus 2 or -1. That is the graph we're looking for, or y is equal to absolute value x minus 3 minus 2, looks like this. So here's the y-axis, and here's the x-axis. So the point 3, 0 was moved to 3, negative 2. So we have this point here on our graph, 3, negative 2. And the point 4, 1 was moved to 4, negative 1. So we also have this point here on our graph, 4, negative 1. And the point 2, 1 was moved to 2, negative 1. So we also have this point here, 2, negative 1 on our graph. So our graph looks like this. So our graph is being transformed by rigid translations in both these examples. Thank you, and we'll see you next time. Let's look at graph transformations. For example, let's sketch y is equal to 3 minus 2 times the quantity x minus 1 squared by using graph transformations. Now, we already saw in the part 1 lesson on graph transformations what this 1 and this 3 will do to the graph. But what does this 2 and this negative do? Well, we have the following. That if c is greater than 1, to obtain the graph of y equals c times f of x, we vertically stretch the graph of f by a factor of c. If we divide by c, then we vertically shrink the graph by a factor of c. And if we multiply the x inside the function by c, then we horizontally shrink the graph of f by a factor of c. But if we divide the x by c, then it's a horizontal stretch of this graph. So these four here determine this stretching and shrinking. Whereas these last two down here determine the reflecting. And what they say is that to obtain the graph of y equal to negative f of x, we reflect the graph about the x-axis. And if we multiply the x inside the function by a negative, then we reflect the graph of f about the y-axis. So we still start with our base function, y equal to x squared. So let's say that this is the y-axis, and this is the x-axis. Y equal to x squared looks like this, where this point here is 0, 0, the origin. We also have that 1 lies on the graph, as well as negative 1, 1. All right, so remember, what does this minus 1 do inside the function? This rigidly shifts this graph 1 unit to the right, which means to each x coordinate here, we're adding 1 while leaving the y coordinate alone, which means that 0, 0 will move to 0 plus 1, or 1, 0. 1, 1 will move to 1 plus 1, which is 2, and then 1. And negative 1, 1 will move to negative 1 plus 1, which is 0, 1. Therefore, y is equal to x minus 1 quantity squared will look like this. So here's the y-axis. Here's the x-axis. So here's 1, 2, and 1. So 0, 0 moved to 1, 0, which is here. 1, 1 moved to 2, 1, which is here. And negative 1, 1 moved to 0, 1, which is here. So this graph will look like this. So this is the point 1, 0. This is the point 2, 1. And this is the point 0, 1. All right, now let's discuss what this 2 up here does to this graph. Well, we're in this first case down here, aren't we? Which means that we're going to vertically stretch this graph here by a factor of 2. Which means what? Which means for every y-coordinate that you see on the second graph, we're going to be multiplying that y-coordinate by 2. So the graph of y is equal to 2 times x minus 1 squared will look like this. Say this is the y-axis and the x-axis. This is 1, 2, and this is 1, 2. Now this point over here, 1, 0, isn't really going to move because we're multiplying the y-coordinate by 2. So we're still at 1 and then 2 times 0, which is still 1, 0. So we're here. But these other 2 points will move. This is going to move 2, 2, and then 1 times 2, which is 2. And this is also going to move to 0, and then 1 times 2, which is 2. So we have this point here and this point here on our graph. And therefore, this function will look like this. So we're vertically stretching it. All right, looking back up here to the function, now what does this negative do here? Well, looking down here, that means that we are going to reflect this graph about the x-axis. That is y equal to negative 2 times x minus 1 squared will look like this. So if this is the y-axis, and this is the x-axis, this is 1, 2, this is negative 1, negative 2. We still have the same vertex here, but now those other 2 points, 0, 2, and 2, 2, are going to be flipped down below the x-axis to 0, negative 2, and 2, negative 2. So this graph will look like this. And finally, the graph we're looking for, this y is equal to 3 minus 2 times x minus 1 squared, will be a vertical shift up 3 units of this graph. That is, it's going to look like this. So here's the y-axis. Here's the x-axis. So the point 1, 0 is going to move to 1, 3. 1, 2, 3. Because we need to add 3 to every y-coordinate. And the point 0, negative 2 is going to move to 0, positive 1. And the point 2, negative 2 is going to move to 2, 1. So it's here. So the graph we're looking for is this. All right, and this is how we work with graph transformations. Thank you, and we'll see you next time. Let's learn about odd and even functions. For example, the entire graph of 3 different functions is shown below. Let's determine whether each function is odd, even, or neither. A function is called even if f of negative x is equal to f of x for all x in the domain, and the graph of an even function is symmetric with respect to the y-axis. For example, f of x is equal to x squared is a famous example of an even function. And if you notice here that whenever x, f of x is on the graph, then negative x, f of negative x is also on the graph, where f of negative x is equal to f of x. That is, plugging in opposite x values yields the same y value. And therefore, this part of the graph is a mirror image of this part of the graph. That is, the graph is symmetric with respect to the y-axis. And a function is called odd if f of negative x is equal to negative f of x for all x in the domain. And the graph of an odd function is symmetric with respect to the origin. For example, f of x equal to x cubed is a famous example of an odd function. And notice, whenever f of x is on the graph, then so is negative x, f of negative x, but moreover, f of negative x is equal to negative f of positive x. In other words, when the x values are opposites, so are the y values. Which means that this part of the graph here is a mirror image of the part of the graph here. In other words, its graph is symmetric with respect to the origin. And so if we have the graph of the function, we can look at whether or not its graph is symmetric with respect to the y-axis, or the origin, or neither, to determine whether it's even, odd, or neither. But if we don't know the graph and only are given the equation, then we can see if plugging in opposite x values yields the same y value, or opposite y values, or neither. So in this first example here, we're given the graph of 3 different functions. So let's look at this first function here. We see that this part of the graph is a mirror image of this part of the graph. That is, its graph is symmetric with respect to the y-axis, which means it's an even function. And looking at our second function, we see that this part of the graph is a mirror image of this part of the graph. That is, it's symmetric with respect to the origin. So this is an odd function. And finally, looking at our last graph here, it's not symmetric with respect to the y-axis or the origin, is it? So therefore, this would be neither odd nor even. All right, let's look at another example. Let g of x equal x to the 4th plus 1, h of x equal x to the 5th plus x cubed, and k of x equal x to the 6th plus x to the 5th. Let's determine whether each function is odd, even, or neither. Again, we have the following definitions. However, now we're not given the graphs. We're only given the equations. So we want to see if plugging in opposite x values yields the same y value, or plugging in opposite x values yields opposite y values, or neither of these. Let's start with g. What is g of negative x? This is equal to negative x to the 4th plus 1, which is equal to x to the 4th plus 1. And isn't that g of x? And therefore, this statement over here is true for f equal to g. Therefore, g is an even function. That is, plugging in opposite x values gave us the same y value. All right, what about h? What is h of negative x? This is equal to negative x to the 5th plus negative x cubed, which is equal to negative x to the 5th minus x cubed. And then we can factor out a negative 1, so this is negative x to the 5th plus x cubed. And isn't what's inside the parentheses here just h of x? So this is equal to negative h of x. Therefore, this second statement over here is true for f equal to h, which means that h is an odd function. That is, plugging in opposite x values yielded opposite y values. And finally, what about k of x? What is k of negative x? This is equal to negative x to the 6th plus negative x to the 5th, which is equal to x to the 6th minus x to the 5th, which is not equal to k of x. So k is not an even function, but it's also not equal to negative k of x, which means k is not odd either. And therefore, k is neither odd nor even. All right, and this is how we work with odd and even functions. Thank you, and we'll see you next time. Let's work with the equation of a quadratic function. For example, let's find the equation of the quadratic function whose graph passes through the point -2, -1, and has vertex at -1, -3. And then we'll put our answer in standard form. Now we have the following vertex form for the equation of a quadratic function. F of x is equal to a times x minus h quantity squared plus k, where hk is the vertex. So here we're given that the vertex is at -1, -3, which means h is equal to -1 and k is equal to -3, which we can plug into this vertex form here, which gives us that f of x is equal to a times x minus a -1 quantity squared plus -3, or f of x is equal to a times x plus 1 squared minus 3. Now it still remains to find a here, but we can use the fact that this point up here, -2, -1, lies on our graph in order to help us find a. Because if -2, -1 lies on the graph, that means that f of -2 is equal to -1. So we can plug in x equal to -2 and f of x equal to -1 in our equation here, and we'll be able to find a. Namely, -1 is equal to a times -2 plus 1 quantity squared minus 3, or -1 is equal to a times -1 squared minus 3, which means that -1 is equal to a minus 3, or a is equal to 2. And so plugging this value of a into our equation here gives us that f of x is equal to 2 times x plus 1 quantity squared minus 3. Now this is our equation. However, looking back up here, we're asked to write our answer in standard form, which we can do by squaring this out. Namely, f of x is equal to 2 times x squared plus 2x plus 1, and then minus 3. And now distributing the 2, we get f of x is equal to 2x squared plus 4x plus 2 minus 3, or f of x is equal to 2x squared plus 4x minus 1, which is the equation we're looking for in standard form. And this is how we find the equation of a quadratic function given information about its graph. Thank you, and we'll see you next time. Let's learn how to convert a quadratic function from standard to vertex form. For example, let's convert this function here, f of x equal x squared plus 2x minus 2, to the vertex form, f of x is equal to a times x minus h squared plus k, and then we'll give the vertex of its graph. Now our function here is written in standard form, and in order to convert a quadratic function written in standard form into this vertex form here, we complete the square. So we're starting with f of x is equal to x squared plus 2x minus 2. And then the first step in completing the square is to make sure that the coefficient of this square term is 1, which it is here. And then we take 1/2 the coefficient of x, which in our case is 2. This gives us 1. And then we square this. So we have 1 squared is equal to 1. And then we add and subtract this number. That is, we have f of x is equal to x squared plus 2x plus 1 minus 1, and then we still have the minus 2. Now these first three terms will combine to give us a perfect square, namely x plus 1 squared. And then we have minus 1 minus 2, which is minus 3. And so we've written our function in vertex form. And when we write a quadratic function in this vertex form, then hk is the vertex of its graph. Looking here, we have x plus 1, which we can think of as x minus a negative 1. Therefore, our h is equal to negative 1, and our k is equal to negative 3. So the vertex then is the point negative 1, negative 3. Let's see another example. Let f of x equal negative 3x squared plus 12x minus 11. Again, we're going to convert this to vertex form and then give the vertex of its graph. Again, we'll begin in the same way by completing the square. So we have f of x is equal to negative 3x squared plus 12x minus 11. But now we notice that the coefficient of the square term is not equal to 1. And when completing the square, what we need to do then in this case is factor that number out of both of these two x terms here. That is, we have f of x is equal to negative 3 times x squared and then minus 4x, because negative 3 times negative 4x is positive 12x. And then let's leave a little bit of room here. And then we still have the minus 11. And then we take 1/2 the coefficient of x, which is negative 4, which gives us negative 2. And then we square this. So negative 2 squared, which is 4. And then we add and subtract that number within the parentheses here. So plus 4 minus 4. Again, these first three terms here will form a perfect square. However, we need to get this -4 out of the parentheses here. But in order to do that, we need to multiply it by this -3. That is, we have the following. F of x is equal to, we have -3 times the first three terms, and then plus -3 times -4. And then we still have the -11. That is, we just distribute the -3 to the first three terms and then the last term. All right, and this gives us that f of x is equal to -3 times the quantity x minus 2 squared, and then we have +12 minus 11 is +1. And our equation now is in vertex form. And again, comparing it to this form, we see that h is equal to 2 and k is equal to 1. Which means our vertex is at 2, 1. All right, this is how we convert a quadratic function from standard form to vertex form. Thank you, and we'll see you next time. Let's learn how to graph a parabola. For example, let's sketch the graph of this quadratic function here. Well, the graph of a quadratic function is what we call a parabola. And an important point on a parabola is called the vertex. It is the point where the parabola turns around. So this would be called the vertex here. Or this would be considered the vertex. And the vertex is also the only point on the parabola that lies on what we call the axis of symmetry. This is the line about which the parabola is symmetric. That is, the graph is a mirror image on either side of this axis of symmetry. Now, in general, we can graph a parabola by plotting its vertex and a few points on either side of it. But how do we find the vertex? Well, we have the following vertex form for the equation of a quadratic function. F of x is equal to a times x minus h squared plus k, where hk is the vertex. And if a is greater than 0, then the parabola will open upward like this second figure here. And if a is less than 0, then the parabola will open downward like the first figure. But how do we get a quadratic function that's in standard form like ours here into vertex form? Well, we complete the square. So let's do that. We have f of x is equal to x squared minus 8x plus 15. Now remember that the first step in completing the square is to make sure that the coefficient of the square term is 1, which it is here. And then we take 1/2 the coefficient of x, which in this case is -8, which gives us -4. And then we square this number. So -4 squared is 16. And then we add and subtract this number. That is, this is equal to x squared minus 8x plus 16 minus 16, and then we still have the plus 15. Now these first three terms will form a perfect square, namely x minus 4 quantity squared. And then negative 16 plus 15 is negative 1. And so we've put our function into vertex form. So we have f of x is equal to x minus 4 squared minus 1. And therefore our a is equal to 1, our h is equal to 4, and our k is equal to negative 1. And since a here is greater than 0, our parabola will be opening upward, and our vertex is at 4, negative 1. So let's plot our vertex. Let's say that this is the y-axis, and this is the x-axis. And let's say that this is 1, 2, 3, 4, and that this is negative 1. Then our vertex is here at 4, negative 1. Now let's find some other points on our parabola. So x and y. When x is equal to 2, for example, we can plug that value into this form here, and we get that y is equal to what? 2 minus 4 is negative 2. Negative 2 squared is 4, and 4 minus 1 is 3. So when x is 2, y will be 3. What about when x is 3? We get 3 minus 4, which is negative 1, quantity squared, which is 1, and then 1 minus 1 is 0. So when x is 3, y will be 0. And when x is equal to 5, we have 5 minus 4 is 1, 1 squared is 1, and 1 minus 1 is 0. And then when x is equal to 6, we have 6 minus 4, which is 2. 2 squared is 4, and 4 minus 1 is 3. So let's plot these points. So this is 1, 2, 3. So 2, 3 will be here. 3, 0 will be here. 5, 0 will be here. And 6, 3 will be here. And our parabola will look like this. So this is the sketch that we're looking for. However, let's notice a few things. Let's draw our line of symmetry here. That is, x is equal to 4. And doing this, we can see that this graph is symmetric about that axis, or the mirror image on either side of it. And so looking back over here in the table, we really only needed to determine these 2 points here. That is this point over here on the graph, 2, 3, and this point here, 3, 0. Because we get the other 2 by symmetry, don't we? 5, 0, and 6, 3. So using this axis of symmetry is very useful when sketching parabolas. Thank you, and we'll see you next time. Let's look at graphing a parabola. For example, let's sketch the graph of this quadratic function f of x is equal to negative 3x squared plus 18x minus 22, and then we'll find the maximum or minimum value of f, as well as its domain and range, and the intervals where it's increasing or decreasing. Now to sketch the graph of a quadratic function or a parabola, we plot the vertex and a few points on either side of it. Our quadratic function here is written in standard form, and what we need to do is convert it to vertex form. That is, f of x is equal to a times x minus h squared plus k, where hk here is the vertex. And the way we do that is by completing the square. So we have f of x is equal to negative 3x squared plus 18x minus 22. And now the first step in completing the square is to make sure that the coefficient of the square term is 1. And right now it's -3. So what we'll do first is factor in -3 out of these first two terms. That is, this is equal to -3 times x squared minus 6x. And let's leave a little bit of room here, and then we still have the -22. And now the next step in completing the square is we take 1/2 of the coefficient of x, which in this case is -6, which gives us -3, and then we square this. So we have -3 squared, which is equal to 9, and then we add and subtract that within the parentheses here. That is, we have +9 minus 9. And now these first three terms will form a perfect square, but we'll need to get this -9 out of the parentheses. But remember, we have to multiply by this -3. That is, f of x is equal to -3 times x minus 3 quantity squared, and then -3 times -9 is +27, and then we still have -22. Or f of x is equal to -3 times x minus 3 squared plus 5. And now comparing this to our vertex form over here on the left, we see that a is equal to -3, h is equal to 3, and k is equal to 5. And since a is less than 0, our parabola will be opening downward, and our vertex is at 3, 5. So let's plot the vertex. Let's say that this is the y-axis, and this is the x-axis. So we have 1, 2, 3, and then 1, 2, 3, 4, 5. So the vertex is here at 3, 5. And when finding other points, we're going to use the fact that the parabola will be symmetric about this axis of symmetry, namely x is equal to 3. Namely, if we choose x values to the left of 3, like 1 and 2, for example, that's going to give us corresponding values to the right of 3. So let's compute what y is equal to when x is equal to 1, which we can do by plugging in x equal to 1 down here in our vertex form of our function. So when we do that, we plug 1 in here. We have 1 minus 3, which is -2. -2 squared is 4. 4 times -3 is -12, and -12 plus 5 is -7. And when we plug in x is equal to 2, we have 2 minus 3, which is -1. -1 squared is 1. 1 times -3 is -3, plus 5 is 2. So let's plot 1, -7. So this is -1, -2, -3, -4, -5, -6, -7. So 1, -7 will be here. And 2, 2 will be up here. And now, because of symmetry, we know that 4, 2 also has to lie on our graph, as well as 5, -7. So our parabola will look like this. So it's very helpful to use this axis of symmetry to get the other points. That is, by knowing this point 2, 2 lies on our graph, we can conclude that 4, 2 does as well. And that we knew this point 1, -7 lied on our graph, then we can conclude that 5, -7 does as well. And we'll just darken in the vertex here too. So here's the graph of our quadratic function or our parabola, but we're still asked to find the maximum or minimum values of f, its domain and range, and intervals of increase or decrease. Now, because this parabola is opening downward, it will have a maximum, not a minimum, and the maximum will occur here at the vertex. That is, the maximum value of our function is the y-coordinate of that vertex, or 5. It occurs at x equal to 3, but the actual maximum value of the function is the y-coordinate, or 5. And the domain is all real numbers. And the range is from that vertex down, or the interval from -infinity up to 5. And we see that to the left of that vertex, the graph is rising, and to the right it's falling, which means that the function is increasing on the interval from -infinity up to 3, and it's decreasing from 3 to infinity. And remember that increasing and decreasing are defined on an interval, not pointwise, but in terms of intervals. So we could have included 3 on either of these intervals, and we would have been correct. All right, and this is how we work with the graph of a parabola. Thank you, and we'll see you next time. Let's look at a word problem in which we'll find the maximum or minimum of a quadratic function. A ball is thrown vertically upward. After t seconds, its height h in feet is given by this function here. H of t is equal to 64t minus 16t squared. And we're going to find how long it's going to take for this ball to reach its maximum height. Well, the ball's height here, h of t, is a quadratic function whose graph is a parabola, and sets the coefficient of the square term, namely -16, is less than 0, this parabola will be opening downward, which means that the ball will reach its maximum height at the vertex of this parabola. So to find the time that the ball will reach its maximum height, we need to find the t value of the vertex. That is, we need to find this value here for which this ball reaches a maximum. Now, there are a few different ways to find this vertex. We can either complete the square and put the equation in vertex form. But since we're only interested in how long it will take to reach its maximum height, that means we only need to find the t value of the vertex. And we can do that by using the fact that the vertex of a quadratic equation, h of t, is equal to at squared plus bt plus c, is at t equal to -b over 2a, which actually is a direct result from completing the square. So looking at our equation here, we see that a, the coefficient of t squared, is -16, and b, the coefficient of t, is equal to 64. Therefore, the t value of the vertex, namely -b over 2a, is equal to -64 divided by 2 times -16, or -64 divided by -32, which is equal to 2. That is, our answer then is that after t equal to 2 seconds, this ball will reach its maximum height. Thank you, and we'll see you next time. Let's look at solving quadratic inequalities. For example, let's solve the following inequality. Now, when we solve quadratic inequalities, we start in the same way as we do when we solve quadratic equations, namely bringing everything to one side and getting 0 on the other. So this gives us x squared minus 4x minus 5 is greater than 0. And now we can factor the left-hand side. It factors into x minus 5 times x plus 1 is greater than 0. Now, when solving these types of inequalities, there's a few different approaches. The first approach is what we call a sine analysis. Now remember, if we have a product, a times b greater than 0, what does that mean? That means that either a and b are both positive or a and b are both negative. In other words, a is greater than 0 and b is greater than 0, or a is less than 0 and b is less than 0. So let's apply that here. We have a product of factors greater than 0, which means that the first factor, x minus 5, is greater than 0, and the second factor, x plus 1, is greater than 0, or the first factor is less than 0, and the second factor is less than 0, which means that x is greater than 5 and x is greater than negative 1, or x is less than 5 and x is less than negative 1. Now we can consolidate this into just x is greater than 5, can't we? Because if you think of the number line, let's say this is negative 1 and this is 5. If x is larger than 5, certainly it's larger than negative 1. And similarly, you can condense this to x is less than negative 1. Because if x is less than negative 1, certainly x is less than 5. So combining these on one number line, we get x is less than negative 1, or x is greater than 5. And notice here that we have open circles at these values because our original inequality up here was a strict inequality. Now we're asked to put our answer in interval notation. Therefore, our answer is negative infinity up to negative 1, open parenthesis because we do not want to include negative 1, union, again, open parenthesis because we do not want to include 5, up to infinity. All right, what about the other approach? The second approach is what we call a graphical approach. So we still start with the same inequality, And we begin in the same way by bringing this 5 over. So we have x squared minus 4x minus 5 is greater than 0. But now let y equal this left-hand side, this x squared minus 4x minus 5. So to solve this, we need to find x values that make y greater than 0, which we can do by thinking of the graph of y. The graph of y is a parabola, isn't it? And because the leading coefficient here, namely 1, is greater than 0, we have the parabola opening upward, and we found this vertex here by using the formula that x is equal to negative b divided by 2a, which in this case is negative 4 divided by 2 times 1, or 2. And then we can find the y-coordinate of the vertex by plugging that value 2 into the equation. So we'd get y is equal to 2 squared minus 4 times 2 minus 5. And 2 squared is 4, and 4 times 2 is 8. So we have 4 minus 8 minus 5, which is equal to negative 9, which is how we get this vertex here. Now remember, we want to find the x values that make y greater than 0. Y will be greater than 0 above the x-axis here on these green pieces. So what we need to do is to determine what x values will land us on those green pieces, which means we need to find these x-intercepts here. And we can do that by factoring. What does this factor into? It factors into x minus 5 times x plus 1. And the x-intercepts are the values where this is equal to 0. And these values are x equals 5 and negative 1, which means this here is x equal to negative 1, and this is x equal to 5. Now we know y is equal to 0 at those values, but we're only interested in the x values that make y strictly greater than 0. Therefore, we need to exclude those values in our answer. So we'll put open circles here on the graph. So as long as x is greater than 5 or less than negative 1, we'll land on these green pieces of the parabola. Therefore, our answer is the same as it was in the first approach, namely, negative infinity up to negative 1, union 5 to infinity. And these are two different approaches to solving quadratic inequalities. Thank you, and we'll see you next time. Let's look at finding the inverse of a function. For example, let f of x equal 1 minus 4x. Let's find f inverse of x if it exists. Remember that the inverse of a function is defined as follows. Y is equal to f inverse of x if and only if f of y is equal to x. And remember here, be very careful with this notation. This does not mean 1 divided by f. It's just the notation for the inverse function. So notice what we're doing here is we are switching the roles of x and y, and then solving for y. And that will give us f inverse of x. That is, let's let y equal f of x, or 1 minus 4x. And now we'll interchange the roles of x and y. So wherever we see a y, we'll put an x, and wherever we see an x, we'll put a y. And then we'll solve for y. So we have 4y is equal to 1 minus x. And then dividing both sides by 4 gives us that y is equal to 1 minus x divided by 4, or dividing both terms in the numerator by 4, we get y is equal to 1/4 minus x over 4. And we were uniquely able to solve for y, so this is f inverse. So f inverse of x is equal to 1/4 minus x divided by 4. All right, let's look at another example. Let f of x equal x squared plus 1. Let's find f inverse of x if it exists. Again, we'll let y equal f of x, or y is equal to x squared plus 1. And then we'll interchange the roles of x and y, which gives us x is equal to y squared plus 1. And then we'll solve for y. We have y squared is equal to x minus 1, or y is equal to plus or minus the square root of x minus 1, which means we weren't uniquely able to solve for y, because for any input x, we'd get two possible y values, the positive and the negative square root, which means that f inverse of x does not exist. Which shouldn't surprise you if you think of the graph of this function. It's a parabola with vertex at 0, 1, opening upward, which isn't a one-to-one function, is it? Because by the horizontal line test, if we pass a horizontal line through this graph, it's going to intersect it in more than one spot. And if the original function f is not one-to-one, then f inverse of x will not exist as a function. However, if we restrict the domain of f of x to x greater than 0, then we're only looking at this part of the parabola. Therefore, on that restricted domain, f is one-to-one. So f on the restricted domain will have an inverse. That is, if we restrict the domain of f to the interval 0 to infinity, for example. We could have also restricted it from negative infinity to 0, but let's just restrict it from 0 to infinity. Then f will be one-to-one. And therefore, f inverse will exist. So if we look at the graph of this, here is f of x on the restricted domain. And its inverse will exist. But what are we going to choose over here for f inverse of x, the positive or the negative? We're going to choose the positive because remember that the range of the inverse is equal to the domain of the original function. And if we're restricting that domain to 0 to infinity, this has to be the range of the inverse. And so the output, namely y, has to be positive. That is, f inverse of x on this restricted domain is equal to the square root of x minus 1. And let's plot this on the graph above. This is 1. Then our inverse looks like this, doesn't it? This is f inverse, which is square root of x minus 1. Now look at these graphs. Aren't they symmetric about the line y equal x? And that will always be true of a function and its inverse. Their graphs will always be symmetric about the line y equal x. And you should graph the two lines from example number 1. You'll see that their graphs are symmetric about the line y equal x. And this is how we find inverse functions. Thank you, and we'll see you next time. Let's look at inverse functions. For example, let's find the inverse of this one-to-one function f, and then we'll state its domain and range. The first thing we do when we're finding an inverse of a function is, in the definition of that function, we replace f of x by y. In other words, we have y is equal to x plus 3 divided by x minus 4. And then we interchange the roles of x and y. In other words, wherever we see a y, we put an x, and wherever we see an x, we put a y, which gives us x is equal to y plus 3 divided by y minus 4. And now we want to manipulate this equation in order to solve for y. When we do that and solve for y, y will be equal to f inverse of x. And we know we're going to be able to do that because we're given that f is 1-to-1 and therefore the inverse will exist. So let's begin by multiplying both sides of the equation by this denominator here, the y minus 4, which gives us x times y minus 4 is equal to y plus 3. And now let's distribute this x to both of these two terms, which gives us x times y minus 4x is equal to y plus 3. Now remember, we want to solve for y. So let's bring all the terms with y in them to one side and everything else to the other. And this will give us that x times y minus y is equal to 3 plus 4x. And now on the left-hand side, we can factor out a y. And if we divide both sides of the equation by this x minus 1, we will have solved for y. So y is equal to 3 plus 4x divided by x minus 1. And this is f inverse. So f inverse of x is equal to 3 plus 4x divided by x minus 1. So here's our inverse. However, we also are asked to find its domain and range. So let's start with the domain. Looking here at f inverse, the only issue would be if x were equal to 1, because then we'd be dividing by 0. So we need to exclude this value. That is, the domain of f inverse, written in interval notation, is equal to negative infinity up to 1, open parenthesis because we want to exclude 1, union, again, open parenthesis at 1 because we want to exclude it, up to infinity. All right, what about the range, though? Now, this is where we can use the fact that the range of the inverse is the domain of the original function. That is, this is equal to the domain of f. But what is this domain? Looking back up here at our original function, the only issue would be if x were equal to 4, because then we'd be dividing by 0. That is, we need to exclude this value in the domain of f. That is, the domain of f, written in interval notation, is the interval from negative infinity up to 4, open parenthesis, because we want to exclude 4, union, open parenthesis again at 4, because we want to exclude 4, up to infinity, which is also the range of the inverse. That is, this is equal to negative infinity up to 4, union 4 to infinity. Now this is very useful to be able to look at the domain of the original function to determine the range of the inverse. And this is how we work with inverse functions. Thank you, and we'll see you next time. Let's look at verifying inverse functions. For example, let's determine whether f of x equal to 5 minus 2x and g of x is equal to 5 halves minus x over 2 are inverses of each other. Well, we have the following fact. The two functions f and g are inverses of each other if and only if both of the following compositions hold. Namely, when we compose f with g of any x in the domain of g, then we get back to x. And if we compose g with f at any x in the domain of f, we also get back to x. That is, the composition in either direction gets us back to x. So let's compute f of g of x for our situation here. This is equal to f of, and g of x is this 5 halves minus x over 2. And now to compute f at any input, we put this input in where we see x. That is, this is equal to 5 minus 2 times that entire input. And then distributing the minus 2 through, we have 5 minus 2 times 5 halves. And then minus 2 times negative x over 2, which is equal to 5 minus 5, and then plus 2x divided by 2. And 5 minus 5 is 0. And then these 2's will cancel, which sure enough leaves us with x. So this first composition property is satisfied. However, we have to make sure the second one is also satisfied. So let's compute g of f of x. This is equal to g of, and f of x is this 5 minus 2x. And then to evaluate g at any input, we take this input and we put it up here wherever we see an x. That is, this is equal to 5 halves minus this whole input, or 5 minus 2x, all divided by 2, which is equal to 5 halves minus, and then dividing both terms in the numerator by 2, and distributing our negative gives us 5 halves minus a minus 2x over 2, or a plus 2x over 2. And 5 halves minus 5 halves is 0. And then these 2's will cancel. And sure enough, we get x. So this second composition property is satisfied as well. So yes, f and g are inverses of each other. That is, we can say that f is equal to g inverse, and g is equal to f inverse. All right, let's look at another example. Let's determine whether these two functions are inverses of each other. Again, we're going to compute both of these compositions and see if they yield x. So let's start with f of g of x. This is equal to f of negative 4 over x, because g of x is equal to negative 4 over x. And then f of any input, we put that input in wherever we see an x. That is, this is equal to 4 divided by negative 4 divided by x, which is 4 times x divided by negative 4. And then the 4's will cancel. However, we're still left with a negative 1 in the denominator, which means this is equal to negative x. It's not equal to x. So this is not satisfied. So these will not be inverses of each other. But let's, for the fun of it, compute the composition in the other direction. This is g of 4 divided by x, because f is 4 divided by x. And to compute g at any input, we take that input and plug it in wherever we see an x here. That is, this is equal to negative 4 divided by 4 over x, which is equal to negative 4 times x divided by 4. And again, these 4's will cancel, which leaves us with negative x, which again is not equal to x. So the second composition down here is also not satisfied. Now be careful here. Some students will think that because this composition down here, namely g composed with f, and this composition up here, namely f composed with g, are equal to one another, that these functions would be inverses of each other. But they're not, because not only do these compositions have to be equal to one another, they also have to be equal to x, not negative x. So our answer here then would be no, they're not inverses. All right, and this is how we verify whether two functions are inverses of one another. Thank you, and we'll see you next time. Let's learn how to divide polynomials. For example, let's divide x squared plus 9x plus 19 by x plus 4. Now we begin dividing polynomials in a similar way as we do when we divide numbers. But we start by looking at the leading terms and ask ourselves, x times what is equal to x squared? And this would be x, wouldn't it? Because x squared divided by x is equal to x. So that's the first term in our quotient here, x. And now we need to multiply x by the entire divisor x plus 4, which gives us x squared plus 4x. And then just like when we divide numbers, we now subtract. X squared minus x squared is 0. 9x minus 4x is 5x. And we still have this plus 19 here. Now, are we done? We're not, because the degree of this is not less than the degree of this. So we continue until the degree is smaller than the degree of the divisor. Again, we look at the leading terms here, x and 5x, and ask ourselves, x times what is equal to 5x? And this would be 5, wouldn't it? Because 5x divided by x is 5. So that's the next term in our quotient. So we have plus 5. And now we multiply 5 by the entire divisor, x plus 4, which gives us 5x plus 20. Again, we'll subtract. 5x minus 5x is 0, and 19 minus 20 is negative 1. And now the degree of negative 1 is 0, which is smaller than the degree of the divisor, so we're done. Well, how can we represent our answer here? By the division algorithm, we have that the dividend, x squared plus 9x plus 19, divided by the divisor, x plus 4, is equal to the quotient, x plus 5, plus the remainder, which is negative 1, divided by the divisor, x plus 4. Or we can multiply both sides of the equation by the divisor, x plus 4, which gives us that x squared plus 9x plus 19 is equal to x plus 5 times x plus 4, and then minus 1. So these are two nice ways of representing our answer. And in this last form here, we can actually check that we've done this division correctly by FOILing this out and then subtracting 1. So let's do that. When we FOIL out the right side, we get x squared plus 4x plus 5x plus 20, and then we still have the minus 1, which is equal to x squared plus 9x plus 19, which sure enough is our dividend. All right, let's look at another example. Let's divide. Well, the first thing to notice here is that our dividend is not written in standard form. Standard form would be 4x to the 4th minus 11x squared plus 15x plus 7. And the other thing to notice is also there's no x cubed term. So let's add a placeholder term with a coefficient of 0. That is, let's write our dividend 4x to the 4th plus 0x cubed minus 11x squared plus 15x plus 7. All right, so we're ready to divide now. Our divisor is 2x squared plus 3x minus 2. And our dividend is 4x to the 4th plus 0x cubed minus 11x squared plus 15x plus 7. Again, we start by looking at the leading terms, which is why we wanted to rewrite this dividend in the first place. So we're going to ask ourselves, 2x squared times what is equal to 4x to the 4th. And isn't that 2x squared? Because 4x to the 4th divided by 2x squared is equal to 2x squared. So that will be the first term in our quotient up here. So we have 2x squared. And then we multiply 2x squared by the entire divisor, 2x squared plus 3x minus 2, which gives us 4x to the fourth plus 6x cubed minus 4x squared. And now we subtract. 4x to the fourth minus 4x to the fourth is 0. And then 0x cubed minus 6x cubed is negative 6x cubed. And then negative 11x squared minus a minus 4x squared is negative 7x squared. And then we still have this plus 15x plus 7. Now we didn't need to write this placeholder here, this 0x cubed, but when we subtract this 6x cubed, it comes in handy because then we know we are subtracting 6x cubed from 0x cubed. All right, now we have to ask ourselves how many times this goes into this. That is 2x squared times what is equal to negative 6x cubed. And that would be negative 3x, wouldn't it? Because negative 6x cubed divided by 2x squared is equal to negative 3x, which is the next term in our quotient. So we have a negative 3x. And then negative 3x times our entire divisor gives us negative 6x cubed minus 9x squared plus 6x. Again, we subtract. Negative 6x cubed minus a minus 6x cubed is 0. And then negative 7x squared minus a minus 9x squared is positive 2x squared. Then 15x minus 6x is positive 9x. And then we still have the plus 7. All right, 2x squared goes into 2x squared one time. So that would be the last term in our quotient here. So 1 times our divisor is 2x squared plus 3x minus 2. Again, we subtract. 2x squared minus 2x squared is 0. 9x minus 3x is 6x. 7 minus a minus 2 is plus 9. And now the degree of this is smaller than the degree of our divisor up here. So we're finished. So by the division algorithm, this dividend divided by the divisor is equal to the quotient, which is 2x squared minus 3x plus 1 plus the remainder, 6x plus 9, divided by the divisor, this 2x squared plus 3x minus 2. And this is how we divide polynomials. Thank you, and we'll see you next time. Let's learn about synthetic division. For example, let's use synthetic division to divide 2x cubed minus 9x squared plus 6x minus 7 by x minus 4. Now, synthetic division is a shortcut used to divide a polynomial by x minus r. Notice here, this is a degree 1 polynomial. So synthetic division can only be used when the divisor is a degree 1 polynomial. And this technique comes from looking at the coefficients of p of x and the value of r. Now, what are the coefficients of p of x here? Well, let's put them under a division sign. We have 2, negative 9, 6, and negative 7. And it is imperative that our polynomial is in standard form before we read off these coefficients. But moreover, if there were any missing powers of x here, we'd have to write 0 for that power as a placeholder. Now what is our r here? Our r is 4. So let's put the 4 to the left of the division symbol. Now that these numbers are set up, the first step in synthetic division is to drop the first coefficient of p, so we'll drop the 2. The next step is that we multiply the 4 and the 2 and put our result here, so 4 times 2 is 8. And then we add. So -9 plus 8 is -1. And now we continue this pattern. So we multiply the 4 and the -1, which gives us -4. Again, we're going to add, which gives us 2. And then we multiply, which gives us 8. And then we add, which gives us 1. Now, what are these numbers down here? These first 3 numbers are the coefficients of the quotient of the division. And this last number here is the remainder of the division. And moreover, the degree of this quotient is 1 less than the degree of our dividend p of x. And this is because our divisor, x minus r, is a degree 1 polynomial. And since our dividend here, p of x, is a degree 3 polynomial, then our quotient will be a degree 2 polynomial. Therefore, our quotient, which we'll call q of x, is equal to a degree 2 polynomial with these coefficients. Namely, it's 2x squared minus 1 times x plus 2. And our remainder is equal to 1. This number here, this last number. Therefore, by the division algorithm, p of x divided by x minus r is equal to q of x, which is 2x squared minus x plus 2, plus the remainder divided by the divisor, which is x minus 4 in this case. Let's actually take a quick look at the long division so you can see why this technique works. So we'll be dividing p of x by x minus 4. Now x goes into 2x cubed, 2x squared times, and 2x squared times x minus 4 is 2x cubed minus 8x squared. And now subtracting, we get negative x squared plus 6x minus 7. And x goes into negative x squared, negative x times, and negative x times x minus 4 is negative x squared plus 4x, and subtracting gives us 2x minus 7. And now x goes into 2x 2 times, and 2 times x minus 4 is 2x minus 8, and when we subtract, we get 1. So sure enough, our quotient is 2x squared minus x plus 2, and our remainder down here is 1. Now, sometimes students get confused that we subtract here, but we add with synthetic division. But notice here we have this negative in front of the 4. Whereas with synthetic division, we don't. So subtracting then here will give us the same result as adding when we use synthetic division. All right, let's look at one more example. Let's use synthetic division to divide p of x by x plus 4. Now, the first thing to notice about p of x here is that it's not written in standard form. So let's do that. Let's write it in standard form. We have p of x is equal to, we have this x to the fourth term, so negative 2x to the fourth. And then we have this x cubed term, so negative 7x cubed. And then we have this x squared term, so plus 4x squared. And finally, we have this constant, plus 1. Now notice here that there is no x term. And with synthetic division, it's very important that we have every power of x. That is, before reading off the coefficients of p, we need to write p of x as follows. Negative 2x to the fourth minus 7x cubed plus 4x squared plus 0x. We have to have a placeholder, and then plus 1. Now we're ready to read off the coefficients of p. They're negative 2, negative 7, 4, 0, and 1. But what is r? We're dividing p by x plus 4. And we can think of x plus 4 as x minus a minus 4. So this is r here. So let's put the minus 4 here. And now we drop. We multiply, which gives us 8. Then we add, which gives us 1. Then we multiply the negative 4 and the 1, which gives us negative 4. And then we add, which gives us 0. And then negative 4 times 0 is 0. We add, we get 0 again. And negative 4 times 0 is 0. We add, we get 1. Now remember, these are the coefficients of our quotient. But moreover, our quotient is 1 less in degree than this dividend here, p of x, which is of degree 4. Which means q of x, then our quotient, is of degree 3 with these coefficients. Therefore, it is equal to negative 2x cubed plus 1x squared plus 0x plus 0, which we don't need to write. And this is our remainder, r of x. Therefore, by the division algorithm, we have that p of x divided by x minus r is equal to the quotient q of x plus the remainder r of x divided by x minus r. Or in our case, p of x is 1 plus 4x squared minus 2x to the fourth minus 7x cubed divided by x minus r, or x plus 4, is equal to q of x, which is negative 2x cubed plus x squared, plus the remainder of 1 divided by x plus 4. All right, and this is how we can use synthetic division to divide a polynomial by a divisor that is a degree 1 polynomial. Thank you, and we'll see you next time. Let's look at properties of polynomials. For example, let's state the left and right behavior, find the maximum number of zeros and the maximum number of local extrema for this polynomial here. F of x is equal to 6x to the fourth minus 7x cubed plus 4x squared plus 6x. Let's begin by looking at the left and right behavior, or the end behavior of this polynomial. Now, a polynomial function is one of the following form. F of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a1x plus a0. N here is called the degree of the polynomial, and a sub n is called the leading coefficient, which we are assuming is non-zero. Now, the graph of any polynomial function f will eventually rise or fall without bound, and to determine what happens, we look at this degree and the leading coefficient. Namely, we have the following four cases. If n is odd and a sub n is greater than 0, then the graph of f will eventually fall to the left and rise to the right, as this figure shows here. And this should make sense to you, because as x goes to positive infinity or negative infinity, the leading term a sub n x to the n will dominate all the other terms combined. So if n is odd and x goes to infinity, then x to the n will also go to infinity. And because a sub n is greater than 0, then the graph will eventually rise without bound as x goes to infinity. And as x goes to negative infinity, then x to the n will also go to negative infinity. And because a sub n is positive, then the graph will eventually fall without bound as x goes to negative infinity. And applying the same type of logic when n is odd and a sub n is less than 0, we get that the graph of f will eventually rise to the left and fall to the right. However, when n is even though, and a sub n is greater than 0, then the graph of f will eventually rise to the left and rise to the right. But when n is even and a sub n is negative, then the graph of f will eventually fall to the left as well as fall to the right. So looking at our polynomial here, we see that the degree is 4 and that the leading coefficient is 6. That is, n is equal to 4, which is even, and a sub n is equal to 6, which is greater than 0. So we're in this case here, we're in case 3. Which means that we can write our answer up here that the graph of f eventually rises to the left and rises to the right. Now it still remains to find the maximum number of zeros, or x-intercepts, and the maximum number of local extrema. And again, the degree here governs that. We have the following two cases. That a polynomial of degree n with real coefficients has at most n real zeros, and at most n minus 1 local extrema or turning points. So for our polynomial, we have n is equal to 4, which means coming back up here, the maximum number of zeros then would be n, or 4, and the maximum number of local extrema would be 4 minus 1, or 3. All right, let's look at one more. Let's state the left and right behavior of this polynomial here, as well as find the maximum number of zeros and the maximum number of local extrema. All right, let's start again with the left and right behavior. Which of these four cases are we in? Well, what is the degree and the leading coefficient of our polynomial here? If we multiplied it all out, we'd have f of x is equal to negative 2x cubed plus a bunch of other stuff. Because when we square this out, we're going to have a degree 2 polynomial, which then we're multiplying by a degree 1 polynomial, which would give us a degree 3 polynomial with leading coefficient negative 2, which means n is equal to 3, which is odd, and a sub n is negative 2, which is negative. Which means we're over here in case 2, aren't we? Therefore, the graph of f eventually rises to the left and falls to the right. And now let's state the maximum number of zeros as well as the maximum number of local extrema. Recall from our last example that a polynomial of degree n with real coefficients has at most n real zeros and at most n minus 1 local extrema. So here n is 3, which means coming back up here, the maximum number of zeros then would be 3. And the maximum number of local extrema would be 3 minus 1, or 2. And this is how we work with some properties of polynomials. Thank you, and we'll see you next time. Let's learn about the remainder theorem. For example, let's use the remainder theorem to find p of 1, where p of x is equal to 2x cubed minus 3x squared minus 9. Now the remainder theorem states the following. If a polynomial p of x is divided by x minus c, then the remainder of that division is p evaluated at c. Let's think about why this is true. By the division algorithm, when we divide p of x by x minus c, then p of x is equal to x minus c times some polynomial q of x plus a constant r, where here q is the quotient and r is the remainder. And the reason this remainder is a constant is because it has to be 1 less in degree than this divisor here, which is of degree 1, so r would have to be of degree 0 or a constant. Now let's evaluate p at c. That is, p of c is equal to, we're putting a c everywhere we see an x, so it's c minus c times q of c plus r, or p of c is equal to 0 times q of c plus r, or sure enough, p of c is this remainder r. Let's apply this to our problem. We want to find p of 1, so our c here is equal to 1. So p of 1 will be the remainder when we divide p of x by x minus c, or x minus 1. Now we could either use long division or synthetic division to divide, but let's use long division here. Now x goes into 2x cubed, 2x squared times, and 2x squared times x minus 1 is 2x cubed minus 2x squared. When we subtract, we get negative x squared minus 9, and x goes into negative x squared, negative x times, and negative x times x minus 1 is negative x squared plus x. And when we subtract here, we need to be careful. Let's think of there being a plus 0x here. So when we subtract, we have 0x minus x, or negative x, and then we still have the negative 9. X goes into negative x, negative 1 times. Negative 1 times x minus 1 is negative x plus 1, and then when we subtract, we get negative 10, which is our remainder. Therefore, p of 1 is equal to this remainder, negative 10, which is our answer. Now we can check this answer by plugging this value 1 into our polynomial p. Namely, p of 1 is equal to 2 times 1 cubed minus 3 times 1 squared minus 9, or 2 minus 3 minus 9, which sure enough is 2 minus 12, or negative 10. Let's look at another example. Again, let's use the remainder theorem to find p of negative 3, where p of x is equal to x to the 4th plus 2x cubed minus 4x squared plus 5. Again, in order to find p of c, we divide p by x minus c, where here in this case, c is equal to negative 3. So we would need to divide our polynomial by x minus a minus 3, or x plus 3. Again, in order to perform this division, we could either use long division or synthetic division. Let's use synthetic division here. So we write our c, negative 3, and then we put all the coefficients of p, namely 1, 2, negative 4, and now be careful here. Remember, it's mandatory that we hold the place of the x and write plus 0x. So we have a 0 and then our 5. And then we drop the 1. Negative 3 times 1 is negative 3. We add, we get negative 1. We multiply, we get 3. We add, we get negative 1. We multiply, we get 3. We add, we get 3. We multiply, we get negative 9. And then we add, we get negative 4. Now remember, with synthetic division, this last number here is our remainder. Therefore, that is p of negative 3 by this theorem. So our answer then is that p of negative 3 is equal to negative 4. Again, we can check our answer by plugging negative 3 into our polynomial here. Namely, p of negative 3 is equal to negative 3 to the 4th power plus 2 times negative 3 cubed minus 4 times negative 3 squared plus 5, which is equal to 81 minus 54 minus 36 plus 5. And minus 54 minus 36 is negative 90. So we're left with 81 minus 90 plus 5, which is negative 9 plus 5, which sure enough is equal to this negative 4. And this is how we work with the remainder theorem. Thank you, and we'll see you next time. Let's work with the factor theorem. For example, let's determine whether x minus 3 is a factor of p of x. And we can use the factor theorem to help us out here. And the factor theorem states that a polynomial p has a factor x minus r if and only if r is a zero or a root of that polynomial. So we want to use this to determine whether x minus 3 is a factor of this polynomial here. So our r here is 3, and we want to compute p of 3 by plugging in 3 wherever we see an x and see if we get 0 as our answer. And if we do, then yes, x minus 3 will be a factor of p. All right, so what is p of 3? This is equal to 2 times 3 cubed minus 5 times 3 squared minus 3 minus 6, which is equal to 2 times 27 minus 5 times 9 minus 3 minus 6, or 54 minus 45 minus 3 minus 6. And 54 minus 45 is 9, and then minus 3 minus 6 is negative 9. So sure enough, yes, this is equal to 0. So since p of 3 is equal to 0, x minus 3 is a factor of p. Let's see another example. Let's determine whether x plus 2 is a factor of p. Again, we'll use the factor theorem, which states that x minus r will be a factor if r is a zero of p. We want to determine whether x plus 2 is a factor of p of x. But what is our r here? X plus 2 is really x minus a minus 2. So be careful here, our r is negative 2. So we'll plug in negative 2 everywhere we see an x here, and if we get 0 as an answer, then yes, x plus 2 will be a factor of p. So what is p of negative 2? This is equal to negative 2 times negative 2 to the 4th minus 2 times negative 2 cubed plus 6 times negative 2 squared minus 5, which is equal to negative 2 times 16, and then minus 2 times minus 8, and then plus 6 times 4 minus 5, which is equal to negative 32 plus 16 plus 24 minus 5. Now 16 plus 24 is 40, and 40 minus 5 is 35, so this is minus 32 plus 35, which is equal to 3, which is not 0. So since p of negative 2 is not equal to 0, x plus 2 is not a factor of p. And this is how we work with the factor theorem. Thank you, and we'll see you next time.
Welcome! In this unit, you'll be learning about exponential and logarithmic functions. You've already spent a great deal of time learning about functions, but these two functions are so special that they're worth their own unit. These functions get used a lot in applications, so let's start with an application to see why we need an exponential function and a logarithmic functions, and why the ones you've learned so far won't suffice. Let's begin by looking at an example to understand why we need the exponential and logarithmic functions. Suppose we have a bunny. And if this bunny has a bunny every month, well, after 1 month, we'd have 1 bunny. After 2 months, he would have a bunny, and we would have 2 bunnies. After 3 months, each of those 2 bunnies would have a bunny, and we'd have 4 bunnies. If each of those 4 bunnies had a bunny, we would have 8 bunnies, and so on. And eventually, we'd have a ton of bunnies. So suppose we track the bunnies' population over time. What if we wanted to know how many bunnies there were after a month, after 2 months, after 5 months, after a year, after 5 years, after a century? To do these sorts of calculations, we would need to have some sort of function which captured the doubling behavior of the bunny population. So the function we're going to look at is something called the exponential function. We have a graph, and in this graph we see the population of the bunnies for several iterations. We started with 1 bunny, then we had 2, then we had 4, and so on. What kind of function matches this behavior? Well, if you look back at think about the catalog of functions you already know. You know linear functions, polynomial functions, rational functions, and you try to think about this curve over here. Well, what does that look like? This curve doesn't look like any of the curves you're familiar with. You might guess a parabola because it seems to be curving up. However, that won't work for this population. If we want to match this with a curve, it would have to look something like this. And that curve is getting steeper and steeper because this population of bunnies is getting large very, very quickly. And that brings us to the need for the exponential function. In John Napier's book, A Wonderful Description of Logarithms, he described how the logarithm was such a useful tool to help do calculations for celestial mechanics. This book was the first one of its time to describe how a logarithm could be used to turn hard multiplications into simple additions. He also gave a table of logarithmic values, which was used for hundreds of years afterwards. Another mathematician, Leonhard Euler, played a large role in the development of the exponential and logarithm functions. Leonhard Euler was actually the first guy to use the notation for a function, f of x. So whenever you see that f parentheses x, that was due to Euler. Euler was a very prolific mathematician. He wrote over 800 published papers in his lifetime, and his works would complete 90 volumes. In one of Euler's works, he looked at a constant that came up from numerous calculations, and it's since been known as Euler's constant or Euler's number. Let's look a little more closely now at Euler's constant. Euler's constant, denoted by an E, is equal to 2.712818, etc. Euler's constant is an infinite non-repeating decimal number, which we call a transcendental number in mathematics. You're already familiar with the transcendental number pi, 3.1415, etc. That's a number you've probably seen already in your studies. Euler's constant can be thought of as coming from a wide variety of areas, including things like geometry, the interest when you're talking about interest on a loan or interest you earn in a bank account, and other situations such as continued fractions. Euler's constant can be derived from a number of these situations, and you'll encounter these more later in your mathematical studies. Let's move on and talk about the function that results from Euler's constant, or the exponential function. Using that notation that Euler developed for functions, f of x equals e to the x is called the exponential function. This means we take that Euler constant number, 2.71, etc., and raise it to any number x as the power. For example, f of 1 would just be e raised to the 1 power, which is just e itself, or that 2.71, etc. The related function to the exponential function is the logarithm function. Here you see our logarithm function, g of x, equals log base e of x. We also denote this as ln. The ln stands for natural logarithm, or it's a special logarithm function where the base is e. The base is that little number written as a subscript of the logarithm. We read this as log base e of x. These two functions are very closely related to each other. Namely, they're inverse functions for each other. Inverse functions have the property that when we compose them together, they undo each other and we're just left with x. For example, a composition f of g of x or e to the ln of x just gives me x. Same thing if I compose them in the opposite order. G of f of x equals ln of e to the x power, and those exponentials and logs again undo each other and I'm just left with x. That's the inverse property of functions. You may have just seen we did this with a base of e. E isn't the only base you can use when dealing with the exponential and logarithm functions. Let's look now at the general exponential and logs. The general exponential function would just be f of x equals a to the x. A here is taking the place of some constant. A can be any positive number not equal to 1. So a has got to be greater than 0, but we won't let it be equal to 1. The reason is, if a was 1, 1 to any power is just 1, and we'd get a constant function, which really doesn't satisfy the properties of exponential functions that we'll be talking about shortly. Another function we can look at, g of x equals log base a of x. Again, that subscript on the log stands for the base. We can convert back and forth between the logarithm and the exponential function according to if y equals log base a of x, this really just means that a to the y power equals x. Once again, these two functions have the inverse property. If I compose them together, f of g of x or g of f of x, the exponential and logarithm undo each other and I'm just left with the x. Let's do a quick example so you can see how the log works, because with different bases, sometimes this can be new to students. For example, what if I wanted to compute the log base 2 of 16? First, I'm going to notice to myself that 2 to the 4th power, or 2 times 2 times 2 times 2, is just equal to 16. So 2 raised to the 4th power is 16. In other words, log base 2 of 16 is asking the question, what power do I need to raise 2 to get 16? And the answer is 4, because 2 raised to the 4th power gives me 16. So you can see logarithm is kind of asking the inverse question of what power do I need to raise the base to get the quantity that I'm taking the logarithm of. Let's review some of the exponential properties that you'll see later in this course. You see a lot of properties listed here. You'll be talking about these in much more detail later on. But for right now, what you'll want to be noticing is that there's a lot of properties of exponential functions, and utilizing these will allow you to solve equations involving exponents. Specifically, exponential equations with e or any other base that we're talking about. A and b here are standing for bases. Remember, those numbers have to be positive and cannot equal 1. The logarithm also has a lot of properties. Don't worry about memorizing these now, but you will be utilizing them later to solve logarithm equations. Some of these properties come up again and again in calculus, so I highly recommend you pay attention now, learn these well, because that'll help you a lot later in your calculus studies. We can also consider the properties of the graphs of exponentials and logarithms. Here I've shown you an example of an exponential graph. This is if the value of a, or the base of the exponential, is greater than 1. If the value were between 0 and 1, the function would just be going down to the right and increasing on the left. That would be a base that's smaller, and it would be negative growth or decreasing function. Notice here, I've listed some properties of the exponential function graph. One of the key properties is all exponential functions go through the special point 0, 1. This is because anything raised to the 0th power just gives you a 1, and that's why that special point is on all of our exponential functions. Another property you'll notice from the graph is this function is continuous. There's no gaps, breaks, or jumps in our curve. This also has a horizontal asymptote at the x-axis, or y equals 0. Notice as I go to smaller values of x, the function gets closer and closer to the x-axis, but it actually never reaches it. That's why it's an asymptote. We also have the properties that this function increases as I go to the right and decreases as I go to the left. Finally, notice this function is 1-to-1. Remember, we check for functions being 1-to-1 by looking at the horizontal line test. Any horizontal line across my curve will intersect the graph at exactly 1 point and not more than 1 point. All right, let's now look at the exponential function's inverse, namely the logarithm function, for contrast. The logarithm function here is given by a graph like this. The logarithm function graph is also continuous because notice there's no breaks, gaps, or jumps. It goes through the special point 1, 0. It also has a vertical asymptote at x equals 0, or the y-axis. Notice that this function also increases as we go to the right, and as I head towards x equals 0, this function goes to negative infinity. This function is also 1-to-1 because notice any horizontal line through this function will intersect the graph at most 1 time. How are these two functions related to each other? Well, if you start to look at their graphs, you can probably see that these two functions are inverses, which we've been talking about a lot, and if we look at the graphs, you can see that more easily. So here I've graphed a sample of an exponential function with base e and a logarithm function, or natural logarithm, ln of x. The red line there is the line y equals x. Notice if I folded the screen over the red line, the two curves would line up on top of each other. That's because they're inverse functions, so they're basically a reflection across the line, y equals x. Well, let's see, what are we going to learn about exponentials and logarithms in this course? In this unit, you will learn to, first of all, evaluate exponential and logarithm expressions. You'll also learn to convert back and forth between the exponential and logarithm form of an equation. You'll learn to graph those exponential and logarithm functions, particularly when you have transformations. You'll learn to solve exponential and logarithm equations. That's going to be one of the most important skills that you'll need to take with you to your calculus course. Finally, we'll talk about using exponentials and logarithms to solve application problems. Speaking of applications, what are the applications of exponentials and logarithms? There's quite a few applications, including population dynamics is probably the most standard one you'll hear about. If we look at the population, for example, the bunnies we looked at earlier, growing with time, you'll often see exponential growth. Radioactive decay is another popular application of exponentials and logarithms. You may have heard of carbon dating. Carbon dating is where they figure out the age of old artifacts using the decay of carbon over time. And that's looking at an example of decay. In this case, it's not radioactive, but we are looking at the decay of a substance. Also, if you're ever investing money in the bank, you're often getting compound interest. Compound interest is an example of an application of exponential functions. Newton's law of cooling is the law that tells you if you put a cake on the counter, how quickly that cake will reach room temperature, or if you put hot soda in the fridge, how quickly will that soda cool. That's Newton's law of cooling, and that is another application of exponentials and logarithms. Finally, the Richter scale for earthquakes. In California, you may be very familiar with this. The Richter scale for earthquakes is actually a logarithm function, and those numbers that tell you how severe an earthquake is actually based on a logarithmic scale. Sound intensity is another thing that is measured in logarithms. The sound intensity decibel levels is a logarithmic function. And finally, the learning curve, which is the rate at which you acquire knowledge, can be modeled closely by exponential and logarithm functions. So if you're looking to figure out how much information you retain as a function of time at which you're studying, that actually will be modeled by exponentials and logarithms. Well, I hope you enjoy learning about exponential and logarithm functions. Thank you, and I'll see you next time.
Let's look at some examples of solving exponential equations. For example, let's solve this equation for x. Now, although these bases are different, they're both powers of 3. So let's write 9 as 3 squared, which will still be raised to the x plus 4th power, and we'll write 27 as 3 cubed, still raised to the 1 minus x power. And now, by properties of exponents, we can multiply the exponents. That is, we have 3 raised to the 2 times x plus 4 is equal to 3 raised to the 3 times 1 minus x. And now that these bases are the same, we know that these exponents have to be the same as well. And this is a direct result from the fact that exponential functions are one-to-one. Therefore, we have 2 times x plus 4 is equal to 3 times 1 minus x. And now let's distribute both the 2 and the 3, which gives us 2x plus 8 is equal to 3 minus 3x. And now we'll bring all the x terms to one side and the numbers to the other, which gives us 2x plus 3x is equal to 3 minus 8, or 5x is equal to negative 5, And now dividing both sides by 5 will give us our answer of x is equal to -1. All right, let's look at another example. Now the first thing to notice here is that 16 is a power of 4. In fact, it's 4 squared, isn't it? Which means we can rewrite this equation as follows. 4 raised to the 5y minus y squared is equal to 4 squared raised to the -3rd power. And now on the right, we can multiply those exponents, which gives us 4 raised to the 5y minus y squared is equal to 4 raised to the 2 times -3, or -6th power. Again, now that these bases are the same, these exponents will be as well. That is, 5y minus y squared is equal to -6. And now let's bring all the terms to one side, which would give us y squared minus 5y minus 6 is equal to 0. And now the left-hand side can factor. It factors into y minus 6 times y plus 1. Now we have a product of factors equal to 0, which means either the first factor is 0 or the second factor is 0. And if the first factor is 0, then y is equal to 6. Or if the second factor is 0, then y is equal to -1, which would be our answers. And these are a few examples on how we can solve exponential equations. We get the bases the same, and then we equate the exponents. Thank you, and we'll see you next time. Let's look at some examples of solving exponential equations. For example, let's solve this equation for x. Now, although these bases are different, they're both powers of 3. So let's write 9 as 3 squared, which will still be raised to the x plus 4th power, and we'll write 27 as 3 cubed, still raised to the 1 minus x power. And now, by properties of exponents, we can multiply the exponents. That is, we have 3 raised to the 2 times x plus 4 is equal to 3 raised to the 3 times 1 minus x. And now that these bases are the same, we know that these exponents have to be the same as well. And this is a direct result from the fact that exponential functions are one-to-one. Therefore, we have 2 times x plus 4 is equal to 3 times 1 minus x. And now let's distribute both the 2 and the 3, which gives us 2x plus 8 is equal to 3 minus 3x. And now we'll bring all the x terms to one side and the numbers to the other, which gives us 2x plus 3x is equal to 3 minus 8, or 5x is equal to -5. And now dividing both sides by 5 will give us our answer of x is equal to -1. All right, let's look at another example. Now the first thing to notice here is that 16 is a power of 4. In fact, it's 4 squared, isn't it? Which means we can rewrite this equation as follows. 4 raised to the 5y minus y squared is equal to 4 squared raised to the -3rd power. And now on the right, we can multiply those exponents, which gives us 4 raised to the 5y minus y squared is equal to 4 raised to the 2 times -3, or -6th power. Again, now that these bases are the same, these exponents will be as well. That is, 5y minus y squared is equal to -6. And now let's bring all the terms to one side, which would give us y squared minus 5y minus 6 is equal to 0. And now the left-hand side can factor. It factors into y minus 6 times y plus 1. Now we have a product of factors equal to 0, which means either the first factor is 0 or the second factor is 0. And if the first factor is 0, then y is equal to 6. Or if the second factor is 0, then y is equal to -1, which would be our answers. And these are a few examples on how we can solve exponential equations. We get the bases the same, and then we equate the exponents. Thank you, and we'll see you next time. We're going to learn about the change of base formula for logarithms here. How would we compute log base 3 of 5? Now remember that log base a of x is equal to y if and only if a to the y is equal to x. For example, log base 3 of 9 would be equal to 2 since 3 squared is equal to 9. But looking at our problem over here, do we know a power that we can raise 3 to get 5? We don't. And so we'd like to use our calculator, but how? Most calculators only have 2 log buttons. They have LOG, which means log base 10. And then they have LN, which means log base E. But they don't have a log base 3 button. So how are we going to compute log base 3 of 5? Well, we can use the change of base formula for logs, which states that we can change our base from A to C as long as we divide by the log of our old base. So let's apply that here with A equal to 3, B equal to 5, and we can use C equal to 10 because we have that button on our calculator. Now we could have also used C equal to E because we have that button as well, but let's use base 10. That is, log base 3 of 5 is equal to log base 10 of 5 divided by log base 10 of 3. And we don't normally write the base 10, so this is log 5 divided by log 3. Which, when we plug into our calculator, we get 1.4649 and so on. Now, if we would have used C equal to E, we would have arrived at the same answer. So this change of base formula for logs is very handy when we need to use the calculator to compute a logarithm. Thank you, and we'll see you next time. Let's look at converting between logarithmic and exponential equations. For example, let's rewrite this logarithmic equation as an exponential equation. Now we have the following equivalence between logarithmic and exponential forms. For a, x, and y, with a and x greater than 0, and a not equal to 1, log base a of x is equal to y is equivalent to a to the y is equal to x. Notice here that the answer to the logarithm, namely y, is the exponent that we raise this base to get what we're taking the log of. So matching our equation to the left-hand side here, we have that the base a is equal to 4, x, what we're taking the log of, is equal to 1 over 64, and y, the answer to the logarithm, is equal to negative 3. And therefore, the exponential form would be a, which is 4, raised to the yth power, or the negative third power, is equal to x, or 1 over 64, which would be our answer. And sure enough, 4 to the negative third power, we know, is 1 over 64. All right, what about going in the other direction? Let's rewrite this exponential equation as a logarithmic one. Again, we have this equivalence here, but we'll be starting on the right side now. We'll let a, our base, be equal to 3, our exponent, y, be equal to 4, and our answer, x, be equal to 81. Now writing this in the equivalent logarithmic form gives us that log base a, which is 3, of x, which is 81, is equal to y, which is 4. And this would be our answer. So we use this equivalence here to convert between logarithmic and exponential forms. Thank you, and we'll see you next time. Let's work with the properties of logarithms. For example, given that log x is 3 and log y is negative 2, let's find the log of x to the 5th y cubed and the log of x squared divided by square root of y. And we'll be using the following properties of logs to help us, where here a is any positive base not equal to 1, m and n are positive numbers, and p is any number. So let's begin with the log of x to the 5th y cubed. By this property down here, the logarithm of a product is the sum of the logs. In other words, this is equal to log of x to the 5th plus log of y cubed. And by this last property down here, the logarithm of a power, we can take this power and bring it down in front of the logs. So let's do that to both of these logarithm expressions here. We can bring the 5 down in front here, as well as the 3 down in front here, which gives us 5 times log of x plus 3 times log of y. Now we're given that log x is equal to 3, which we can plug in here, as well as that log y is negative 2, which we can plug in here. Therefore, this is equal to 5 times 3 plus 3 times negative 2, or 15 minus 6, which is 9. All right, and what about this last log we're asked to find? The log of x squared divided by the square root of y. Well, by the second property over here, the logarithm of a quotient is equal to the difference in the logarithms. That is, this is equal to log of x squared minus log of the square root of y. which is equal to log of x squared. And then minus log, and we can rewrite square root of y as y to the 1/2 power. We wanted to write both of these expressions with powers so that we can bring these powers down in front of the log by this logarithm of a power property down here. That is, this is equal to 2 times log of x minus 1/2 times log of y. Again, we can use the fact that log x is equal to 3 and that log y is equal to -2, which gives us 2 times 3 minus 1/2 times -2, or 6 plus 1, which is equal to 7, which is our answer. All right, let's look at another example. Let's compute log base 2 of 24 minus log base 2 of 3. Now, do we know a power that we can raise 2 to get 24, or a power we can raise 2 to get 3? We don't. So we could use a change of base formula on each of these logs separately, but it's going to be much easier if we use these properties of logs. If we look here at this middle property, we can use it in the reverse direction. In other words, we're starting with this, and then we're going to condense it using this property. That is, this is equal to log base 2 of 24 divided by 3, which is equal to log base 2 of 8, which is equal to 3. Since converting to exponential form, we know that 2 cubed is equal to 8. So this would be our answer. And this is how we work with properties of logs. Thank you, and we'll see you next time. Let's evaluate logarithmic expressions. For example, let's evaluate log base 2 of 32. Now we have the following definition of the logarithm, that log base a of x is equal to y if and only if a raised to the y power is equal to x, where a and x are positive and a is not equal to 1. That is, the answer y to a logarithm is the exponent that we need to raise the base to get what we're taking the logarithm of. Let's apply this here. Namely, let's let y equal log base 2 of 32, which is what we're looking for. And by this equivalence over here, this means that the base, namely 2, raised to the answer y, is equal to what we're taking the log of, namely 32. So we have to ask ourselves, what power would we need to raise 2 to get 32? And that power would be 5, wouldn't it? Since 2 to the 5th power is equal to 2 times 2 times 2 times 2 times 2, 5 times, which is equal to 32. Therefore, log base 2 of 32 is 5, which would be our answer. Let's look at another example. Let's evaluate log base 16 of 1/4. Again, we're going to let y be equal to what we're looking for, log base 16 of 1/4. And by our equivalence over here, this means that the base 16 raised to the power y is equal to what we're taking the log of, namely 1/4. Now 16 is a power of 4. In other words, we can rewrite this as 4 squared raised to the yth power, and we can also rewrite 1/4 as 4 raised to the negative first power. By properties of exponents, we can multiply the exponents on the left, so 4 raised to the 2yth power is equal to 4 to the negative first power. And now these bases are equal, which means these exponents are as well, which is a direct result from the fact that exponential functions are one-to-one. That is, 2y is equal to -1, or dividing both sides by 2 gives us that y is equal to -1/2, which would be our answer here. That is, log base 16 of 1/4 is equal to -1/2. Okay, let's look at one more. Let's evaluate log base 27 of 9. Again, we'll let y equal what we're looking for, this log base 27 of 9, and converting to exponential form gives us 27 raised to the yth power is equal to 9. Now both 27 and 9 are powers of 3. In other words, we can rewrite this as 3 cubed raised to the yth power is equal to 3 squared. Again, by properties of exponents, we can multiply the exponents on the left, so we have 3 to the 3y is equal to 3 squared. And again, now that these bases are equal, these exponents will be as well. That is, 3y is equal to 2, or dividing by 3, we get y is equal to 2/3, which means that log base 27 of 9 is equal to 2/3. And this is how we evaluate logarithmic expressions. We convert to the equivalent exponential form. Thank you, and we'll see you next time. Let's look at some examples of solving logarithmic equations. For example, let's solve this equation for x. We can begin by bringing the 8 to the right-hand side, which would give us that log base 5 of x plus 4 is equal to 9 minus 8, or 1. And now writing this in exponential form gives us that 5 raised to the first power is equal to x plus 4. Because remember that log base a of x is equal to y is equivalent to the exponential form a to the y is equal to x, which is what we used here. And now if we subtract 4 from both sides, we get that x is equal to 5 minus 4, or 1. Now, in solving logarithmic equations, it's very important for us to check our answers. So let's do that. Let's check that this value, x equal to 1, satisfies this equation. Namely, is 8 plus log base 5 of 1 plus 4 equal to 9? Or is 8 plus log base 5 of 5 equal to 9? And it is, because log base 5 of 5 is 1, and 8 plus 1 is 9. So yes, it works. Therefore, our answer is x is equal to 1. All right, let's see another example. Let's solve this equation for x. Now we can begin here by condensing the left-hand side into a single logarithm by using the following property. The log of a plus the log of b is equal to the log of the product, a times b. That is, this equation is equivalent to log of x minus 15 times x is equal to 2. And now we can convert this into exponential form again by using this equivalence here. And remembering, though, that log means log base 10. That is, this equation is equivalent to 10 raised to the second power is equal to x minus 15 times x. Or 100 is equal to, and now distributing our x, we have x squared minus 15x. And bringing all the terms to one side gives us that x squared minus 15x minus 100 is equal to 0. And now let's factor the left-hand side. It factors into x minus 20 times x plus 5. And now we have a product of factors equal to 0, which means either the first factor is 0 or the second factor is 0. When the first factor is 0, that means x is equal to 20. And when the second factor is 0, that means x is equal to negative 5. But remember, we have to check these answers. So let's start with x equal to 20. We'll plug it in here and here. So the question is log of 20 minus 15, which is 5, plus the log of 20 equal to 2. Again, we can use this property. So the question is the log of 5 times 20, or log of 100, equal to 2? And it is, because remember, log means log base 10, and 10 squared is indeed 100. So x equal to 20 works. It is a solution. What about x equal to negative 5? Well, that would require us to plug in a negative 5 here, as well as here. Which we can't do, right? Because log of negative 5 minus 15, which is log of negative 20, and log of negative 5 are both undefined. Because remember that the domain of the logarithm is values that are strictly greater than 0. Which means we're going to cross off x equal to negative 5 over here. And therefore, our only answer is x equal to 20. So it's very important to check your answers when solving logarithmic equations. Thank you, and we'll see you next time. Let's look at exponential graphs. For example, let's sketch the graph of f of x is equal to 3 raised to the x minus first power minus 2. And then we're going to find any x or y intercepts of its graph. Let's use graph transformations to help us here. Let's start by sketching y is equal to 3 to the x. So if this is the y-axis, and this is the x-axis, what does y equal 3 to the x look like? Well, it has a y-intercept at 1, and then when x is 1, y is 3 raised to the first power, which is 3. So this is 2, here's 3. So we have the point 1, 3, it lies on the graph. And the exponential function looks like this. Now the x-axis, or y equals 0, is a horizontal asymptote. Now what does this minus 1 do here? What that does is it shifts this graph rigidly 1 unit to the right. That is, the graph of y is equal to 3 to the x minus first power. Looks like this. So here's the y-axis. Here's the x-axis. What's going to happen to this point over here, 0, 1, if we shift our graph 1 unit to the right? This is going to move to 0 plus 1, 1, or 1, 1. And what's going to happen to this point here, 1, 3? It's going to move to 1 plus 1, 3, or 2, 3. Now let's plot these points. This is x equal to 1 and y equal to 1. Here's our point 1, 1. And if this is x equal to 2, y equal to 3, then here's our point 2, 3. And the horizontal asymptote will still remain at y equal to 0, so our graph will look like this. Now what does this negative 2 do to this graph? What that does is it shifts this entire graph rigidly down 2 units. So let's say this is the y-axis, and this is the x-axis. What is going to happen to this point here, 1, 1? It's going to move to 1, and then 1 minus 2, or 1 negative 1. And what's going to happen to this point here? This 2, 3. It's going to move to 2, 3 minus 2, or 2, 1. So let's plot these points over here. Here is x equal to 1, y equal to negative 1. So here's our point, 1, negative 1. And then here's 2. And 1. So here's our point, 2, 1. Now the horizontal asymptote was at y equal to 0, which is also shifting down 2 units, which means that the new horizontal asymptote then will be at y is equal to negative 2. And so our graph looks like this. And let's darken these points we plotted. That is, this is f of x is equal to 3 raised to the x minus first power, and then minus 2. Now we're also asked to find any x or y intercepts of its graph. And looking at our graph, we see that we have a y-intercept here and an x-intercept here. So let's find these intercepts. To find the y-intercept, we set x equal to 0 in our equation. That is, we have y is equal to 3 raised to the 0 minus 1 minus 2, or y is equal to 3 to the negative first power minus 2, or y is equal to 1/3 minus 2, or y is equal to negative 5/3, which would be our y-intercept. That is, coming back over here to our graph, the y-coordinate of this point is negative 5/3. All right, and what about our x-intercept? To find our x-intercept, we set y equal to 0. That is, we have 0 is equal to 3 raised to the x minus first power minus 2, or 3 raised to the x minus first power is equal to 2. And now writing this in the equivalent logarithmic form gives us that log base 3 of 2 is equal to x minus 1. And now adding 1 to both sides gives us that x is equal to log base 3 of 2 plus 1, which would be our x-intercept. That is, the x-coordinate of this point here is log base 3 of 2 plus 1. And this is how we work with exponential graphs. Thank you, and we'll see you next time. Let's look at logarithmic graphs. For example, let's sketch the graph of f of x is equal to 1 plus log base 2 of x plus 3, and then we'll find any x or y-intercepts of its graph. Let's sketch this by using graph transformations. First of all, what does y equal log base 2 of x look like? So let's say that this is the y-axis, and this is the x-axis. Log base 2 of x looks like this, where this x-intercept is 1. And then when x is equal to 2, y is equal to log base 2 of 2, which is 1. Now what does this plus 3 do here? By adding 3 to x, what that does is it rigidly shifts this graph 3 units to the left. So the graph of y is equal to log base 2 of x plus 3 will look like the following. Let's say this is the y-axis, and this is the x-axis. Now, if we're rigidly moving this entire graph 3 units to the left, what's going to happen to this point here, this 1, 0? And what's going to happen to this point here, the 2, 1? Well, 1, 0 is going to move to 1 minus 3, 0, or negative 2, 0. And 2, 1 will move to 2 minus 3, 1, or negative 1, 1. So here's negative 1, negative 2, 0. And if this is 1, then here's the point negative 1, 1. Now remember, we originally had a vertical asymptote here at x is equal to 0. So if we're shifting everything to the left 3 units, then the vertical asymptote will be shifted to x is equal to negative 3. So therefore, log base 2 of x plus 3 will look like this. All right, and finally, what does this plus 1 do here? What that does is it shifts this graph rigidly up 1 unit. So let's say this is the y-axis, and this is the x-axis. Now what is going to happen to this point here, negative 2, 0? it moves to -2, 0 plus 1, or -2, 1. And what happens to this point, -1, 1? It moves to -1, and then 1 plus 1, or 2. Let's say this is -1 and -2, then our vertical asymptote is still at x equal -3. Let's say this is y equal 1 and this is y equal 2. Then -2, 1 is right here, and -1, 2 is right here. And our graph then looks like this. So this is f of x is equal to 1 plus log base 2 of x plus 3. Now we're also asked to find any x or y intercepts. And looking at our graph, we have an x-intercept here and a y-intercept here. So let's find out what these values are. Now to find the y-intercept, we set x equal to 0. That is, we have y is equal to 1 plus log base 2 of 0 plus 3, or y is equal to 1 plus log base 2 of 3. This is the y-intercept. Therefore, the y-coordinate of this point here is 1 plus log base 2 of 3. And what about the x-intercept? To find the x-intercept, we set y equal to 0. That is, we have 0 is equal to 1 plus log base 2 of x plus 3, or subtracting 1 from both sides gives us log base 2 of x plus 3 is equal to -1. And now rewriting this in exponential form gives us 2 raised to the -1st power is equal to x plus 3. Or 1/2 is equal to x plus 3. And then subtracting 3 from both sides gives us x is equal to 1/2 minus 3, or x is equal to -5/2. So this is our x-intercept. That is, the x-coordinate of this point here is -5/2. And this is how we work with logarithmic graphs. Thank you, and we'll see you next time.
Welcome. In this unit, we'll be learning about trigonometry. Trigonometry is the study of angles of triangles. Let's look at the technical definition. Trigonometry is a branch of mathematics that deals with the relationships between sides and angles of triangles and the calculations based on them, particularly involving trigonometric functions. You can think of trigonometry as kind of having 4 components. We want to study both triangles, circles, and the relationships between the angles of these objects. We look at 3 main trigonometric functions, sine, cosine, and tangent, and we want to study oscillatory behavior, as we see in this graph here, the functions that oscillate back and forth. Let's look at a simple example. When you were a kid, you might have had a slinky toy. Well, the slinky toy is a great example of oscillatory behavior. Notice if I take my slinky and bounce it, I get some oscillations. The slinky oscillates back and forth. You can also take the slinky and make some waves. When I make waves with my slinky, that's another example of oscillatory behavior. Notice that the polynomials we've been studying so far won't be able to account for this type of behavior. Polynomials can have some wiggles to them, but eventually they either tend to infinity or minus infinity. So we need some sort of function with periodic behavior. By periodic, I mean it oscillates with time and does the same thing over and over again forever and ever. We're not going to play with this slinky forever, though. Let's look at the correspondence between circles and triangles. You might not think these two things have a lot in common. If we consider a circle of radius r, and we can think of a point on the circle with coordinates x, y, we could create a triangle from this circle by dropping a perpendicular from the point x, y onto the x-axis. Then we have the triangle labeled as you see here. This is often called the unit circle when I replace that radius with 1. So take the circle I had before, replace the radius with 1, we get a unit circle, and we call the angle that radial line makes with the x-axis an angle theta. Theta is just a Greek letter that we often use for angle. There's nothing special about the letter theta. It's just a convenient way to let people know we're talking about an angle there. If we just look at the triangle from this picture, we can think about, well, how would we determine what theta was if we knew some of the sides from that right triangle? So with my right triangle, I have three kind of main sides to the triangle. There's the hypotenuse, the side opposite the right angle. There's the adjacent side, the side next to the angle I'm interested in, theta, and the opposite side, the side on the opposite side of the triangle from theta. This brings us to those trigonometric functions we mentioned before. We have three main trigonometric functions we'll talk about. That's the sine, the cosine, and the tangent. These three functions can be related to the right triangle via the relationship that the sine is the opposite side over the hypotenuse, the cosine is the adjacent side over the hypotenuse, and the tangent of an angle is the opposite side over the adjacent. A lot of students like to use the mnemonic SOHCAHTOA to help you remember this. SOHCAHTOA basically is so, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and TOA, tangent is opposite over adjacent. Let's take some more look at these trigonometric functions. Well, we said that this triangle was also related to the unit circle, or any circle for that matter. The unit circle is just a special circle with radius 1. On that unit circle, there's several angles that we study a lot because these are values that we can evaluate explicitly for a circle. So those points x, y on the circle that are interesting or we know the values of would be things going from the x-axis along the unit circle to angles like 30 degrees, 45 degrees, 60 degrees, 90 degrees, etc. These special angles are just values for which the x, y coordinates on the unit circle are easy to find. Well, we don't always work with degrees in mathematics when we're looking at trigonometric functions. We also work with something called radians. Most of you probably know a circle has 360 degrees. What you may not know is that we also can say a circle has 2 pi radians. The relationship between degrees and radians is simply that 360 degrees equals 2 pi radians. So in these two circles, I'm just depicting the degree value and radian value of some key angles on the unit circle. We can also look at the trigonometric values of the trig functions at those key angles. So for example, I could make a table of my sine, cosine, and tangent with those angles theta as the input. Notice here we have some values. By the end of this course, you definitely want to memorize this table. It takes a little bit of work, but it will be worth it, particularly when you get to calculus. Being a master of trig values is super important. Notice on this table I snuck in 3 extra functions. I haven't talked much about these 3 extra trigonometric functions because they're basically directly related to the ones you already know, sine, cosine, and tangent. The cosecant is 1 over sine, the secant of theta is 1 over cosine, and another trig function, the cotangent, is 1 over the tangent or cosine over sine. Let's look at our 3 main trig functions. I said that they correspond to oscillatory behavior or an oscillating function. Just looking at a triangle, it may not be clear to you that those are oscillatory functions. But basically, as I change an angle, theta, and input it into this function, I get differing values, and these values repeat with time. Each of these functions has what we call a characteristic period, or the amount of time before that function repeats again. Up on this graph, you see our sine, our cosine, and our tangent graphs. You'll be working with these more in future units. Another thing that you'll be learning a lot about is trig identities. Trig identities are basically relationships between our trig functions that help us solve equations and manipulate expressions involving the trig functions. There's quite a few of these. Many of them you'll want to memorize. Some of them you'll want to make sure you know how to derive or figure out what the relationship between these quantities is. You'll be spending a lot of time working with trig identities. One trig identity you may have already seen is Pythagorean theorem. You may have seen this in a geometry course. The Pythagorean theorem says that a squared plus b squared equals c squared. If you remember what that means, for a triangle, one side squared plus the other side squared gives you that hypotenuse squared. The way we say this with trig functions is sine squared plus cosine squared equals 1. This is just an example to give you a flavor for what these trig identities are all about. They're relationships between your trig functions that give you an expression that might be helpful in evaluating some sort of equation. In this unit, you're going to learn several things about trigonometric functions. First of all, you're going to learn how to work with angles, convert back and forth between degrees and radians, and figure out which angle are you talking about. Do you want the smaller acute angle or the larger obtuse angle when you're drawing these pictures? You'll also learn how to utilize right triangles and the unit circle to find angles and lengths in triangles and points on the circle. Finally, you're going to evaluate and graph trig functions and use those trig identities that we talked about. You'll solve trig equations, and most importantly, you'll learn to use trigonometry to solve real-world applications. What might those real-world applications be? Well, applications of trigonometry include things like astronomy. Trigonometry was actually first developed to help talk about astronomy problems. They wanted to figure out things like where bodies were going to be in the sky at different periods of time, and that involves a lot of triangles. If you think about it, if I know the planet was here one day and up there the next, I'm making some sort of angle that I can use trigonometry to deal with. Other things include geography, optics, architecture, mechanics, seasonal phenomena, anything that changes with time in some sort of oscillatory behavior, like the seasons or the temperature as a function of time throughout the year, is something that might be suitable for study with trig functions. Signal processing is another very popular area to use trigonometry with, because most signals you can think of as waves, and studying those waves involves trig functions. Well, I hope you enjoy learning about trigonometry. Thank you, and we'll see you next time.
Let's convert between degrees, minutes, seconds, and degrees. For example, let's convert 5 degrees, 13 minutes, and 11 seconds to degrees. 1 degree can be divided into 60 parts called minutes. And this notation here means minutes. And these minutes are further divided into 60 parts called seconds. And this notation here means seconds. And it should be pointed out that the words minute and second used in this context have no immediate connection to how these words are usually used as amounts of time. So we have the following, that 1 degree is equal to 60 minutes and 1 minute is equal to 60 seconds. Well, if 1 minute is equal to 60 seconds, then how many seconds does 60 minutes equal? This would be 60 times 60, or 3,600 seconds. But isn't 60 minutes also just equal to 1 degree? Which means we have 1 degree is equal to 3,600 seconds as well. Now if we divide both sides of this equation by 60, we get that 1 minute is equal to 1 divided by 60 degrees. And if we divide both sides of this equation by 3600, we get that 1 secant is equal to 1 divided by 3600 degrees. And these are the equations that we'll be using to help us convert here to degrees. Namely, this is equal to, what this means is 5 degrees plus 13 minutes plus 11 seconds. So we need to know how many degrees are in 13 minutes and in 11 seconds to convert this to degrees. Namely, this is equal to 5 degrees plus 13 times the number of degrees in 1 minute. And looking over here, we know that there's 1 divided by 60 degrees in 1 minute. Plus 11 times the number of degrees in 1 second. And looking over here, we have that 1 second is 1 divided by 3600 degrees. And if we do these divisions in our calculator, we'll get that this is equal to 5.21972 repeating degrees, which would be our answer. Let's look at going the other way. Let's convert 41.795 degrees to degree, minute, second form. Let's start off by rewriting 41.795 degrees as 41 degrees plus 0.795 degrees. In other words, we're splitting off the whole number part of this degree measure. And now what we want to do is convert this decimal part of the degree measure to minutes and seconds. So remember, we have that 1 degree is equal to 60 minutes. Therefore, this is equal to 41 degrees plus 0.795 times the number of minutes in 1 degree, which is 60 minutes. And this product here turns out to be equal to 47.7. Therefore, this is equal to 41 degrees plus 47.7 minutes. And now let's break off the whole number portion of these minutes. In other words, we'll rewrite it as 47 minutes plus 0.7 minutes. And now we'll want to convert this decimal portion of the minutes to seconds. And we can do so by remembering that 1 minute is equal to 60 seconds. Therefore, this is equal to 41 degrees plus 47 minutes plus 0.7 times the number of seconds in 1 minute, which is 60. And this product here is 42. Therefore, this is equal to 41 degrees plus 47 minutes plus 42 seconds, which we write 41 degrees, 47 minutes, 42 seconds, which would be our answer. And this is how we convert between degree, minute, seconds, and degrees. Thank you, and we'll see you next time. Let's look at converting between degrees and radians. For example, let's convert 120 degrees to radian measure in terms of pi. Now we have the following conversion formulas, that 1 degree is equal to pi over 180 radians, and 1 radian is equal to 180 divided by pi degrees. Before applying these, though, let's take a minute to think about why they're true. Let's think of a unit circle that is a circle with radius 1. Remember that the radian measure of this angle here is the length of this corresponding arc. So what would the radian measure be of one full rotation? Wouldn't that be the length all the way around this unit circle? That is the circumference of this circle, which is 2 pi times the radius, which is 1. Therefore, one rotation measures 2 pi radians. And what is the degree measure of one full rotation? Isn't that 360 degrees? So regardless of what measure we use to measure one full rotation, the measure has to be the same. That is, 2 pi radians is equal to 360 degrees, or dividing both sides by 2, we get pi radians is equal to 180 degrees. And if we divide both sides of this equation by pi, we'll get the second conversion here. And if we divide both sides by 180, we'll get the first conversion here. And we'll use this first equation when we convert from degrees to radians. And we'll use the second equation when we convert from radians to degrees. So here we're asked to convert from degrees to radians, so we'll be using this first conversion here. That is, 120 degrees is equal to 120 times the radian measure of 1 degree, which is pi divided by 180 radians. And both 180 and 120 are divisible by 60, so we'll be left with a 2 here and a 3 here. That is, the radian measure of 120 degrees is 2 pi divided by 3 radians. And sometimes when we measure in radians, the word radians will be dropped and we just write 2 pi divided by 3. All right, let's see another example. Let's convert negative 5 pi divided by 4 radians to degree measure. Again, we have the following conversions, but since we're going from radians to degrees, we're going to be using the second one now. That is, negative 5 pi over 4 radians is equal to negative 5 pi over 4 times 1 radian is 180 divided by pi degrees. And then the pi's will cancel. And 4 goes into 180 45 times. Therefore, this is equal to negative 5 times 45, or negative 225 degrees, which would be our answer. And this is how we convert between degree and radian measure. Thank you, and we'll see you next time. Let's look at coterminal angles. For example, let's find an angle between 0 and 2 pi that is coterminal with negative 11 pi divided by 6. Now, two angles are coterminal if they share the same initial and terminal sides. So let's sketch our angle here in standard position. Now, an angle is in standard position when its initial side is on the positive x-axis. And because our angle here is negative, That means that we're going to start rotating in the clockwise direction. But how far are we going to go? Well, one complete revolution in the clockwise direction measures negative 2 pi. Now, how many sixths is negative 2 pi? Isn't that negative 12 pi divided by 6? Which means that our angle here, negative 11 pi over 6, didn't quite make it there. Because 11 is smaller than 12, which means we're pi 6 short of negative 2 pi or negative 12 pi 6. So here's our angle, negative 11 pi over 6. Therefore, the angle that we're looking for between 0 and 2 pi that has the same initial and terminal side as theta is this angle here, pi divided by 6, which would be our answer. Another way to think about it is if we add or subtract 2 pi radians from theta, then we're going to land on an angle that has the same terminal side, and hence will be coterminal with theta. Specifically, pi divided by 6, which is our answer, is equal to theta, or negative 11 pi over 6, plus 2 pi. All right, let's look at another one. Let theta equal 600 degrees. We'll first find an angle between 0 and 360 that is coterminal with theta, and then we'll find an angle between 0 and negative 360 that's also coterminal with theta. Again, let's sketch theta in standard position. Its initial side will be the positive x-axis. And because this angle here is positive, we're going to start rotating in the counterclockwise direction. But how far do we go? Well, one complete revolution measures 360 degrees. So if we go another 180 degrees, where are we? Well, 360 degrees plus 180 degrees is equal to 540 degrees. So this angle here would be 540 degrees. Well, we want to get to 600 degrees, which means we're 60 short, because 540 plus 60 is this 600. Which means we'll need to go another 60 degrees in the counterclockwise direction to get to 600 degrees. Namely, we go one full revolution, then we go another half, then we go 60 more. So this would be 600 degrees here. All right, so we're first looking for an angle between 0 and 360 degrees that is coterminal with this angle. Wouldn't that just be this angle here? Which would be 180 degrees plus 60 degrees, or 240 degrees. Both of these angles have the same initial and terminal sides, and moreover, 240 degrees is between 0 and 360 degrees. So 240 degrees would be our answer to part A. Now we still need to find an angle between 0 and negative 360 degrees that is coterminal with theta. And with negative measured angles, we go counterclockwise from the initial side. So wouldn't that be this angle here, which is negative 120 degrees? Because a quarter turn in the clockwise direction measures negative 90 degrees, and then we have to go 30 more. So that would be negative 120 degrees. So our answers here then would be 240 degrees and negative 120 degrees. And this is how we find coterminal angles. Thank you, and we'll see you next time. Let's look at reference angles. For example, let's find the reference angle for theta equal 5 pi divided by 6. Now, the reference angle is the acute positive angle formed by the terminal side of theta and the x-axis. So looking here, 5 pi over 6 is here. And then this here is the reference angle. It's the acute angle formed by the terminal side of theta and the x-axis. So what is this acute angle? Well, this angle here measures pi radians, and we can think of pi as 6 pi divided by 6, which means our angle 5 pi over 6 is pi over 6 units short of pi. So our reference angle is equal to pi minus 5 pi over 6, or 6 pi over 6 minus 5 pi over 6, which is pi divided by 6. Therefore, the measure of this angle then, or a reference angle, is pi divided by 6. All right, let's look at another example. Let's find the reference angle for theta equal to negative 156 degrees. Well, here is negative 156 degrees, and this angle here is the reference angle, or the acute angle, formed from the terminal side of the angle and the x-axis. Now this angle here measures negative 180 degrees. So negative 156 degrees didn't quite reach negative 180 degrees. So how much was it short? Well, since 180 minus 156 is equal to 24 degrees, then this reference angle is this positive acute measure here, which would be our answer. All right, let's look at one more. Let's find the reference angle for theta equal to 17 pi divided by 9. So here is 17 pi divided by 9. That is, it's almost one complete revolution. And remember, the radian measure of one complete revolution is 2 pi radians, or thinking of that in terms of ninths, it's 18 pi divided by 9, isn't it? So 17 pi divided by 9 is 1/9 short of one complete revolution. That is, this reference angle here we're looking for then is pi divided by 9. Because 2 pi minus 17 pi divided by 9 is equal to 18 pi divided by 9 minus 17 pi divided by 9, which is pi divided by 9. So the reference angle then is simply the acute angle formed by the terminal side of theta and the x-axis. Thank you, and we'll see you next time. Let's learn how to sketch an angle in standard position. For example, let's sketch theta is equal to 2 pi divided by 3 in standard position. Let's begin by drawing a unit circle here. So let's say this is the y-axis. And this is the x-axis. So a unit circle is a circle of radius 1, which means this is the point 1, 0. Now an angle is in standard position if its initial side is on the positive x-axis. Now if theta is greater than 0, we rotate in the counterclockwise direction. And if theta is less than 0, then we rotate in the clockwise direction. And since our angle here, theta, 2 pi divided by 3, is greater than 0, we're going to be rotating in the counterclockwise direction. But where do we stop? Well, one complete rotation measures 2 pi radians. Because remember that the radian measure of an angle is defined as the length of the corresponding arc on the unit circle. And since the circumference of the unit circle is 2 pi, then the radian measure of one complete revolution is 2 pi radians. And therefore, half of a rotation would measure pi radians. Which means looking over here on the left, if we started rotating our initial side all the way to here, this would be pi radians. And how many thirds is pi? Isn't that 3 pi thirds? That means our angle here didn't quite get there. We're pi thirds short of it. In other words, 2 pi divided by 3 is equal to 3 pi divided by 3, which is pi, minus pi thirds. So therefore, our angle is here. 2 pi divided by 3. And this here is pi thirds. Not in standard position, of course, but the measure of that angle is pi thirds. Another way to think about it here's the initial side. This would be pi thirds. That's 1 pi third. This is 2 pi thirds. This is 3 pi thirds. So this is our angle we're looking for. All right, let's look at another example. Let's sketch this angle here. Theta is equal to negative 5 pi divided by 4 in standard position. Again, we'll begin by drawing a unit circle. So here's the initial side on the positive x-axis. And because our angle up here is less than 0, we're going to be rotating in the clockwise direction. But again, where do we stop? So remember that 1/2 of a rotation measures negative pi radians in the clockwise direction. And how many fourths is negative pi? Isn't that negative 4 pi fourths? Which means we need to keep going. We have to go negative pi fourths more. So this would be the angle here, negative 5 pi over 4. Because negative 5 pi over 4 is equal to negative 4 pi over 4 minus pi over 4. Or another way to think of it is to count off multiples of negative pi over 4. So this is 1 times negative pi over 4. This is 2 times negative pi over 4. This is 3 times negative pi over 4. This is 4 times negative pi over 4. And this is 5 times negative pi over 4, which is our angle. And so sketching it in standard position, this is the initial side, and this is the terminal side. So our angle, negative 5 pi over 4, is here. And this is how we sketch an angle in standard position. Thank you, and we'll see you next time. Let's look at trig values of special angles. For example, let's find the exact value of sine of 2 pi divided by 3. Now the sine of theta is equal to the y-coordinate of the point of intersection of the terminal side of the angle and the unit circle. So we need to find the point where the terminal side of this angle here, 2 pi divided by 3, intersects the unit circle. That is, we need to find this point here. Now, since 2 pi over 3 is in quadrant 2, its reference angle here is pi minus 2 pi over 3, which is equal to pi over 3, or 60 degrees. So we can form this triangle shown here. It's a 30, 60, 90 triangle with hypotenuse equal to 1. Remember, the radius of the unit circle is 1. Therefore, the side adjacent to the 60-degree angle has length 1/2, and the side opposite the 60-degree angle will have length square root of 3 over 2. And let's recall why this is true. So let's draw an equilateral triangle here with side lengths equal to 1. Now the angles here are 60 degrees. And then we can split this equilateral triangle into 2 congruent 30, 60, 90 triangles by dropping this perpendicular bisector here. That is, we can form these 2 triangles here. If the total measure of this top angle here was 60 degrees, then each of these is 30 degrees. This is still 60. This is still 60. This still has length 1. This still has length 1. But then this bottom side has been split into 2 pieces of equal length. So this has to be 1/2, and this has to be 1/2. So the question is, what is the length here, z, of that side of each of those triangles? Well, let's look at this right triangle here. By the Pythagorean theorem, we have that z squared plus 1/2 squared is equal to the hypotenuse squared. Or z squared is equal to 1 minus 1/2 squared, which is 1/4. Or z squared is equal to 3/4, which means that z is equal to plus or minus the square root of 3 over 4, which is plus or minus the square root of 3 divided by 2. But z here is the length of a side of this triangle, and so we're going to choose the positive value here. So this z then is square root of 3 over 2. That is, this right triangle here is the triangle we see here. So this distance is square root of 3 over 2, and this distance is 1/2. Now remember that xy is in quadrant 2, which means the x-coordinate has to be negative. So this point then is negative 1/2, and the y-coordinate is positive, so the y-coordinate is square root of 3 over 2. And therefore, like we said earlier, the sine is the y-coordinate of the point of intersection of the terminal side of the angle and the unit circle. So it's this y-coordinate here. That is, this is equal to the square root of 3 divided by 2. All right, let's look at another example. Let's find the exact value of cosine of negative 7 pi over 4. Now the cosine of theta is the x-coordinate of the point of intersection of the terminal side of the angle and the unit circle. Which means we need to find the point where the terminal side of this angle here, negative 7 pi over 4, intersects the unit circle. That is, we need to find this point here. And since negative 7 pi over 4 is here in quadrant 1, its reference angle here is 2 pi minus 7 pi over 4, which is pi over 4, or 45 degrees. And so we can draw this triangle shown. It is a 45, 45, 90 triangle with hypotenuse equal to 1. And therefore, the lengths of the other two sides are both square root of 2 over 2. Again, let's think about why this is true. If you recall from geometry, when you have a 45, 45, 90 triangle, it forms an isosceles triangle. So let's call this Z and this Z. Both of these lengths are equal. And by the Pythagorean theorem, we get Z squared plus Z squared is equal to 1, or 2Z squared is equal to 1, which means Z squared is equal to 1/2, or Z is equal to plus or minus the square root of 1/2, which is equal to plus or minus the square root of 2 over 2 if we rationalize the denominator. But since Z represents these two lengths here, then we're going to choose the positive value here. That is, Z here is square root of 2 over 2. Same here, this is square root of 2 over 2. Which is how we get that triangle there. All right, so therefore this point here is square root of 2 over 2, square root of 2 over 2. And like we said earlier, remember that the cosine of theta is the x-coordinate, the point of intersection of the terminal side of the angle and the unit circle. And that's this point here, so the x-coordinate is here, which would be our answer. This is equal to square root of 2 over 2. Now, angles whose radian measure are multiples of either pi over 6 or pi over 4, like these two examples here, are called common trigonometric angles. This first circle here shows the multiples of pi over 6. This is 1 times pi over 6. This is 2 times pi over 6, or pi over 3. This is 3 times pi over 6, or pi over 2. And then look, 4 pi divided by 6, or 2 pi over 3, was our first example. And remember, we found this point. And then this second circle here shows us the multiples of pi over 4. And remember, the angle we saw in our last example was negative 7 pi over 4, which is coterminal with pi over 4. And we found this point here. Now, rather than having to derive the x and y coordinates of these points each time, like we did in our examples, you're going to want to memorize these circles. And really, if we just memorized these 1, 2, 3 points, then because of the symmetry of the unit circle, it's easy to find the other ones by affixing the appropriate sign in front of the numbers. For example, here, we know that this point that corresponds to pi over 6 is square root of 3 over 2 1/2. By the symmetry of the unit circle, then this angle here, 5 pi over 6, also has these same values, square root of 3 over 2 1/2, but we put a negative on the x coordinate because x is negative in quadrant 2. So it will be to your benefit to memorize these circles. All right, and this is how we find common trigonometric values. Thank you, and we'll see you next time. Let's learn about right triangle trigonometry. For example, let's find sine theta, cosine theta, and tangent theta, where theta is the angle shown in this triangle here. Now, whenever we have a right triangle, and one of the other angles is known, then that determines the other angle, because all the angles have to add up to 180 degrees, which means this other angle here would have to be 90 degrees minus theta. Therefore, the shape of the triangle is completely determined, except for similarity, by the angles. So once the angles are known, the ratios of the sides are determined regardless of the overall size of the triangle. And we have names for these ratios. But before stating what these ratios are, let's label or give names to these sides of this triangle here. So the side that's across from theta, or opposite theta, I'm going to label as opposite. The side across from the right angle is called the hypotenuse. And the third side next to theta, or adjacent to theta, we call the adjacent side. And now we're ready to name these ratios. So we have that the sine of theta, sin is short for sine, is equal to the opposite side divided by the hypotenuse. The cosine of theta, and cos is short for cosine, is equal to the adjacent side divided by the hypotenuse. And the tangent of theta, tan is short for tangent, is equal to the opposite side divided by the adjacent side. Now there's a mnemonic that is commonly used to help us remember these ratios. And the mnemonic is as follows. It's SOHCAHTOA. The S here stands for sine. The O stands for opposite. And the H stands for hypotenuse. So looking down here, we have S, O, and H. That is, the sine of theta is opposite over hypotenuse. Now the C here in C stands for cosine. The A stands for adjacent. And the H stands for hypotenuse. So looking down here, cosine C is equal to adjacent A divided by hypotenuse H. So this is adjacent divided by hypotenuse. And finally, with the TOA, the T stands for tangent. The O stands for opposite. And the A stands for adjacent. So coming down here, we have T for tangent, O for opposite, and A for adjacent. So this is opposite over adjacent. So now with this background information, we can solve our problem. We can now find sine of theta, cosine theta, and tangent of theta. Looking here, here's theta, which means this 3 is the opposite, or O. This 4 is the adjacent, or A. But what's the hypotenuse, H? Well, the hypotenuse we can find by using the Pythagorean theorem. Namely, 3 squared plus 4 squared is equal to the hypotenuse squared. Or 9 plus 16 is the hypotenuse squared. Or 25 is the hypotenuse squared. Which means the hypotenuse then would be the square root of 25, or 5. Therefore, coming back over here to these ratios, the sine of theta is equal to opposite over hypotenuse, which is equal to, in this case, 3 divided by 5. And the cosine of theta is equal to the adjacent over hypotenuse, which is equal to 4 divided by 5. And finally, the tangent of theta is equal to opposite over adjacent, which is equal to 3 divided by 4. So these would be our 3 answers here. By the way, the word trigonometry comes from the Greek words meaning triangle and measure, and you should see why now. All right, let's look at another example. Let's find x and y in this figure here. Well, let's start by labeling our given angle, theta. And this number 4 here is the length of the side opposite theta, so let's label it O. And y down here is the length of the side that's adjacent to theta, so we'll label it A. And x up here is the hypotenuse, so we'll label it H. So by what we just learned, the sine of theta, or the sine of 30 degrees, is equal to opposite over hypotenuse, which is equal to 4 divided by x. The cosine of theta, or the cosine of 30 degrees, is equal to adjacent divided by hypotenuse, which is equal to y divided by x. And the tangent of 30 degrees is equal to opposite divided by adjacent, which is equal to 4 divided by y. Now we can use this first equation to solve for x. So we have sine of 30 degrees, which is 1/2, is equal to 4 divided by x. And then cross-multiplying, this gives us that x is equal to 2 times 4, or 8. Now to solve for y, we can use either of these last 2 equations. That is, we could use this middle equation. So cosine of 30 degrees is square root of 3 divided by 2 is equal to y divided by x, but we just found that x was equal to 8. And cross multiplying will give us that y is equal to 8 square root of 3 divided by 2, which is 4 square root of 3. Now this computation, though, required that we knew what this value of x was. If we use this third equation, though, we didn't need to know what x was. Because tangent of 30 degrees is 1 divided by square root of 3, and this is equal to 4 divided by y. And then cross multiplying, we'd get to our same answer of y is equal to 4 times square root of 3. And this is how we work with these trig ratios. Thank you, and we'll see you next time. Let's look at right triangle word problems. For example, a ladder leans against the side of a house. If the angle of elevation of the ladder is 69 degrees when the bottom of the ladder is 16 feet from the side of the house, let's find the length of the ladder. So let's let x equal that length. So looking over here in our figure, this is x then. Now, how are we going to solve for x? Well, we have a right triangle here. And 16 here is the side adjacent to the given angle, and x here is the hypotenuse. And therefore, the cosine function can help us, because remember, cosine of theta is equal to adjacent divided by hypotenuse. So for our triangle here, that means that cosine of 69 degrees is equal to, the adjacent is 16, and the hypotenuse is x. Which means that x is equal to 16 divided by cosine of 69 degrees. And plugging this into our calculator, we get that this is approximately 44.7 feet. Let's look at another example. A kite flying in the air has a 91-foot line attached to it, and the line is pulled taut. The angle of elevation of the kite is 63 degrees. Find the height of the kite. So let's let x equal the height of the kite. That is, looking in our figure here, this is x. So we have a right triangle, and x here is the side that's opposite this angle of 63 degrees. And 91 here is the hypotenuse of the triangle. So which trig function is going to help us here? Wouldn't that be sine? Because sine of theta, remember, is equal to opposite divided by hypotenuse. So in our situation, we have sine of 63 degrees then is equal to opposite is x, hypotenuse is 91, which means that x is equal to 91 times sine of 63 degrees. And putting this in our calculator gives us that this is approximately 81.1 feet. All right, and these are a few examples of right triangle word problems. Thank you, and we'll see you next time. Let's find trigonometric values given a point on the unit circle. For example, let's suppose that theta is an angle in standard position whose terminal side intersects the unit circle at negative 21 over 29, negative 20 over 29. Let's find the exact values of sine of theta, tangent of theta, and cosecant of theta. Now we define the trigonometric functions in terms of coordinates of points on the unit circle as follows. Suppose that theta is an angle in standard position whose terminal side intersects the unit circle at xy. Then the 6 trigonometric functions are defined as follows. Sine of theta is equal to the y-coordinate, cosine of theta is equal to the x-coordinate, tangent of theta is equal to y divided by x, cosecant of theta is equal to 1 divided by y, secant of theta is equal to 1 divided by x, and cotangent of theta is equal to x divided by y. Now these definitions are consistent with the right triangle trigonometric ratios that you might be used to. To see this, suppose that theta is acute, like the angle shown here. Let's drop a perpendicular from the point xy to the x-axis. Now this length then is y, and this is x, and remember the radius of this circle is 1, so this length is 1. Using our trig ratios, we have that sine of theta is equal to opposite over hypotenuse, which is equal to y divided by 1, or y, which looking over here, isn't that what this says? That the sine of theta is equal to y? And cosine of theta is equal to adjacent divided by hypotenuse, which is equal to x divided by 1, which, looking over here, is exactly what this says. And we can validate the other 4 equations in a similar way. Okay, so let's apply this to our situation here. We're given that x is equal to negative 21 divided by 29, and y is equal to negative 20 divided by 29, as shown in this figure here. So let's use this definition to find sine of theta, tangent of theta, and cosecant of theta. Namely, sine of theta is equal to the y-coordinate of this point, which is negative 20 divided by 29, and tangent of theta is equal to the y-coordinate divided by the x-coordinate, which is equal to negative 20 divided by 29 divided by negative 21 divided by 29, which is equal to, the 29s will cancel as well as the negatives, and we get 20 divided by 21. And finally, cosecant of theta is equal to 1 divided by y, which is equal to 1 divided by negative 20 over 29, which is equal to negative 29 divided by 20. So these are the 3 values that we were looking for: sine of theta, tangent of theta, and cosecant of theta. All right, let's look at another example. Suppose that theta is an angle in standard position whose terminal side intersects the unit circle at 3/4 negative square root 7 divided by 4. Let's find the exact values of cosine of theta, cotangent of theta, and secant of theta. Again, we're going to use the following definition, but now we're going to find cosine of theta, cotangent of theta, and secant of theta. So we're given that the terminal side of theta intersects the unit circle at 3/4 negative square root 7 over 4, as shown in the figure here. Therefore, the x-coordinate of this point is 3/4, and the y-coordinate is negative square root 7 divided by 4. Therefore, cosine of theta is equal to the x-coordinate, or 3 divided by 4. And cotangent of theta is equal to the x-coordinate divided by the y-coordinate, which is equal to 3/4 divided by negative square root of 7 divided by 4. And the 4's will cancel, which leaves us with negative 3 divided by the square root of 7, which we then can rationalize, which leaves us with our answer of negative 3 square root of 7 divided by 7. And finally, the secant of theta is equal to 1 divided by the x-coordinate, or 1 divided by 3/4, which is equal to 4/3. So these are the three values we're looking for. Cosine of theta is 3 divided by 4. Cotangent of theta is negative 3 square root of 7 divided by 7. And secant of theta is 4 divided by 3. And this is how we find trigonometric values given a point on the unit circle. Thank you, and we'll see you next time. Let's look at trig values given information about the angle. For example, let 12, negative 5 be a point on the terminal side of theta. Find the exact values of cosine of theta, cosecant of theta, and tangent of theta. Now, the first thing to notice is that this point here, 12, negative 5, does not lie on the unit circle. Because in order for a point to lie on the unit circle, x squared plus y squared has to be equal to 1. But looking here, we have 12 squared plus negative 5 squared is equal to 144 plus 25, which is equal to 169, which is not 1. Therefore, we cannot use the unit circle definition of the trig functions, but there is an equivalent one. That is, if xy is the point of intersection of the terminal side of the angle and a circle of radius r, then the sine of theta is equal to y divided by r, cosine of theta is equal to x divided by r, tangent of theta is y divided by x, cosecant of theta is r divided by y, secant of theta is r divided by x, and cotangent of theta is x divided by y. And we're assuming here that r is greater than 0, or that xy is not the origin. So in our case, we have that xy is equal to 12, negative 5, as shown in this figure here. So we'll find r by using this formula here. Namely, r is equal to the square root of x squared, which is 12 squared, plus negative 5 squared, or the square root of 144 plus 25, which is equal to the square root of 169, which is equal to 13. So let's write that on the graph up here. R is equal to 13. And now that we know r, we can find these three values here by using this equation, and this equation. That is, cosine of theta is equal to x divided by r, which is equal to 12 divided by 13. Cosecant of theta is equal to r divided by y, which is equal to 13 divided by negative 5, or negative 13 over 5. And tangent of theta is equal to y divided by x, or negative 5 divided by 12, which is negative 5/12. Let's look at another example. Let negative 3 square root of 7 be a point on the terminal side of theta, and let's find the exact values of sine of theta, secant of theta, and cotangent of theta. Again, our given point here does not lie on the unit circle because negative 3 squared plus the square root of 7 squared is equal to 9 plus 7, which is 16, which is not equal to 1. Therefore, we cannot use the unit circle definitions of the trig functions. So we're going to use these definitions instead. And here we have that xy is equal to negative 3 square root of 7, as shown in this figure here. So let's find r by using this equation again. Namely, r is equal to the square root of x squared, or negative 3 squared, plus square root of 7 squared, which is equal to the square root of 9 plus 7, which is equal to the square root of 16, or 4. So let's write that here in the figure. This is equal to 4. Now notice in both of these examples, we're basically doing the same work twice. Because looking up here, didn't we already know that r squared was 16? So basically, you would just have to take the square root of that number to get your r each time. All right, now we're ready to find the sine of theta, secant of theta, and cotangent of theta by this formula, and this formula. That is, sine of theta is equal to y divided by r, which is equal to the square root of 7 divided by 4. Secant of theta is equal to r divided by x, which is equal to 4 divided by negative 3, or negative 4/3. And finally, cotangent of theta is equal to x divided by y, which is equal to negative 3 divided by the square root of 7, which we then can rationalize. Which would give us negative 3 divided by square root of 7 times square root of 7 over square root of 7, or negative 3 square root 7 divided by 7. And this is how we find trigonometric values given information about the angle. Thank you, and we'll see you next time. Let's find trigonometric values given information about the angle. For example, let theta be an angle such that cosine of theta is equal to negative 4 divided by 5, and sine of theta is greater than 0. Let's find the exact values of the other 5 trigonometric functions. Now, since cosine of theta is equal to negative 4 divided by 5, in other words, cosine of theta is negative, then theta is either in quadrant 2 or quadrant 3. Because cosine values are negative in those two quadrants. However, we're also told that sine of theta is greater than 0. And sine values are not positive in quadrant 3, which means we can conclude that theta is in quadrant 2, and we can draw the following reference triangle. Because remember our trigonometric function definitions here. Cosine of theta by definition is x divided by r. And we're given that this ratio is equal to -4 divided by 5. And notice over here in the figure that we're putting the negative with the x, because x's are negative in quadrant 2 and r is always positive. Now we'll need to find y here before we start computing these values down here. Sine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. Although really the secant of theta doesn't involve y, but the other four do. And we can find y by using the Pythagorean theorem. Namely, x squared plus y squared is equal to r squared, or -4 squared plus y squared is equal to 5 squared, or 16 plus y squared is equal to 25, and subtracting 16 from both sides gives us that y squared is equal to 9, which means y is equal to plus or minus the square root of 9, or plus or minus 3. The question is, which value do we choose, plus or minus? And we're going to choose the positive value here because y's are positive in quadrant 2. So let's mark that on the figure here. Y here is equal to 3. And now we're ready to find our other 5 trig values. So sine of theta is equal to y divided by r, which is equal to 3 over 5. Tangent of theta is equal to y divided by x, which is equal to 3 divided by -4, or -3/4. And cosecant of theta is equal to r divided by y, which is equal to 5 divided by 3. And secant of theta is equal to r divided by x, which is equal to 5 divided by -4, or -5/4. And finally, cotangent of theta is equal to x divided by y, which is -4 divided by 3, or -4/3. And this is how we find trigonometric values given information about the angle. Thank you, and we'll see you next time. Let's look at inverse trigonometric values. For example, let's find the exact value of inverse cosine of 1/2. Now be very careful here with this notation. This does not mean 1 divided by cosine x. This is just the notation for the inverse cosine function. If we meant this, we would have written cosine x to the -1 power. And by the way, there's another notation for the inverse cosine function that avoids this ambiguity. Inverse cosine of x and arc cosine of x mean the same thing. But this inverse cosine with the -1 here, this notation is more common. So what does this mean, inverse cosine function? If we think of the graph of cosine, this here is pi halves, this is pi, this is 3 pi halves, and so on. Over here is negative pi halves. This is negative pi. This is negative 3 pi over 2, and so on. Cosine is not a one-to-one function, is it? This is the graph of y is equal to cosine x. And remember that in order for a function to have an inverse, it must be one-to-one. So in order to discuss this function here, this inverse cosine function, what we do is we restrict the domain of cosine. And if we restrict the domain of cosine to the interval 0 to pi, for example, then cosine will be one-to-one on this interval. So we restrict the domain of cosine to the interval 0 to pi. And remember that the domain of a function is the range of the inverse. So we have the following definitions. We're working with this middle one here, the inverse cosine function. So y is equal to inverse cosine of x means that cosine of y is equal to x. And moreover, y is in this interval. This is a restricted domain of our cosine function, which is the range of our inverse function. So we're thinking backwards now. Our inverse cosine values will be angles. We're used to plugging in angles into the cosine function. Now they're the output. All right, so looking at our problem here, let's set y equal this inverse cosine of 1/2. This is equivalent to cosine y is equal to 1/2, where y is in this interval down here. So thinking of our unit circle, the cosine of this angle here, pi divided by 3, is equal to 1/2, because the x-coordinate of this point is 1/2. But also the cosine of this angle is also equal to 1/2. And this angle is 5 pi divided by 3, because the x-coordinate of this point is also 1/2. And the cosine of any angle coterminal with either of these angles will also be equal to 1/2. However, the only angle in this interval down here is this pi over 3, which would be our answer. So this is equal to pi over 3. And if we look over here at the green graph on the right, this angle here is pi over 3. And the cosine of it will be equal to 1/2. But also, all the y-coordinates of these points is also equal to 1/2, which means that the cosine of all of those angles, which corresponds to these points, will be 1/2 as well. But the only one in the interval 0 to pi is this pi over 3. All right, let's look at another example. Let's find the exact value of inverse sine of negative 1/2. Again, we have the following definitions, but now we'll be working with this first one here. So y is equal to inverse sine of x means that sine of y is equal to x, but moreover, y is in this interval, negative pi halves to pi halves. And let's graph the sine function to see why this interval works. So if here's the y-axis, and here's the x-axis, sine will look like this. Where this here is pi over 2, this is pi, this is 3 pi over 2, and so on. And over here, this is negative pi over 2. This is negative pi. This is negative 3 pi over 2. And again, y equal to sine x is not a one-to-one function. However, on the interval from negative pi halves to pi halves, for example, it is 1-to-1, isn't it? So on that restricted domain, sine will be 1-to-1, and therefore it will have an inverse. And remember, the restricted domain is now the range of our inverse. And notice that is a different interval than we just saw with the cosine function. In fact, on the interval from 0 to pi, sine is not 1-to-1. All right, so let's compute our value here. Let's let y equal to inverse sine of -1/2. This means we're looking for an angle y whose sine is equal to -1/2. Thinking of our unit circle, the sine of this angle here, which is 7 pi divided by 6, is equal to -1/2 because the y-coordinate of this point is -1/2. But also this angle here, which corresponds to 11 pi divided by 6, also has sine equal to -1/2, because the y-coordinate of this point is also -1/2. And the sine of any of their coterminal angles will also equal -1/2. However, looking down here in the table, what we need to do is find the angle in this interval that has sine equal to -1/2. Now, a very common mistake that students will make is they will think that this interval, -pi/2 to pi/2, corresponds to any angle in quadrants 4 and 1. And so they'll answer this 11 pi divided by 6. However, 11 pi divided by 6 does not lie between -pi/2 and pi/2. So what we need to do is find the angle that is coterminal with 11 pi divided by 6, whose sine is equal to -1/2. And that angle would be -pi divided by 6, which is our answer. So let's write that here, -pi divided by 6. And let's look at that on this graph over here. This angle here is -pi divided by 6. The sine of it will be equal to -1/2, but also the y-coordinates of all of these points here is -1/2. Which means that the sine of all of those angles corresponding to those points will also equal -1/2. But the only one in the restriction is -pi divided by 6. So we have to be really careful when computing inverse sine values of a negative input. And this is the same thing with computing inverse tangent of negative inputs. So let's see an example of that. Let's find the exact value of inverse tangent of -1. Again, we have the following definitions, and we'll be working with the last one down here. So y equal inverse tangent of x means that tangent of y is equal to x, and moreover, y has to be in this interval, -pi/2 to pi/2. So let's take a look at the graph of tangent to see why this interval works. Now y equal to tangent of x looks like this. Here's the y-axis. Here's the x-axis. Its graph has vertical asymptotes at pi/2, at 3 pi/2, and so on, as well as -pi/2 and -3 pi/2, and so on. And within each of these consecutive vertical asymptotes, tangent looks like this. And notice that tangent is not a one-to-one function, and therefore it will not have an inverse on its entire domain. However, it will have an inverse if we restrict its domain, for example, to just use this branch here. Therefore, we can restrict the domain of the tangent function to this interval, -pi/2 to pi/2. And on this restricted domain, the tangent function will be one-to-one. And the domain of the tangent function will then be the range of the inverse. So our answers to inverse tangent values have to lie in that interval. So let's look at our example. Let's let y equal inverse tangent of -1, which means that we're looking for an angle y whose tangent is equal to -1. But moreover, y has to lie in that restricted interval, -π/2 to π/2. Again, let's think of our unit circle. This angle here, 3π divided by 4, will have tangent equal to -1 because the ratio of the y-coordinate to the x-coordinate will be -1. But also the tangent of this angle here, 7π divided by 4, will also be -1 because the ratio of the y-coordinate to the x-coordinate here is -1. And the tangent of any of their coterminal angles is also equal to -1. But remember, looking down here, we have to have our answer in this interval. And again, be very careful here. Don't just look in quadrants 4 and 1 and be tempted to answer 7π divided by 4. We have to find the angle that's coterminal with 7π over 4, but that lies in this interval down here. And that angle would be -π over 4, wouldn't it? So let's write that up here. Our answer then is that inverse tangent of -1 is -π divided by 4. And again, let's look at that over here on this green graph. This angle here is -π over 4, and the tangent of it is -1. But also the y-coordinate of all these points is also -1. Which means that the angles corresponding to those points will also have tangent equal to -1. But none of those angles are in our restriction. So be very careful when computing inverse sine and inverse tangent when the input is a negative value.
Thank you, and we'll see you next time. Let's look at compositions involving inverse trig functions. For example, let's find the exact value of tangent of inverse cosine of square root of 3 over 2. So let's let y equal this angle here. So y is equal to inverse cosine of square root of 3 over 2. And if this is y here, then we're looking for tangent of y. So if y is equal to inverse cosine of square root of 3 over 2, that means that cosine of y is equal to the square root of 3 over 2, where y is in the interval from 0 to π. Remember that when computing inverse cosine values, our answers must lie in this interval 0 to π. Thinking of our unit circle, and remembering that the cosine is the x-coordinate of the point of intersection of the terminal side of the angle and the unit circle. And we know that the terminal side of the angle π divided by 6 intersects the unit circle at square root of 3 over 2, 1/2. Therefore, the cosine of this angle is root 3 over 2. And moreover, it's the only angle in this interval whose cosine is equal to square root of 3 over 2. That is, y is equal to π divided by 6. And therefore, tangent of y is equal to tangent of π divided by 6, which is equal to y divided by x, or 1/2 divided by the square root of 3 over 2. And the 2's will cancel, which gives us 1 divided by square root of 3. And then rationalizing gives us our answer of square root of 3 divided by 3.
All right, let's look at another example. Let's find the exact value of arc sine of cosine of 4 pi divided by 3. Well, what is cosine of 4 pi divided by 3? Well, thinking of our unit circle, the terminal side of the angle 4 pi over 3 intersects the unit circle at -1/2 negative square root of 3 over 2. And the cosine is the x-coordinate of this point here, or -1/2. So therefore, this is equal to arc sine of -1/2, which is equal to negative pi divided by 6. Because remember, y equal arc sine of -1/2 is equivalent to sine of y equal to -1/2, but moreover, y is in the interval negative pi halves to pi halves. And thinking again of the unit circle, we know that the terminal side of this angle, which is 7 pi divided by 6, intersects the unit circle at negative square root of 3 over 2, -1/2. But also the terminal side of this angle here, 11 pi divided by 6, intersects the unit circle at square root of 3 over 2, -1/2. Which means the sine of both of these angles is equal to -1/2. Because remember that the sine is the y-coordinate of these points here. However, neither of these angles lie within the restriction of arc sine. So what we need to do is determine the angle that's coterminal with 11 pi over 6 lying in that interval, which is this negative pi over 6 up here. So this is our answer. And this is how we work with compositions involving inverse trig functions. Thank you, and we'll see you next time. Let's look at compositions involving inverse trig functions. For example, let's find the exact value of tangent of arc cosine of -5/6. Now this here is an angle, so let's call it theta. In other words, let's let theta equal arc cosine of -5/6. And therefore, if this is theta, then we're looking for tangent of theta. So if theta is equal to arc cosine of -5/6, that means that cosine of theta is equal to -5/6, and moreover, theta is in quadrant 2. Now, why is theta in quadrant 2? Well, looking here, we see that cosine of theta is less than 0, which means there's two possibilities. Either theta is in quadrant 2 or quadrant 3. However, remember, looking back up here, theta is equal to the arc cosine of -5/6, which means that theta also has to be in the range of the arc cosine function, which, remember, the range of arc cosine is the interval 0 to pi. And therefore, theta cannot be in quadrant 3, which means theta is in quadrant 2. And therefore, we can draw the following triangle. Because remember that cosine of theta is equal to x divided by r. And this is equal to -5 divided by 6. And notice over here we're putting the negative with the x because x is negative in quadrant 2, and r is always positive. And therefore, by the Pythagorean theorem, we can find y. That is, x squared plus y squared is equal to r squared, or -5 squared plus y squared is equal to 6 squared, or 25 plus y squared is equal to 36. And therefore, y squared is equal to 36 minus 25, which is 11. Or y is equal to plus or minus the square root of 11. But which one do we choose, the plus or the minus? Remember that y is in quadrant 2 here. And in quadrant 2, y is greater than 0. So we're going to choose the positive value. That is, y here is equal to the square root of 11. Now remember, looking back up here, we're looking for tangent of theta, which is equal to the y-coordinate divided by the x-coordinate, which is equal to square root of 11 divided by -5, or negative square root of 11 divided by 5. And this is an example of how we work with compositions involving inverse trig functions. Thank you, and we'll see you next time. Let's look at verifying trigonometric identities. For example, let's verify this identity here. Now, when verifying trigonometric identities, we can either work with one side until we get it equal to the other side, or work with both sides at the same time until we get them equal to one another. So in this case, the left-hand side looks a little bit more complicated, so let's start working with that side first. That is, this is equal to 1 minus cosine squared y divided by, and then foiling the denominator, we get 1 plus sine y minus sine y, and then minus sine squared y. Now the outer and inner terms will cancel, which leaves us with 1 minus cosine squared y divided by 1 minus sine squared y. Now let's recall the following Pythagorean identity. That sine squared y plus cosine squared y is equal to 1. Now, if we subtract cosine squared y from both sides, what do we get? We have that sine squared y is equal to 1 minus cosine squared y, which is the numerator over here on the left, isn't it? And if we subtract sine squared y from both sides, what do we get? We have cosine squared y is equal to 1 minus sine squared y, which is the denominator over here on the left. So let's use those facts. That is, this is equal to sine squared y divided by cosine squared y, which is equal to tangent squared y, which is our right-hand side, and so we verified this identity. All right, let's look at another example. Let's verify this identity here. Now with this identity, let's work with both sides at the same time. Now recall that cosecant of x is equal to 1 divided by sine of x. And also cotangent of x is equal to cosine of x divided by sine of x. So we'll use this on the left-hand side and this on the right-hand side. That is, this left-hand side is equal to 1 divided by sine x minus sine x. And the right-hand side is equal to cosine of x divided by sine x times cosine x. And now we can find a common denominator on the left-hand side. That is, this is equal to 1 minus sine squared x divided by sine x. And by the Pythagorean identity we just saw in the last example, the numerator here is equal to cosine squared x. But isn't that the same expression that we have on the right-hand side over here? Because on the right-hand side, this is equal to cosine x times cosine x, which is cosine squared x. Still divided by sine x. And therefore, these are equal, and we verified the identity. And these are a few examples of how we verify trigonometric identities. Thank you, and we'll see you next time. Let's work with the sum and difference identities. For example, let's find the exact value of sine of pi over 12 by using a sum or difference identity. Well, let's first recall these identities. Now, since we're looking for a sine value, we'll want to use one of the first two identities here. So what we need to do is find two angles, A and B, that either add or subtract to give us this pi over 12. But moreover, whose sine and cosine values we know. Now let's recall some of our common trigonometric angles. Pi over 2, pi over 6, pi over 4, pi over 3, and so on. Now we know the sine and cosine of all of these angles. We want to find two of them that will add or subtract to give us pi over 12. And looking here, these denominators 4 and 3 multiply together to give us 12, so they seem pretty promising. And in fact, pi divided by 12 is equal to pi divided by 3 minus pi divided by 4. And since we've written our angle pi over 12 as a difference, we'll be using this difference identity for sine over here. Namely, sine of pi over 12 is equal to the sine of pi over 3 minus pi over 4, which is equal to, by this identity, the sine of the first angle, or sine of pi over 3, times the cosine of the second angle, or cosine of pi over 4, minus cosine of the first angle, or cosine of pi over 3, times the sine of the second angle, or sine of pi over 4, which is equal to the sine of pi over 3 is square root of 3 over 2, times cosine of pi over 4 is square root of 2 over 2, minus cosine of pi over 3 is 1/2, times sine of pi over 4, which is square root of 2 over 2. And this is equal to the square root of 6 divided by 4 minus the square root of 2 divided by 4, or the square root of 6 minus the square root of 2, all divided by 4, which would be our answer. Now, is this the only way we could have written pi over 12 as a sum or difference of these common trigonometric angles? And it isn't. It is not the only breakup. In fact, let's compute this. Pi divided by 4 minus pi divided by 6. This is equal to 6 pi minus 4 pi divided by 24, or 2 pi divided by 24, which is pi over 12. That is, pi over 12 can also be written as this difference here. Which means we could have also computed sine of pi over 12 as follows. Sine of pi over 12 is also equal to sine of pi over 4 minus pi over 6. And by this identity, this is equal to sine of the first angle, or sine of pi over 4, cosine of the second, or cosine of pi over 6, minus cosine of the first, or cosine of pi over 4, times sine of the second, or sine of pi over 6, which is equal to square root of 2 over 2 times the square root of 3 over 2 minus square root of 2 over 2 times 1/2, which is equal to the same answer, square root of 6 minus square root of 2, all divided by 4. So in some cases, there's more than one way to apply these sum and difference identities. Thank you, and we'll see you next time. Let's work with the sum and difference identities. For example, let's find the exact value of this expression here by using a sum or difference identity. Now, to compute this value here, without using one of these identities would be very challenging, because 16 degrees is not one of our common trigonometric angles. Neither is 14 degrees. However, the sum and difference identities will be very helpful here. Let's recall these identities. Now, matching our expression here to the right-hand sides of these identities, we see it matches the third one here, with A equal to 16 degrees and B equal to 14 degrees. That is, this is of the form cosine A, cosine B, minus sine A, sine B. And looking over here in our table, we know that this has to equal cosine of A plus B. Which is equal to cosine of 16 degrees plus 14 degrees. And 16 plus 14 is 30. So this is cosine of 30 degrees, which is one of our common trigonometric angles. And we know that the cosine of it is square root of 3 over 2. So using these identities helped us compute this value quite easily. All right, let's look at another example. Let's use a sum or difference identity to find the exact value of this expression here. Again, pi over 8 is not one of our common trigonometric angles. Neither is 5 pi divided by 8. But these sum and difference identities can help us solve this quite easily. Again, we're going to compare our expression to the right-hand sides here, and we see that it matches this fifth one here with A equal to pi divided by 8 and B equal to 5 pi divided by 8. That is, it's of the form tangent of A plus tangent of B divided by 1 minus tangent of A times tangent of B. And looking back over here in the table, we know this has to equal tangent of A plus B. Which is equal to tangent of pi divided by 8 plus 5 pi divided by 8, which is equal to tangent of 6 pi divided by 8, or tangent of 3 pi divided by 4, which is one of our common trigonometric angles. And we know that the tangent of it is equal to -1. So again, these identities were very helpful in solving this problem. Thank you, and we'll see you next time. Let's work with the sum and difference identities. For example, let's find cosine of alpha minus beta if sine of alpha is -5/13, cosine of beta is 12/13, alpha is in quadrant 3, and beta is in quadrant 4. Well, let's recall the difference formula for cosine. We have cosine of alpha minus beta is equal to cosine of alpha, cosine of beta, and then plus sine of alpha times sine of beta. Remember, with the cosine identities, if this is a minus, then this is a plus. Now we're given that sine of alpha is -5/13. Therefore, we know this already. And we're also given that cosine of beta is 12/13, which means we know this as well. So it remains to find cosine of alpha and sine of beta. Now there are different approaches here. We could use identities, for example, but let's use triangles instead. Now we're given that sine of alpha is equal to -5/13, and moreover, alpha is in quadrant 3, which means we can draw the following triangle. Because remember, sine of alpha is y divided by r. And notice we're putting the negative with the y because y's are negative in quadrant 3, and r is always positive. And then we can use the Pythagorean theorem to find x here. Namely, x squared plus y squared is equal to r squared, or x squared plus -5 squared is equal to 13 squared, or x squared plus 25 is equal to 169, and therefore x squared is equal to 144, which means x is plus or minus the square root of 144, which is equal to plus or minus 12. Now remember that x's are negative in quadrant 3, which means we're going to choose the negative possibility down here. That is, x is equal to -12. Now looking back over here on the left, remember that we need to know what cosine of alpha is. And remember that cosine of alpha is equal to x divided by r, which is equal to -12 divided by 13. All right, so it still remains to find this sine of beta here. So let's do the same thing. We're given that cosine of beta is equal to 12 over 13. And beta is in quadrant 4. So we can draw the following triangle, remembering here that cosine is the x divided by the r. So our x is 12 and our r is 13. And again, we can use the Pythagorean theorem to help us find y. Namely, x squared plus y squared is equal to r squared. Or 12 squared plus y squared is equal to 13 squared. Or 144 plus y squared is equal to 169. Which means y squared is equal to 169 minus 144, which is 25. And therefore, y is equal to plus or minus the square root of 25, which is equal to plus or minus 5. Now, since y's are negative in quadrant 4, we're going to choose the negative down here. That is, y is equal to negative 5. Now remember, we need to find sine of beta. So let's compute that over here on the left. Sine of beta is equal to y divided by r, which is equal to this negative 5 divided by 13. Okay, and now we have all the pieces to compute cosine of alpha minus beta. In other words, looking up here on the right, we found cosine of alpha, so we know that. We're given cosine of beta, as well as sine of alpha. And looking down here on the left, we just found sine of beta. And therefore, cosine of alpha minus beta is equal to cosine of alpha, which is negative 12 over 13, times cosine of beta, which is 12 over 13, plus sine of alpha, which is negative 5 over 13, times sine of beta, which is negative 5 over 13, which is equal to negative 144 divided by 169, plus 25 divided by 169, which is equal to negative 119 divided by 169, which would be our answer. And this is an example of how we work with the sum and difference identities. Thank you, and we'll see you next time. Let's verify trigonometric identities that use the sum and difference formulas. For example, let's verify this identity here. Now we see on the left that we have cosine of a difference. So let's recall the difference formula for cosine. The difference formula for cosine is that the cosine of a minus b is equal to the cosine of a times the cosine of b plus the sine of a times the sine of b. And we'll use that here. That is, the left-hand side is equal to the cosine of x times the cosine of 3 pi divided by 2 plus the sine of x times the sine of 3 pi divided by 2. And this is equal to the cosine of x times the cosine of 3 pi divided by 2, which is 0, plus the sine of x times the sine of 3 pi divided by 2, which is negative 1. And cosine x times 0 is equal to 0. And so we're left with negative sine of x, which, looking up here, is the right-hand side of this identity that we're trying to prove, which means we have verified this identity. All right, let's look at another example. Let's verify this identity here. Looking on the left-hand side of this equation, we have the sign of a difference. So let's recall the difference formula for sine. It states that the sine of a minus b is equal to the sine of a times the cosine of b minus the cosine of a times the sine of b. And using this here on the left-hand side gives us that this is equal to the sine of x times the cosine of y minus the cosine of x times the sine of y, still all divided by the cosine of x times the cosine of y. Now let's divide each term in the numerator by the denominator. That is, this is equal to the sine of x times the cosine of y divided by the cosine of x times the cosine of y minus the cosine of x times the sine of y divided by the cosine of x times the cosine of y. Now on this first fraction, we can cancel a cosine y from the numerator and the denominator. And on the second fraction, we can cancel the cosine x from the numerator and the denominator, which leaves us with sine x divided by cosine x minus sine y divided by cosine y. But sine x divided by cosine x is equal to tangent x, and sine y divided by cosine y is tangent of y, which is exactly the right-hand side of this identity that we wanted to verify. And so we have verified the identity. Thank you, and we'll see you next time. Let's look at verifying trigonometric identities that involve the double angle formulas. For example, let's verify this identity. Well, we can start working with the left-hand side here. This is equal to sine x plus cosine x times sine x plus cosine x. And now we can FOIL. So this is sine squared x plus sine x cosine x, and then plus cosine x sine x, and then plus cosine squared. Now sine x cosine x and cosine x sine x are the same, so we'll have two of them. That is, this is equal to sine squared x plus 2 sine x cosine x, and then plus cosine squared x. Now let's group these two together. In other words, this is equal to sine squared x plus cosine squared x, and then plus 2 sine x cosine x. Now, why did we do that? Because remember, we have the following Pythagorean identity. Sine squared x plus cosine squared x is 1, which we can use here. That is, this is just 1. So this is equal to 1 plus 2 sine x times cosine x. Now remember, the double angle formula for sine. Namely that sine 2x is equal to 2 sine x cosine x. So let's use that here, which means that this is equal to 1 plus sine 2x, which is our right-hand side. And therefore, we've verified this identity. Okay, let's see another one. Let's verify this identity. We're going to start working here on the right-hand side. Now, looking in the denominator here, there is another Pythagorean identity that will help us. Namely, 1 plus tangent squared x is equal to secant squared x. So let's use that here. Namely, this is equal to 1 minus tangent squared x divided by secant squared x. And now let's divide both terms in the numerator by secant squared x, which gives us 1 divided by secant squared x minus tangent squared x divided by secant squared x. And now let's convert everything to sine and cosine. In other words, this is equal to 1 over secant x is cosine x, and so 1 over secant squared x is cosine squared x. And then minus, now tangent x is sine x over cosine x, so tangent squared x is sine squared x over cosine squared x. And secant squared x is 1 over cosine squared x. Now, what is this simplified to? Remember, when we divide fractions, it's the same as multiplying the numerator by the reciprocal of the denominator. In other words, this is sine squared x divided by cosine squared x, and then times cosine squared x over 1. Now, won't these cosine squared x's cancel? So all we're left with then is just sine squared x. That is, this is equal to cosine squared x minus sine squared x. Now let's recall all the double angle formulas. Unlike sine and tangent, cosine has 3 different double angle formulas. But if we look at them, what we just got is equal to the right-hand side of the first one, which means that what we just got is equal to cosine of 2x. So this is equal to cosine 2x, which is our left-hand side. And so we verified this identity. And this is how we verify trig identities that involve the double angle formulas. Thank you, and we'll see you next time. Let's learn about the half-angle identities. For example, let's use a half-angle identity to find the exact value of sine of 22.5 degrees. Well, let's recall these identities. Now, since we're looking for a sine value, we'll use this first identity here. So let's let u over 2 equal 22.5 degrees. That is, u over 2 is equal to 22.5 degrees. Or multiplying both sides by 2 gives us that u is equal to 2 times 22.5 degrees, or 45 degrees, which we needed to know so we can plug that value of u into this identity over here. Now there's one other issue with this formula, isn't there? What does this plus or minus mean? Does that mean there's two answers every time? No, we choose plus or minus depending upon what quadrant u over 2 lies. And since 22.5 degrees, or u over 2, is in quadrant 1, we'll choose the plus, because sine values are positive in quadrant 1. And now we're ready to compute our value. Sine of 22.5 degrees is equal to, we're choosing the positive, square root of 1 minus cosine of u, and u we found to be 45 degrees, all divided by 2. Now 45 degrees is one of our common trigonometric angles, and the cosine of it is square root of 2 over 2. Now let's simplify this numerator by finding a common denominator. The common denominator would be 2, so this numerator here is 2 minus square root of 2 divided by 2. And we still have the denominator of 2. And this is equal to the square root of 2 minus the square root of 2, all divided by 4. And since the square root of 4 is 2, we can write our answer as the square root of 2 minus square root of 2, all divided by 2. All right, let's look at another example. Let's use the half-angle identities to find the exact values of cosine of 5 pi over 12 and tangent of 5 pi over 12. Again, let's recall these identities. And now, since we're looking for a cosine and a tangent value, we'll be using these last two identities down here. Again, let's let u over 2 equal this angle here of 5 pi over 12. That is, u over 2 is equal to 5 pi over 12. And again, multiplying both sides by 2 gives us that u is equal to 2 times 5 pi over 12, or 5 pi divided by 6. Which we then can plug into our identities over here, wherever we see a u. And notice with the tangent identities, there's 3 different identities you can use, but we'll be using the first one. And again, we're going to need to determine whether we're going to choose the plus or the minus for both of these. And remember, what determines that is what quadrant u over 2 lies. Well, since 5 pi over 12 lies in quadrant 1, we'll choose the plus for both because both cosine and tangent are positive in quadrant 1. Now there's a common mistake that students make often. We want to be sure that we're looking at what quadrant u over 2 lies and not u to determine whether we're going to choose the plus or the minus. For example, let's look at our situation here. Five pi over 12 is pi over 12 short of 6 pi over 12, which is pi halves, so it lies about right here. Now what about u? Remember, looking back up here, we found that u is equal to 5 pi divided by 6. And 5 pi divided by 6 is over here in quadrant 2. Now, since cosine and tangent are both negative in quadrant 2, students are tempted to choose the negative choices here because they're thinking about what quadrant u lies rather than what quadrant u over 2 lies. Don't make that mistake. Always look at what quadrant this u over 2 lies and not u to determine the plus or minus in these identities. All right, let's compute our values. Cosine of 5 pi divided by 12 by this identity here is equal to, we're choosing the positive, square root of 1 plus cosine of u, which was 5 pi divided by 6, all divided by 2. Now 5 pi divided by 6 is one of our common trigonometric angles, and the cosine of it is negative square root of 3 divided by 2. Again, let's find a common denominator in the numerator, and that common denominator would be 2. We still have the denominator of 2, which is equal to the square root of 2 minus the square root of 3, all divided by 2 times 2, which is 4. And since the square root of 4 is 2, we can simplify this answer as 2 minus the square root of 3, all divided by 2. All right, what about our tangent value? Tangent of 5 pi over 12 by this identity here is equal to, we're choosing the positive, square root of 1 minus cosine of u, or cosine of 5 pi divided by 6, all divided by 1 plus cosine of u, or 5 pi divided by 6. And again, cosine of 5 pi divided by 6 is negative root 3 over 2. So we'll have 1 minus a negative root 3 over 2, or plus root 3 over 2, all divided by 1 minus square root of 3 over 2. And now writing both the numerator and denominator with a common denominator of 2 gives us the square root of 2 plus the square root of 3 over 2, all divided by 2 minus the square root of 3 over 2. And now the 2's will cancel, which leaves us with our answer of the square root of 2 plus square root of 3 all over 2 minus square root of 3. And this is how we use the half-angle identities. Just be careful that you're looking at what quadrant u over 2 lies and not u when determining the plus or minus in these formulas.
Thank you, and we'll see you next time. Let's work with the half-angle identities. For example, if sine of theta is negative 3/5 and theta is between 3 pi halves and 2 pi, we'll find the exact value of sine of theta over 2. Let's recall the half-angle identity for sine. We have that sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine theta, all divided by 2. Now we're given that sine of theta is negative 3/5 and that theta is between 3 pi halves and 2 pi. Therefore, we can draw the following triangle. Remembering that sine of theta is equal to y divided by r. And if this is negative 3/5, notice down here we put the negative with the y because y's are negative in quadrant 4 and r is always positive. And remember that cosine of theta is equal to x divided by r. And so if we can find x here, then we'll be able to determine what cosine of theta is, which we then can use over here on the left to determine sine of theta over 2. And to find x, we can use the Pythagorean theorem to help us. Namely, we have x squared plus y squared is equal to r squared. Therefore, x squared plus negative 3 squared is equal to 5 squared. Or x squared plus 9 is equal to 25.
Or x squared is equal to 25 minus 9, which is 16, which means that x is equal to plus or minus the square root of 16, or x is equal to plus or minus 4. But x is in quadrant 4, and in quadrant 4, x is greater than 0. Therefore, we're going to choose the positive value here. And therefore, cosine of theta is equal to positive 4 divided by 5, which we can plug into our half-angle formula over here. But there's one more issue with this formula, isn't there? What does this plus or minus mean? Does that mean that there's two solutions here? No, we're going to choose either the positive or the negative, depending upon the quadrant that theta over 2 lies. That is, if sine of theta over 2 in that quadrant is positive, we'll choose the positive, and if it's negative, we'll choose the negative. Now remember that we're given that theta lies between 3 pi halves and 2 pi. However, we don't want to know where theta lies, we want to know where theta over 2 lies. So let's divide everything by 2 then. So 3 pi divided by 2, all divided by 2 is 3 pi fourths. And 2 pi divided by 2 is pi. So therefore, theta over 2 lies between 3 pi fourths and pi. That is, if this is 3 pi fourths and this is pi, that means theta over 2 is somewhere in here. And since signs are positive in quadrant 2, sine of theta over 2 is greater than 0. Therefore, we're going to choose the positive value up here in our formula. Now, there's a common mistake that students make that should be pointed out here. Looking over at the figure on our right, we see that theta is in quadrant 4. And students will think because theta is in quadrant 4 and signs are negative in quadrant 4, that they should choose the negative value here. Don't look at where theta lies, look at where theta over 2 lies. All right, so then this is equal to, we're choosing the positive, we have square root, 1 minus, we found that cosine theta was 4/5, still have all divided by 2, which is equal to the square root of 1 minus 4/5, which is 1/5, divided by 2, which is the square root of 1 over 10, or rationalizing, we get square root of 10 over 10, which would be our answer. And this is how we work with these half-angle identities. Thank you, and we'll see you next time. Let's look at solving trig equations. For example, let's solve this equation here, but only on the interval 0 to 2 pi. We can begin by subtracting 3 from both sides of this equation, which would give us 2 times sine of theta is equal to -1. And now dividing both sides by 2 gives us that sine of theta is equal to -1/2. So we need to find all angles theta in this interval here, 0 to 2 pi, that have sine equal to -1/2. Well, let's recall our unit circle. Remember that the sine is the y-coordinate of the point of intersection of the terminal side of the angle and the unit circle. So looking down here in quadrant 3, we see that the y-coordinate of this point is -1/2, which corresponds to the angle of 7 pi divided by 6. But also over here in quadrant 4, the y-coordinate of this point is also -1/2, which corresponds to the angle of 11 pi divided by 6. Therefore, the sine of both of these angles will equal -1/2. which means our answer here then is theta is equal to 7 pi divided by 6 or 11 pi divided by 6. All right, let's look at another example. Again, let's solve this equation only on the interval 0 to 2 pi. We can begin by subtracting 2 from both sides, which gives us secant of theta is equal to -2. Now remember that secant of theta is equal to 1 divided by cosine of theta, or cosine of theta is equal to 1 divided by secant of theta. And therefore, if secant of theta is equal to -2, then we're looking for angles theta such that cosine of theta is 1 divided by -2, or -1/2. Again, recalling our unit circle, and remembering that the cosine of theta is the x-coordinate of the point of intersection of the terminal side of the angle and the unit circle. We see that the x-coordinate of this point here in quadrant 2 is -1/2, which corresponds to the angle of 2 pi divided by 3. But also down here in quadrant 3, the x-coordinate of this point is also -1/2, which corresponds to the angle of 4 pi divided by 3. Therefore, our answer here would be theta is equal to 2 pi divided by 3, or 4 pi divided by 3. All right, let's look at one more example. Again, let's find all solutions to this equation, but only in the interval 0 to 2 pi. We'll begin by adding 1 to both sides, which gives us cotangent of theta is equal to 1. Now remember that cotangent of theta is equal to cosine of theta divided by sine of theta. But we just saw that the cosine of theta was the x-coordinate of the point of intersection of the terminal side of the angle and the unit circle, and the sine of theta was the y-coordinate. So this would be equal to x divided by y. So therefore, we are looking for angles in the interval 0 to 2 pi where this ratio of x to y is equal to 1. And this will happen at pi over 4 as well as 5 pi over 4. Because remember our unit circle. At pi over 4, the ratio of x to y here will be equal to 1. But also down here in quadrant 3, the ratio of x to y will also equal 1, which corresponds to the angle of 5 pi divided by 4. And don't forget this angle down here in quadrant 3. Most students will only remember the angle in quadrant 1, but the ratio of x to y in quadrant 3 will also yield a positive number. Therefore, our answer here is theta is equal to pi divided by 4, or 5 pi divided by 4. And this is how we solve trigonometric equations on this interval 0 to 2 pi. Thank you, and we'll see you next time. Let's solve trig equations. For example, let's find all solutions to this equation here. We'll begin by subtracting square root of 2 from both sides, which gives us 2 sine theta is equal to negative square root of 2. And now dividing by 2 gives us sine of theta is equal to negative square root of 2 over 2. Now remember, with your unit circle, the sine of theta is the y-coordinate of the point of intersection of the terminal side of the angle and the unit circle. And looking down here in quadrant 3, we see that the y-coordinate of this point is negative root 2 over 2, which corresponds to the angle of 5 pi divided by 4. And also over here in quadrant 4, the y-coordinate is negative root 2 over 2, which corresponds to the angle of 7 pi divided by 4. Which means both of these angles will have sine equal to negative root 2 over 2. So theta is equal to 5 pi divided by 4 and 7 pi divided by 4. But what else? Are these the only two angles that have sine equal to negative root 2 over 2? And they aren't, because if we go around this unit circle 2 pi radians in either direction, we'll land on these same 2 points, which means that the sine of those angles will also equal negative root 2 over 2. And those angles are called coterminal angles because they share the same terminal side. For example, 5 pi divided by 4 plus 2 pi is a coterminal angle of 5 pi divided by 4. But so is 5 pi divided by 4 plus 4 pi. Or 5 pi divided by 4 minus 2 pi. Or 5 pi divided by 4 minus 4 pi. And so on. All of these angles will have sine equal to negative root 2 over 2. The same thing with the coterminal angles of 7 pi over 4. All of those angles will also have sine equal to negative root 2 over 2. So not only will these two angles have sine equal to negative root 2 over 2, but also any of their coterminal angles. And we write that in the following way. Theta is equal to 5 pi divided by 4 plus 2k pi, where k is an element of z. Where this notation here means k is an integer. For example, when k is equal to 0, we get this angle of 5 pi divided by 4. And when k is equal to 1, we get this angle up here. When k is equal to 2, we get this angle. When k is equal to negative 1, we get this angle. When k is equal to negative 2, we get this angle, and so on. All of these angles will have sine equal to negative root 2 over 2. And we also have that 7 pi over 4 and any of its coterminal angles also have sine equal to negative root 2 over 2. So theta is also equal to 7 pi divided by 4 plus 2k pi, where k is an integer. So any of these angles here will satisfy our equation, so these would be our answers. All right, let's look at another example. Let's find all solutions to this equation. Well, we can begin by factoring out a cosine theta from the left-hand side, which gives us cosine of theta times 2 cosine of theta plus 1 is equal to 0. So we have a product of factors equal to 0, which means either the first factor is 0, so cosine of theta is equal to 0, or the second factor is 0. So 2 cosine of theta plus 1 is equal to 0. Again, thinking of our unit circle and remembering that the cosine of theta is the x-coordinate of the point of intersection of the terminal side of the angle and the unit circle. And we see that up here the x-coordinate of this point is equal to 0, which corresponds to the angle of pi divided by 2. But also down here, the x-coordinate is also 0, which corresponds to the angle of 3 pi divided by 2. And so for this first equation here, the solution would be theta is equal to pi over 2, 3 pi over 2, or any of their coterminal angles. which remember from the last example, we can write that theta is